तेव्हा त्यांच्याकडे छान बर्फ पडतो की नाही? आणि त्यावेळी ऑस्ट्रेलियासारखे देश जे आहेत त्यांच्याकडे कडक उन्हाळा असतो. असं का असायला हवं? जर उत्तर गोलार्धामध्ये उन्हाळा आहे तर दक्षिण गोलार्धामध्ये हिवाळा. हे तुम्हाला थोडं विचित्र नाही वाटत? कोणाला वाटतं हे माझ्यासारखं विचित्र की पूर्ण पृथ्वीवरती तर आपल्याकडे उन्हाळा असायला हवा ना एक सोबत? अर्ध्या पृथ्वीवरती हिवाळा, अर्ध्या पृथ्वीवरती उन्हाळा, असं का असू शकतं? चला आपण बघूयात. म्हणजे अंतर हे कारण नाही आहे? तर नाही, पृथ्वी आणि सूर्यामधील अंतर हे नक्कीच कारण नाही आहे. दुसरं काय असेल बरं मग? तुला पृथ्वीबद्दलची अजून एक गंमतदार गोष्ट माहिती आहे का की आपली पृथ्वी जी आहे ती जेव्हा स्वतःभोवती फिरत असते तेव्हा तिची कक्षा ही 23.5 अंशांनी कललेली आहे. अच्छा. तर ही जी आणि जेव्हा पृथ्वी सूर्याभोवती फिरत असते तेव्हा ती ह्याच कक्षेमध्ये 23.5 अंशांनी कललेलीच फिरत असते. आणि अजून एक महत्त्वाची गोष्ट म्हणजे आपली पृथ्वी ही गोलाकार आहे. तर तुम्ही सर्वजण विचार करा की पृथ्वी ही गोल असल्यामुळे आणि ती कललेली असल्यामुळे हे एक कारण तर नाही ना असू शकत? चल तर आपण आहे एका डेमो थ्रू बघूयात. बरोबर. आता पुढचं तू सांगतेस? हो हो चालेल. तर इथे आपण ही कार्डशीट म्हणजे आता आपण एक थोड्या वेळासाठी पृथ्वीचा पृष्ठभाग समजूयात. आणि टॉर्च म्हणजे आपला सूर्य आहे. तर जेव्हा सूर्याची किरणे पृथ्वीवरती सरळ रेषेत पडतात तेव्हा ती आपल्याला अशी प्रखर दिसतात. आणि जेव्हा पृथ्वीच्या पृष्ठभागावरती अशी काही कोनात पडतात तेव्हा ती आपल्याला थोड्या जास्त पृष्ठभागावर पसरलेली दिसतात की नाही? सगळ्यांना दिसतंय ना? तर परत एकदा बघूयात. आता ती प्रखर आहेत कारण कमी पृष्ठभागावर पडत आहेत. आणि आता जेव्हा टिल्ट केलं तेव्हा ते काही कोणामध्ये पडत आहेत म्हणून ते जास्त जागेवर पसरलेत. हेच आता आपण आपल्या पृथ्वी गोलाबाबतीत कसं होतं ते बघूयात. तर पृथ्वी ही पृष्ठभागासारखी प्लेन तर नाही आहे ना, ती गोल आहे. म्हणून नेमकं हे कसं होतं ते आता आपण ह्या डेमो थ्रू बघूयात. तर ही नॉर्थ फेस, एन मीन्स हा नॉर्थ फेस आपल्याला दाखवतो म्हणजे आपला उत्तर गोलार्ध. आणि त्याच्या अपोजिटचा जो ॲक्सिस आहे तो म्हणजे आपला दक्षिण गोलार्ध. तर जेव्हा सूर्याची किरणे उत्तर गोलार्धावर पडताना सरळ पडतात तेव्हा ती आपल्याला तिथे प्रखर दिसतात. दिसतायत ना सगळ्यांना? आणि आत्ता जेव्हा हीच किरणे पॅरललमध्ये काही कोनात पडतात तेव्हा ती अशी पसरलेली दिसतात. आता तुम्हाला लाईटचा स्प्रेड दिसतोय का? हां. आता दुसऱ्या साईडने बघूयात हाच डेमो म्हणजे सगळ्यांना दिसेल. उत्तर गोलार्धामध्ये कसे प्रखर दिसत आहेत आणि दक्षिण गोलार्धामध्ये हेच किरणे आपल्याला आता अशी पसरलेली दिसत आहेत. म्हणजे जेव्हा सूर्याची थँक्यू गाईज म्हणजे जेव्हा सूर्याची किरणे सरळ पडतात तेव्हा ते कमी पृष्ठभाग व्यापतात आणि जेव्हा ती काही कोनात पडतात तेव्हा ते जास्त पृष्ठभाग व्यापतात. चला तर ह्यामुळे सीझन्स कसे होतात हे आपण आता थोडं डिटेलमध्ये बघूया. तर सर्वात आधी येणारा ऋतू म्हणजे उन्हाळा. तर उन्हाळ्यामध्ये काय होतं, पृथ्वी ही पृथ्वी इथे असते आणि सूर्य इथे आहे. तर इथे तुम्ही बघू शकता पृथ्वीचा जो हा कललेला अक्ष आहे तो सूर्याच्या दिशेने पॉइंट होतोय ना? हां. तर त्यामुळे सूर्याची जी किरणे पडत आहेत ती उत्तर गोलार्धामध्ये कमी क्षेत्रफळ व्यापतात आणि तेच दक्षिण गोलार्धामध्ये काही कोनात पडत असल्यामुळे जास्त क्षेत्रफळ व्यापतात. म्हणजे इथे लाईटची प्रखरता कमी आहे आणि इथे कशी आहे, जास्त आहे. म्हणून आपल्याला तेव्हा उत्तर गोलार्धामध्ये उन्हाळा तर त्याच्या अगदी अपोजिट दक्षिण गोलार्धामध्ये हिवाळा जाणवतो. हे लक्षात आलंय ना सर्वांच्या? चला तर आता त्यानंतर येणारा ऋतू म्हणजे शरद ऋतू. तर शरद ऋतूमध्ये पृथ्वी ही इथून इथेपर्यंत गेली आहे. आता इथे पृथ्वीचा अक्ष सूर्याकडे, कुठलाही अक्ष सूर्याकडे फेस करत नाहीये किंवा सूर्याकडे कललेला नाहीये. दिसतंय ना हे? तर इथे सूर्यकिरण असे दोन्ही गोलार्धांमध्ये समांतर पडतात, म्हणून इथे आपल्याला उन्हाची प्रखरता कमी जाणवते आणि ऊन कसं सौम्य असतं, म्हणून आपल्याला शरद ऋतूमध्ये असं कम्फर्टेबल फील होतं. आणि ह्यानंतर येणारा ऋतू म्हणजे हिवाळा. तर हिवाळ्यामध्ये अगदी उन्हाळ्याच्या उलट असतं. इथे आता आपली पृथ्वी इथून इथे गेली आहे. आता तुम्ही इथे बघू शकता पृथ्वीचा जो कललेला अक्ष आहे तो सूर्याकडे नसून तो सूर्याच्या विरुद्ध दिशेने कललेला आहे. दिसतंय ना आणि लक्षात पण येतंय ना. हां, तर आत्ता आपल्याला जी पृथ्वीवर पडणारी म्हणजे उत्तर गोलार्धामध्ये पडणारी जी किरणे आहेत ती काही कोनात पडतात, म्हणून इथे ते जास्त क्षेत्रफळ व्यापत आहेत. आणि दक्षिण गोलार्धामध्ये ती सरळ पडून तिथे कमी क्षेत्रफळ व्यापत आहेत. म्हणजे इथे काय असेल बरं, उन्हाची प्रखरता कशी असेल, कमी असेल, आणि इथे कशी आहे, जास्त आहे. म्हणून आपल्याला तेव्हा उत्तर गोलार्धामध्ये हिवाळा तर दक्षिण गोलार्धामध्ये उन्हाळा जाणवतो. तर ह्यानंतर येणारा ऋतू म्हणजे वसंत ऋतू, स्प्रिंग सीझन. ह्यामध्ये अगदी शरद ऋतूसारखंच असतं आणि इथेही आपली कुठलीच अक्ष म्हणजे उत्तर गोलार्ध आणि दक्षिण गोलार्ध हा सूर्याच्या दिशेने फेस करत नाही, म्हणून इथे सूर्याची किरणे दोन्ही गोलार्धांमध्ये समान क्षेत्रफळ व्यापतात. बघू शकता तुम्ही इथे, दिसतंय ना. हो, आणि म्हणून आपल्याला इथे उन्हाची प्रखरता कमी जाणवते. आणि ह्या सीझनमध्ये सुद्धा सेम ऑटमसारखं मीन्स शरद ऋतूसारखंच आपल्याला सौम्य ऊन जाणवतं आणि कम्फर्टेबिलिटी पण तेवढीच जाणवते. अशा प्रकारे ही आपली ऋतूचक्राची सायकल चालत असते. चला, तर आता ह्यावरनं आपण हे लक्षात घेतलं आहे का पृथ्वीची जी कललेली स्थिती आहे ती आणि पृथ्वीचा गोलाकारनेस हे आपल्या ऋतूचक्रामागचं कारण आहे. तर कळलं आहे ना सगळ्यांना.
पण शिवानी,
हां,
वसंत आणि शरद ऋतूमधला तर फरक समजलाच नाही.
अच्छा, चल तर हे आपण ना एका डेमो थ्रू बघूयात. आता हा ब्लॉक म्हणजे आपला सूर्य आहे असं कन्सिडर करूयात थोड्या वेळासाठी. आणि हा जो आपला पृथ्वी गोल आहे तो तर माहितीच आहे ना सगळ्यांना. आता इथे तुम्ही बघू शकता पृथ्वीचा उत्तर गोलार्ध हा सूर्याच्या दिशेने फेस करतोय ना. म्हणजे आता इथे कुठला ऋतू असेल, उन्हाळा, समर, राईट. आता आपली पृथ्वी फिरत फिरत ऑटमच्या इथे जाते, इथे गेली. म्हणजे आता आपला हा उत्तर गोलार्ध आणि दक्षिण गोलार्ध कुठलाही गोलार्ध सूर्याच्या दिशेने फेस करतोय का, नाही. त्यामुळे आपल्याला इथे सूर्याची किरणे सरळ रेषेत पडताना दिसत आहेत, दोन्ही गोलार्धांवरती समान पडत आहेत. म्हणजे आता इथे आपला कुठला ऋतू आहे, शरद ऋतू. आता पृथ्वी विंटरच्या इथे जाणार. आता तुम्ही बघताय का आपला जो उत्तर गोलार्ध आहे तो सूर्यापासून लांब गेलेला दिसतोय. हां, म्हणून आपल्याला इथे विंटर सीझन बघायला मिळतो. आता पृथ्वी स्प्रिंगच्या इथे येणार. आता आपल्याला दिसतंय का उत्तर गोलार्ध किंवा दक्षिण गोलार्ध कुठलाही गोलार्ध सूर्याच्या दिशेने वळलेला दिसतोय का, कुठे दिसतोय, नाहीये. हा उत्तर गोलार्ध इकडे फेस करतोय आणि दक्षिण गोलार्ध खाली दिसतंय. त्यामुळे सूर्याची किरणे दोन्ही गोलार्धांमध्ये समान पडत आहेत आणि म्हणून आपल्याला इथे स्प्रिंग सीझन जाणवतो. तर आता तुला फरक कळला का.
हो, आता माझा फरक लक्षात आला.
थँक्यू तिशांत. कळलं तुला आता.
मला हे तर समजलं, पण मला एक गोष्ट नाही लक्षात आली की पृथ्वीची कक्षा ही 23.5 अंशांनी कललेली का आहे.
अच्छा, तुझ्यासारखं सगळ्यांना हा प्रश्न पडलाच असेल. तर पृथ्वीची कक्षा कललेली का आहे ह्याचं उत्तर ना पृथ्वीच्या अगदी बालपणीच्या स्थितीत आहे. बिलियन्स ऑफ इयर्स अगो जेव्हा आपली सूर्यमाला तयार होत होती तेव्हा सूर्याभोवती असे काही वायू आणि धुळीचे कण गोल फिरत होते आणि हे कण गोल फिरता फिरता छोटे छोटे आकार तयार करायला लागले आणि हे आकार एकमेकांवरती टकरा घेऊन वेगवेगळे ग्रह तयार होऊ लागले. आणि तुला माहिती आहे का, आपल्या पृथ्वीने सुद्धा अशा बऱ्याचशा टकरा सहन केल्या आहेत. आणि अशाच एका टक्करेमध्ये जेव्हा म्हणजे पृथ्वीने अशा मेजर 10 टकरा सहन केल्या आहेत, आणि अशा शेवटच्या टकरेमध्ये एक मंगळ ग्रह एवढा आकार येऊन पृथ्वीला धडकला, आणि त्यामुळे आपल्याला आपला सूर्य, आपल्याला हा चंद्र मिळाला, आणि आपल्या पृथ्वीला थोडा कल पण मिळाला. चल हे आपण आता एका डेमो थ्रू बघूयात. बघ इथे तू बघू शकते, इथे हे दोन्हीही सॉलिड बॉडीज आहेत, पण त्यामधला फोर्स एवढा आहे की ते आपल्याला अगदी पाण्यासारखं किंवा द्रव पदार्थांसारखं मेल्ट होताना दिसत आहेत. आणि ह्याच धडकेमध्ये आपल्याला आपला सूर्य हे चंद्र मिळाला. तर सगळ्यांच्या लक्षात आलं ना आपल्याकडे सीझन्स का होतात ते, आणि आपल्याला चंद्रही याच धडकेमुळे मिळालेला आहे. चला, कुणाला काही प्रश्न असतील तर तुम्ही विचारू शकता, आणि तेही कुठल्याही भाषेमध्ये विचारू शकता, लाईक हिंदी, इंग्लिश, मराठी. व्हॉलेंटियर्स प्लीज गिव्ह देम माईक.
शिवानी आणि
थँक्यू सर. माईक.
ओके, यांनी ऋतुचक्राबद्दल हे जे काही प्रेझेंटेशन दिलं ते सगळ्यांना आवडलं, आणि काही नवीन गोष्टी शिकायला मिळालं की जे माहिती होतं तेच कळालं. आय होप नवीन गोष्टी कळाल्या पण. ठीक आहे, तर आता आपण काही प्रश्न घेऊ. जर कोणाला काही प्रश्न असतील मराठीमध्ये, इंग्लिशमध्ये, हिंदीमध्ये, कुठल्याही भाषेमध्ये विचारू शकता. प्रथम इथनं चालू करू. हां,
नाही, आवाज नाही येते.
हॅलो.
हां आता येतोय.
हॅलो सर, तर माझा डाऊट हा होता की इथे सीझनल चेंजेस एक्सप्लेन केले की इथे म्हणजे ह्या सीझनमध्ये हे चेंजेस, पण सध्या आपण जे बघतोय की लाईक समर नाही राहिला, विंटर नाही राहिला, रेनी नाही राहिला. विंटरमध्ये रेनी सीझन आपण बघतोय, आणि बऱ्याच वेळा असं होतं की खूप कडक उन्हाळा जाणवतो विंटरमध्ये सकाळी सुद्धा. तर आपण जर रिझन विचारलं तर बरेच लोक बोलतात की हे ग्लोबल वॉर्मिंगमुळे होतं, पण व्हॉट इज एक्झॅक्टली द रिझन, की काय होतं ग्लोबल वॉर्मिंगमुळे की आपल्याला परफेक्ट सीझन जाणवत नाही आहेत?
हां, तर हे जे काय आता यू आर सेईंग ना की अचानक खूप सारे बदल होतात, आणि हे जे काही फ्लक्च्युएशन्स होत आहेत, दीज आर वेदर फ्लक्च्युएशन्स. ओके, क्लायमेट जे आहे ते पूर्ण जर उत्तर गोलार्धाचं सगळं जे काही तापमान आहे ते तुम्ही ॲव्हरेज केलं तर त्यावेळेला तुम्हाला ॲव्हरेज केल्यानंतर काहीतरी फरक दिसेल. तर दक्षिण गोलार्धात किती तापमान आहे ॲव्हरेज, आणि उत्तर गोलार्धात किती तापमान आहे ॲव्हरेज, याच्यामध्ये फरक दिसेल. ठीक आहे, मग त्याच्यावरती ऑन टॉप ऑफ इट तुम्हाला काही वर खाली उतार चढ दिसतात, आणि ते लोकल फॅक्टर्सवरती डिपेंड करतात. तर आपल्याला हेही माहिती आहे की क्लायमेट चेंज जेव्हा होतं त्यावेळेला हे जे उतार चढ आहेत ते जास्त प्रखरतेने जाणवणार. ओके, सो हे जे काही बदल होत आहेत आत्ता, किंवा बऱ्याचदा असं दिसतं की अचानक थंडीमध्ये खूप सारं ऊन पडते किंवा खूप सारी गरमी जाणवते, किंवा मधूनच पावसाळा कधीतरी होतं, हे जे प्रकार आहेत ते फ्लक्च्युएशन्स आहेत. ओके, तर हे जे फ्लक्च्युएशन्स उतार चढ जे आहेत ते जास्त होत आहेत ते त्याच्यामुळे. ठीक आहे, पण जर तुम्ही पूर्ण उत्तर गोलार्धाला घेतलात आणि पूर्ण दक्षिण गोलार्धाला घेतलात आणि त्याचं तापमान जर ॲव्हरेज केलं तरी तुम्हाला तेच दिसेल की उन्हाळ्यामध्ये जास्त असते तापमान आणि हिवाळ्यामध्ये कमी असतं. ठीक आहे, तर हे जे ऋतू बदल जे होतं ते ऋतू हे पूर्ण गोलार्धात जे काही होतं आहे त्याच्याबद्दल आहे, आणि जे हवामान आहे ते लोकल असू शकतं.
ओके,
ठीक आहे,
थँक्यू सर.
अजून काही प्रश्न आहेत का? हे बघ इथे. ओके,
आता तुम्ही म्हणता की ऋतू आपल्या सूर्याच्या किरणाच्या ह्याच्यामुळे होतात, तर मग सूर्य कसा बनला?
ऋतू जे आपल्याकडे होतात ते सूर्याच्या किरणांमुळे होतात, दॅट इज ट्रू. आणि ते कसे पडतात पृथ्वीच्या पृष्ठभागावरती. पण सूर्य स्वतःहून कसा बनला ते एक फार गमतीची गोष्ट आहे. तर मी तुम्हाला दाखवतो. या इथे दिसतंय का तुला? तर सगळ्यात पहिल्यांदा जेव्हा सूर्यमाला तयार झाली ती जवळजवळ 4.5 बिलियन इयर्स, आता मला मराठीत त्याला अब्जवर्ष बहुतेक म्हणतात, मी शोधून काढीन काय नक्की म्हणतात ते, पण 4.5 बिलियन वर्षांपूर्वी पृथ्वीची निर्मिती झाली. ठीक आहे, आणि सूर्यमालेचीच निर्मिती झाली. ओके. तर सुरुवातीला सूर्य असा ताऱ्यासारखा नव्हता, तर इनिशियली खूप मोठा एक हायड्रोजनचा गोळा होता. ठीक आहे, आणि तो जो हायड्रोजनचा गोळा आहे तो सगळ्यात सेंटरमध्ये त्याची जी घनता होती ती खूप जास्त होती. आणि मग त्याच्यानंतर त्याच्यामध्ये न्यूक्लिअर रिॲक्शन्स तयार झाले. ओके. न्यूक्लिअर रिॲक्शन्स म्हणजे बरेचसे जे हायड्रोजनचे ॲटम असतात ते एकत्र येतात आणि ते हिलियम तयार करतात. ते जेव्हा एकत्र येतात तेव्हा एवढा मोठा स्फोट होतो की ते जे सूर्यापासून येणारे किरणं आहेत ती त्याच्यापासून तयार होतात. ठीक आहे. मग सूर्याची जी निर्मिती आहे ती त्या प्रकारे झाली. एका हायड्रोजनचा खूप मोठा गोळा होता, तो त्याच्या वजन सहन नाही करू शकला आणि त्याच्यामुळे तो खूप म्हणजे त्याची घनता वाढत गेली. आणि मग ती घनता वाढत गेल्यानंतर मग त्याच्यामध्ये न्यूक्लिअर रिॲक्शन्स तयार व्हायला लागले, स्फोट व्हायला लागले. आणि ते जे स्फोट आहेत ते आजही चालू आहे. ओके. आणि त्याच्यामुळे आपल्याला सूर्य जी आहे ती ऊर्जा देतो.
हॅलो. भारतीय उपखंडामध्ये आपण मुख्य 3 ऋतू म्हणतो, उन्हाळा, पावसाळा, हिवाळा. या आत्ता ऋतूचक्रामध्ये पावसाळ्याबद्दल असं काहीच
हां, बरोबर. सो पावसाळा हा जो आहे तो एक लोकल फिनॉमिना आहे की आपल्या आजूबाजूला जे काही समुद्र आहेत, ओके, आणि उन्हाळ्यामध्ये त्याच्यातनं त्या समुद्रातल्या पाण्याचं बाष्प होतं आणि मग जे काही वारे आहेत ते हे बाष्प जे आहेत ते भारतीय उपखंडावरती आणतात आणि मग त्याच्यापासून जो पावसाळा आहे तो तयार होतो. पण हे सगळीकडे अशाच प्रकारच्या गोष्टी होतात असं नाही. त्याच्यामुळे पावसाळा जो आहे तो एक लोकल फिनॉमिना आहे रादर दॅन ग्लोबल. जर तुम्ही पूर्ण उत्तर गोलार्धात बघितलं तर असं नाही तुम्हाला सापडणार की सगळीकडे मान्सून होतं. ठीक आहे.
ध्रुवावर ऋतूंची नेमकी तीव्रता किंवा परिस्थिती कशी असते दोन्ही ध्रुवांवर?
दोन्ही ध्रुवावरती कसं दिसतं? हां, हिवाळ्याच्या
नेमकं हिवाळा आणि उन्हाळा कसा होतो ते सांगायचं आहे का? अच्छा.
उत्तर ध्रुव. ओके. सो जेव्हा उन्हाळा असतो ना त्यावेळेला जर तुम्ही ध्रुवाकडे बघितलं, उत्तर ध्रुवाकडे बघितलं, तर हा जो उत्तर ध्रुव आहे तो या इथे दिसतोय, बरोबर. आणि पृथ्वी जी आहे ती गोल फिरते, त्याच्यामुळे दिवस आणि रात्र होते. पण आता विचार करा की जर पृथ्वी गोल फिरत असेल तर या ध्रुवावरती तुम्हाला काय दिसेल? सूर्य कधी मावळताना दिसेल का? नाही दिसणार. ठीक आहे. तर जेव्हा उन्हाळा असतो तेव्हा उत्तर ध्रुवावरती सूर्य सतत दिसत राहतो. अगदी 24 तास तुम्हाला ध्रुवावरती, जर तुम्ही उत्तर ध्रुवावरती असाल तर सूर्य तिथेच दिसेल, ओके, आकाशामध्ये. पण जेव्हा हिवाळा होतो त्यावेळेला हा जो उत्तर ध्रुव आहे तो पूर्णपणे रात्रीमध्ये असतो. ओके. तर तिथे जवळजवळ 6 महिन्याची अशी रात्र आणि 6 महिन्याचा दिवस असा प्रकार होतो. ठीक आहे. तो आता या इथे फॉर एक्झाम्पल दक्षिण गोलार्धामध्ये या इथे पूर्णपणे रात्र आहे. किती गोल पृथ्वी फिरली तरी सूर्याचे किरणं तिच्यापर्यंत पोचू शकणार नाही. मग ते कधी पोचायला लागतात तर यावेळी पहिल्यांदा सूर्याची किरणं आहेत ती पडायला लागतात दक्षिण गोलार्धावरती, दक्षिण ध्रुवावरती. ओके. आणि मग नंतर ती पडत राहतात जोपर्यंत आपण या जागी येतो. ओके. 24 तास तुम्हाला सूर्य दिसत राहील. ओके. तर तिथे दिवस आणि रात्र असे राहतच नाही. दिवस आणि रात्र ॲक्च्युली 6-6 महिन्यांचे होतात.
सर, ह्या सेम लॉजिकनं विषुववृत्तावरती कायम उन्हाळाच राहतो का?
नाही, विषुववृत्तावरती कायम उन्हाळा राहत नाही ना, कारण की तुम्ही जर विषुववृत्तावरती बघितलं तर या पोझिशनमध्ये हा जो विंटर आहे त्यावेळेला हा जो रात्रीतला जो भाग आहे तो जास्त वेळ आणि कमी वेळ ओके. सो फॉर एक्झाम्पल या इथे जो आहे तो या इथे दिवस जो आहे तो पूर्ण 24 तास राहतो आहे, बरोबर. त्याच्यानंतर तुम्ही या लॅटिट्यूडला गेलात तर इथे दिवस जास्त राहतो आणि रात्र कमी राहते. ओके. आणि तसंच तुम्ही मूव्ह होत राहिलात तर तुम्हाला इथे दिसेल की इथे रात्र जास्त राहते आणि दिवस कमी राहतो. ठीक आहे. आणि हे जे चक्र आहेत ते बदलत राहतात. या इथे 12 तास रात्र आणि 12 तास दिवस. ओके. पण त्याच्यानंतर जर तुम्ही दुसऱ्या याच्याकडे गेलात तर वेगवेगळ्या गोष्टी होत राहतात. ठीक आहे. ओके.
हां, मला असं विचारायचं होतं की अवकाळी पावसाचे काय कारणं आहेत?
सॉरी, हां, इकडे. हां, अवकाळी पाऊस. हां, अवकाळी जो पावसाळा होतो तो सध्या क्लायमेट चेंजमुळे याचं प्रमाण जे आहे ते वाढलेलं आहे. कारण की आपण पृथ्वीच्या वातावरणामुळे बरंच कार्बन डायऑक्साईड आणि जे बाकीचे मिथेन वगैरे असे जे गॅसेस आहेत ते रिलीज होत आहेत आणि त्याच्यामुळे सूर्याचं जे प्रकाश किरणं असतात ती ट्रॅप होऊन जातात. ओके. आणि ती ट्रॅप होऊन त्याच्यामुळे पृथ्वीचं जे तापमान आहे ते वाढत चाललेलं आहे. ओके. आणि मग ते तापमान वाढत चालल्यामुळे जे काही पृथ्वीवरती ॲव्हरेज तापमान असणार होतं त्याच्यात चढ उतार जास्त होताना दिसतं. ठीक आहे. ओके. येस. आता अँटी क्लॉकवाईज आणि क्लॉकवाईज तुमच्या बघण्याच्या दृष्टिकोनावरती आहे. जर तुम्ही वरून बघितलं किंवा खालून, पण हे लक्षात ठेवायला पाहिजे की अवकाशामध्ये वर आणि खाली असं काहीच प्रकार नसतो. ओके. तर तुम्ही कुठल्या दिशेने बघताय त्या प्रकारे मला हे दॅट्स इट. हां, जर असं बघितलं तर अशा प्रकारे फिरते. बरोबर.
आता तुम्ही जसं सांगितलं की पृथ्वीची जेव्हा एक साईड सूर्याला फेस करते तेव्हा वेगळे वेगळे सीझन्स पडतात. तर एक सीझन 3 ते 4 महिन्याचाच का बरं असतो? का बरं 5 ते 6 किंवा 6 ते 7 महिन्यांचा उन्हाळा का बरं नसतो?
हां, तर ही जी पोझिशन आहे ती जर बघितली आपण, पृथ्वी जी आहे ती वर्तुळाकार ऑर्बिटमध्ये, वर्तुळाकार कक्षेमध्ये जाते आहे, बरं. तर त्याच्यामुळे हा जो पॉईंट आहे इथून इथपर्यंत जायला जवळजवळ 3 महिने लागतात. मग इथून इथपर्यंत जायला अजून 3 महिने, इथून इथपर्यंत 3 महिने आणि नंतर 3 महिने. त्याच्यावरूनच आपल्याला कळतं की हे जे ऋतू जे आहेत त्यांचं ड्युरेशन किती असायला पाहिजे. ठीक. म्हणजे खरं तर लंबवर्तुळाकार आहे कक्षा, पण तुम्ही बघितलं तर ती जे लंबवर्तुळाकार जी कक्षा आहे ती काही एवढी लंबवर्तुळाकार नाही आहे. एक मिनिट. हां, नेक्स्ट वन. या ही जी काही कक्षा आहे ती जर तुम्ही बघितली तर ती अगदी गोलच दिसते तुम्हाला. कारण की याच्यातला जो फरक आहे इथून इथलं अंतर आणि इथून इथलं अंतर ते फक्त 3% फरक आहे, त्याच्यामध्ये जास्त नाही. ओके. परत एकदा मग क्लायमेट आणि वेदर. ओके. सो क्लायमेट इज अ लॉंग टर्म फिनॉमिना. म्हणजे क्लायमेट म्हणजे जे जास्त वेळावरती तुम्ही जेव्हा ॲव्हरेज करता तेव्हा काय होतं त्याला क्लायमेट आपण म्हणतो. आणि वेदर म्हणजे डे टू डे काय बदल होत असतात ते. ठीक आहे. तर त्याच्यामुळे जेव्हा सूर्याची किरणं आपल्या पृथ्वीवरती पडतात आणि ती ट्रॅप होतात त्याच्यामुळे आपण आपली जी जीवसृष्टी आहे ती आज आपल्याला दिसते इथे पृथ्वीवरती. पण जेव्हा आपण थोडेसे बदल करतो वातावरणामध्ये किंवा वातावरणाच्या घटकांमध्ये तेव्हा जे काही सूर्यापासून किरणं येतात ते किती ट्रॅप होत आहेत त्यांचं प्रमाण जे आहे ते कमी जास्त होत राहतं. आणि ते कमी जास्त झाल्यामुळे क्लायमेटवरती बदल होत आहे. ओके. हवामान जे आहे ते लोकली आज काय चालू आहे, आज वारे कसे वाहत आहेत त्याच्यावरती अवलंबून असतं. पण क्लायमेट जे आहे ते हा जो बॅलन्स आहे की सूर्याकडनं किती प्रकाश येतो आहे, त्याच्यापैकी किती प्रकाश रिफ्लेक्ट होतो आहे, त्याच्यापैकी किती प्रकाश जो आहे तो स्टोअर होतो आहे ऊर्जा म्हणून वातावरणामध्ये, त्याच्यावरती क्लायमेट डिपेंड करतं. ठीक आहे.
सर, कधी पण अचानक वेगळे ऋतू कसं काय होतं? म्हणजे समरमध्ये कधी मध्ये पाऊस होतो, असं कसं काय मुळे होतं?
सो हे जे आहेत ते लोकल कारणं आहेत आणि हे जे ऋतूंचे जे कारणं आहेत ती ग्लोबल आहेत. की पृथ्वी जी आहे ती कललेली आहे, पृथ्वीचा अक्ष जो आहे तो तिच्या कक्षेने कललेला आहे, कक्षेपासून, ठीक आहे. आणि मग कधी कधी तो सूर्याकडे बघतो, कधी कधी सूर्याच्या दुसऱ्या दिशेला असतो आणि कधी कधी न्यूट्रल पोझिशनला असतो. त्याच्यामुळे ऋतू होतात. पण हवामान जे आहेत ते लोकल गोष्टींमुळे होतात, की हे जे बाष्प आहे आपल्या आजूबाजूला अरेबियन समुद्र आहे, बे ऑफ बेंगाल आहे, त्यांच्यामधलं जे पाणी आहे ते त्याचं बाष्प होतं आणि त्याच्यानंतर ते जे बाष्प आहे ते भारतीय उपखंडावरती आणलं जातं वाऱ्यांमुळे, बरोबर. आणि मग त्याच्यानंतर पाऊस पडायला लागतो. तर हे जे आहे ते लोकल कारण आहे, ते भारतामध्ये होतं आहे. दुसरी सगळीकडे हा जो मान्सून आहे तो होत असेल असं नाही, ठीक आहे. तो काही लोकल कारणं असतात आणि ऋतू जे आहेत त्यांच्यासाठी ग्लोबल कारण.
नॉर्वेसारख्या देशांमध्ये 3 महिन्यासाठी कधीच सनसेट होत नाही, ते का होतं?
त्याचं कारण हेच आहे एक्झॅक्टली. इथे एक मिनिट हां, एक मिनिट हां, मी ओके. सो आपण इथे जाऊया. नॉर्वे हा जो देश आहे तो उत्तर गोलार्धामध्ये आणि अगदी या ध्रुवाच्या जवळ आहे, ठीक आहे. आणि तो ध्रुवाच्या जवळ असल्यामुळे तुम्ही इथे बघू शकता की हे जे आहे, लाईक जर तुम्ही इथे असाल फॉर एक्झाम्पल, जर तुम्ही उत्तर ध्रुवावरती बरोबर असाल तर मग तर तुम्हाला पूर्ण अगदी 6 महिन्यांसाठी अंधारच दिसेल, ठीक आहे. पण जर तुम्ही या इथे असाल तर असं होईल की तुम्हाला 6 महिन्यांसाठी दिवस न दिसता थोड्या कमी काळासाठी दिवस आणि जास्त काळासाठी रात्र, असे हे जे बदल आहेत ते होत राहतील. ओके. सो हे जो फरक आहे तो एवढाच आहे की तुम्ही हे जे अक्ष आहे त्याच्यापासून किती लांब आहात. ओके. जर तुम्ही खूप जवळ असाल तर तुमच्याकडे खूप मोठी रात्र आणि खूप मोठा दिवस असं होईल बदल. आणि जर तुम्ही त्याच्यापासून दूर असाल म्हणजे विषुववृत्तावरती वगैरे जर असाल तर तुमच्यासाठी जवळजवळ समान प्रमाणाचा दिवस आणि समान प्रमाणाची रात्र अशी दिसते, ठीक आहे.
Good morning, sir. So, sir, as you said that about 3.8 billion years ago the solar system was formed. So, can we predict that how long would the sun would keep burning for next how many years?
येस. सूर्य मराठीत चालेल का बोललेलं? हां. सो त्यांनी मला प्रश्न विचारलेला आहे की सूर्य जो आहे त्याचं निर्मिती कधी झाली ते आम्ही तुम्हाला सांगितलं, पण सूर्य जो आहे तो मरून जाऊ शकतो का किंवा किती वर्षांनी त्याचं पुढे काय होईल. तर इंडीड हा जो प्रश्न आहे तो खूप महत्त्वाचा आहे की सूर्य जो आहे त्याचं जे लाईफ सायकल आहे, त्याचं जे जीवनचक्र आहे ते कसं असणार आहे. तर आत्ता आपण हे जे जीवनचक्र म्हणजे सूर्य किंवा तारे जे आहेत त्यांचे जे जीवनचक्र आहेत ते आपण म्हणजे आपल्या स्वतःच्या आयुष्यामध्ये बघू शकत नाही एका ताऱ्याचं. पण आपल्या पूर्ण विश्वामध्ये खूप सारे तारे आहेत आणि बरेचसे तारे हे सूर्यासारखे पण आहेत. तर त्यांच्याकडे बघून आपण सांगू शकतो की सूर्यासारख्या ताऱ्याचं काय होऊ शकते, ठीक आहे. तर सूर्यासारखा जो तारा आहे तो जवळजवळ त्याच्यामध्ये हायड्रोजन असते, बरोबर. आणि हायड्रोजन तो जाळून त्याचं हिलियम बनवतो आणि त्याच्यापासून तो आपल्याला ऊर्जा देत असतो. तर कुठलंही जेव्हा इंधन असते, फ्युएल असते, ते संपू शकते, बरोबर. आणि ते संपल्यानंतर काही बदल त्याच्यामध्ये होऊ शकतात त्या ताऱ्यामध्ये. तर सूर्य जो आहे त्याचं जे इंधन आहे ते जवळजवळ एक 8 ते 10 बिलियन इयर्स नंतर तर जो हायड्रोजन आहे तो जवळजवळ संपत येईल. ओके. तो जेव्हा संपत येईल तेव्हा त्याच्यामध्ये हिलियम तयार झालेलं असेल तर त्याच्यामध्ये ते जे काही बदल आहेत ते व्हायला लागतील. तर हे जे बदल आहेत ते जवळजवळ 10 बिलियन वर्षांनंतर होतील. आणि त्यावेळेला तुम्हाला दिसेल की सूर्य जो आहे त्याची जी त्याच्यापासून येणारी जी प्रखरता आहे ती कमी व्हायला लागेल. त्याच्यानंतर त्याचा आकारही वाढायला लागेल. तो एक रेड जायंट असा प्रकार असतो ताऱ्यांचा, तशा प्रकारचा एक तो तारा बनेल. इनफॅक्ट त्याची जी सरफेस जी आहे ती खूप जवळ येईल आपल्या पृथ्वीच्या कक्षेच्या. ओके. तर त्याच्यामुळे मर्क्युरी किंवा बुध किंवा शुक्र जे आहेत ते हे जे ग्रह आहेत ते जवळजवळ त्याच्या पृष्ठभागाच्या आतच येतील. ओके. तर अशा प्रकारे बरेचसे जे बदल आहेत ते सूर्यामध्ये होणार आहेत आणि ते या कालावधीत होणार आहेत. जवळजवळ 10 बिलियन वर्ष एवढ्या कालावधीनंतर हे जे प्रकारचे बदल आहेत ते आपल्याला दिसून येतील.
गुड मॉर्निंग सर.
आता शेवटचा प्रश्न घेऊया, कारण की त्याच्यानंतरचं पुढचं लेक्चर चालू होणार आहे.
सर, उत्तरायण आणि दक्षिणायन म्हणजे काय?
उत्तरायण आणि दक्षिणायन म्हणजे काय, हा खूपच छान प्रश्न आहे. आपण जेव्हा सूर्याला बघतो, ओके, आपण हे शोधू शकतो की सूर्य जो आहे तो कुठे मावळतो आणि कुठे उगवतो आहे, बरोबर. आपण कुठल्या दिशेला उगवती दिशा म्हणतो तुम्हाला माहिती आहे का? पूर्व, बरोबर. आणि मावळती कुठली म्हणतो? पश्चिम. ओके, तर तुम्ही आहे ना रोज बघू शकता की सूर्य जो आहे तो नक्की कुठे उगवतो आहे ते. ती जर दिशा तुम्ही मार्क करून ठेवा, की सपोज तुम्ही असं ठरवा की माझ्या घरातनं मी पूर्व दिशेकडे बघणार आहे आणि मी हे शोधणार आहे की सूर्य कुठे उगवतो एक्झॅक्टली. आणि रोज त्याच जागेवरती जाऊन हे निरीक्षण करत राहा. तुम्हाला असं दिसून येईल की सूर्य जो आहे त्याची उगवण्याची जी दिशा आहे ती प्रत्येक काही महिन्यांनंतर बदलताना दिसेल. ओके, सो इन जनरल ती पूर्वेलाच उगवताना दिसेल, पण कधीकधी थोडंसं उत्तरेच्या दिशेला आणि कधीकधी थोडं दक्षिणेच्या दिशेला असा सूर्य उगवताना दिसेल. ओके, तर हे जे उत्तरायण आणि दक्षिणायन आहे ते याचबद्दल आहे की सूर्य जो आहे तो बरोबर पूर्वेला उगवतो आहे की थोडासा उत्तरेला उगवतो आहे की थोडासा दक्षिणेला उगवतो. ठीक आहे, आणि तो थोडासा उत्तरेला किंवा थोडासा दक्षिणेला दिसण्याचं कारण हे आहे की सूर्याची जी पृथ्वीची जी अक्ष जो आहे तो कललेला आहे आणि तो अक्ष कललेला असल्यामुळे कधीकधी सूर्य जो आहे तो तुम्हाला दक्षिणेकडे असताना दिसेल. सो फॉर एक्झाम्पल या इथे जेव्हा उन्हाळा चालू आहे तेव्हा सूर्य जो आहे तो इकडनं येतो आहे, तो थोडासा दक्षिणेकडे असताना दिसेल. आणि जेव्हा, कारण की सूर्याचं उगवण्याची जी दिशा आहे ती तुम्हाला ही गोल पृथ्वी फिरते त्याच्यावरनं दिसते. ओके, सो सूर्य जो आहे तो थोडासा दक्षिणेकडे असलेला दिसेल आणि जेव्हा तुम्ही उन्हाळ्याकडे जाल त्यावेळेला तो तुम्हाला थोडासा नॉर्थ साईडला उगवताना दिसेल. ओके, सो हे जे आहे ते उत्तरायण आणि दक्षिणायनचं कारण. ओके, तर आपण या इथेच हे प्रश्न थांबवूया. तुम्हाला जर अजून काही प्रश्न असतील तर दुपारी 1:30 वाजता एक कार्यक्रम होणार आहे जेव्हा जयंत नारळीकर आणि त्यांच्याबरोबर अजून काही शास्त्रज्ञ आहेत, तर ते येऊन तुम्हाला इथे तुमच्या प्रश्नांची उत्तरं देऊ शकतील. तर हे जे प्रश्न आहेत ते तुम्ही लिहून ठेवा आणि लिहून एखादा बॉक्स तुम्हाला सापडेल आस्क अ सायंटिस्ट नावाचा, त्या बॉक्समध्ये ते डिपॉझिट करा. तुमच्यापैकी सगळ्यांचेच प्रश्न आपण घेऊ शकू असं नाही, पण काही जे निवडक प्रश्न आहेत ते आपण तिथे या शास्त्रज्ञांना विचारू शकतो. ठीक आहे
सर, एक लास्ट क्वेश्चन विचारू का?
या एक्झॅक्टली. सो थोडं 25 मिनटं लेट झाल्यामुळे आय थिंक वी नीड टू रॅप अप. ठीक आहे, तुझा जो प्रश्न आहे तो तू नंतर विचारू शकते. आस्क अ सायंटिस्ट कार्यक्रमाच्या ड्रॉपबॉक्समध्ये टाकू शकते. ओके, थँक्यू.
हॅलो नॅशनल सायन्स डे. हॅलो नॅशनल सायन्स डे. ठीक आहे, मला ठीक आहे. Okay. So, good afternoon. It's almost noon now. Welcome again to the next session at the IUCAA National Science Day celebrations. I am Samir Dhurde and here to share with you exciting journey which I have called the Cosmic Zoom. This is a journey of the things that are studied at IUCAA. So IUCAA is the Inter-University Center for Astronomy and Astrophysics, and in this place we have a lot of learned scientists who study the universe. Okay? And the universe of course includes us and the earth and things inside the earth, around the earth, but an astrophysicist, an astronomer, they study things which are above the earth's atmosphere, let's say. Okay, so the place we call space, right? And space is much bigger than whatever we have on earth. So just imagine the responsibility on astronomers and astrophysicists that they have to study all the other things other than the earth, which is a tiny speck of dust in this whole universe. But of course it has so many complexities, so all sciences are important, and that's why we are celebrating this National Science Day here. Okay, so what I am going to do is in the next 20 minutes or so, I'll take you through a journey across various distances in the universe. Okay, we have something which we are very familiar with, the distances or the distance scales, okay, that we can easily measure things with. What do I mean by that? Let me not get too scientific. Let me just explain what do I mean by scales in the universe. So I'm standing in front of you here. You can see that I have a certain height, and in the crowd there are many people of different heights, right? But when I have to talk about that height, or if I have to fill a form somewhere where I have to mention my height, what will I say there? Somebody will say I'm 5 feet something, or somebody will say I'm 1 meter something. Okay, so we use this, let's say, feet or meter, right? In case you are measuring some cloth, then we use more meter than feet, right? So these are the units that we use, which are very similar to our size, human size, right? And we have taken it according to our convenience, because if we say meter, that is about this much in size, right? Do you agree with that? Yeah. So this is close to our own size. Then what we do is we either multiply this if you want to measure or talk about bigger distances, or we divide this into smaller parts if you want to talk about smaller distances. Then if you just want to talk about the size of a, let's say, cake that you buy, then you say, okay, not feet but inches. Or you don't say, if you are using metric, then you don't say meter, but you say centimeters, right? And if you are going to talk about smaller things, like let's say the size of your hair, right? Then you go to further fractions of the meter. If you want to talk about the distance from here to your home, then you talk about thousands of meters, kilometers, right? So we are going to look at these scales, but in a special way. What we are going to do is, at every, we'll be taking several steps in this journey, and every steps, the distance will be multiplied by 10 or divided by 10. Okay, so first we'll go in multiplication. So if we start with some scale which is 1 meter, then we'll have the next scale as 10 meter and further. And we'll try to see which is the biggest scale which can fit the whole universe. Right? And then we'll go into a journey where we'll try to see which is the smallest scale which we know of in this universe. Right? And of course, further research is needed beyond these scales. And who will do this research? Some of the tiny ones here. Right? So that's going to be our cosmic zoom journey. So I'll start with a film. Okay, and this is going to be a film which I'm going to actually mute, because I'm going to give the commentary for this. All right. So, yeah, we'll slowly dim the lights on the screen, please. Further, thoda idhar ka? Haan. This can go off. Yeah, thank you. Okay, so we start with a video. Okay, so there are some kids playing here. You can see they're playing with hula hoops, and you will notice that the background is very, very beautiful. It's some, obviously some place in some Western country. I'll tell you, this is a very special place for astronomy, and it's in the city of Venice, in the country of Italy. Okay, and there's a very famous Italian astronomer who you may have heard of. Any guesses? Right, so that's the most famous Italian astronomer, and Galileo Galilei was the one who started astronomy with a telescope. He had access to a telescope. In fact, he made his own telescope, not the first one in the world, but he made one for himself and observed the universe for the first time as an astronomer. His was a very small telescope, and it could only show him a limited number of things. But just remember, he was the first one to use it. So all the things that he saw, he was the first one to see all these things, right? And he would not have done that if he was not brave and daring. Why I'm saying this is because at that time, if you went around in society and told somebody that, I'm going to look at these bright objects in the sky, which are called planets. Okay. These at that time were considered as gods. In many mythologies, many stories, they were the gods there. Right? And if you say, okay, I'm going to look at that god, what are they doing through a telescope? वो तो पाप होता था ना. So it would be sacrilege. So you could not do that. But he was convinced it is not some godly affair. It is just some things he was curious about, and he said, let me look at them with the telescope and see better. Yeah. So he used a telescope, and he found a lot of things which I'm not going to go into, but it's an exciting thing to be curious about. You should find out later. What he also did was that rather than just seeing it himself, he also took one of the telescopes and put it out at a public place. Just like what we are going to do tonight at IUCAA, and we do it regularly at IUCAA. IUCAA has special sky shows every Friday. You should find out more about it later. So this was kind of one of the first outreach events with a telescope, and that happened here. That is St. Mark's Square in Venice, okay? And that's why this is very, in general it is a famous landmark in Venice, but it's special for astronomers because this is the first place where generally people got to see things with a telescope. And we are beginning our journey with that place where these kids are playing with some hula hoops. Now you'll realize that if I pause it here, on the screen of course it looks very big, but in real life a hula hoop is about, what would be the diameter of a hula hoop? Just about 1 meter, okay? So it's strategically sized there. So these kids are having fun. Now we start with this circle as a reference, okay? A 1 meter circle, right? And as I said, we are going to increase distance scales by 10 times at every step, right? Of our zoom, cosmic zoom. We will use circles of increasing diameters. And every time you see a circle, it will be 10 times the previous circle's diameter, okay? And what I will ask you to do, rather than me just giving a lecture to you, you also participate. What we'll do is we'll count how many circles we go through. So then you'll keep a track of how many steps we have gone to the farthest reaches of the universe. So this is your first circle, that's right, yeah. So we start with that, and let's go ahead. So they're enjoying this game. They've been playing it for a while. They show us some acrobatics, and the game is getting finished. But by now you must be seeing another circle. Just keep a watch. Do you see another circle which is not drawn out for you because you're all smart people, you can see it. So it's the ring of people around the acrobats, right? And that diameter is about 10 meters, right? So that's your second circle. Okay, so we keep going ahead, and now you'll see lovely scenery of the St. Mark's Square. It's exactly where Galileo pointed his telescope towards this direction and showed the people. See, that's the beautiful city of Venice. This is your third circle, mind you, right? So what will be the diameter of this circle? 100 meters, okay. Now you'll see the number of zeros are increasing, right? So how many zeros did the first circle have after 1? The first circle was 1 meter. So was there any zero after that? No. Okay, so that had 0 zeros. The next one was 10 meters. 1 0. This is 2 zeros. Now just think, now I'll keep multiplying by 10 every time. What is happening? I'm adding a 0, right? Is this very convenient? Yeah, because otherwise I'll have to keep a track of various things. And this is called the decimal system, okay, where we use multiples of 10, right? And this is another great thing to know, that the decimal system was started to be used in mathematics from India. Okay. And when you go into the main campus, you'll see the statue of Aryabhat, who is credited to first time using the decimal system in his calculations, right? So that's something the world has been using for great length. So we are also using it in this video. So that's the circle with 2 zeros. Okay. Now scientists use this fact. So instead of saying 100, then 1000, then when I have to write a billion, then you'll have to scratch your head. How many zeros does a billion have, right? So instead of that, what scientists do is they write it as a power. Okay, so really tiny kids will understand it later in some class, but we can call it the power. So number of zeros is put as the power of 10. Okay, so 1 is actually the 0th power of 10. That's why when you write 1, there's 0 zeros. So you can call it 10 to the power 0. Yeah, that is 1. It's very strange, but that's a good way to remember it. Then 10 to the power 1 is, you have to have 1 0 after 1. So 10. 10 to the power 2 is what you're seeing here. This is a 100 meter circle. right? So you can choose to keep a track of the circle numbers or the power of 10 or anything else. But we'll see at the end, we'll match notes as to where we reach. Keep going. The third circle comes up. That's about a kilometer in diameter. That's about 1 kilometer, 1,000 meters. Now you see, we are not going to use 10,000 meters, 1 billion meters. We are starting to use kilometers because meter has become inconvenient. There's too many meters in that kilometer, right? So now we have started using bigger units like kilometers. So this is kilometer, and you can see the lovely city of Venice. We keep zooming out, and you can see that the city is actually inside the sea. It's connected by a bridge. I don't know how they thought of having a city there. It's all connected not by roads but canals inside, right? It's a lovely place, but now we are seeing it from a zoomed out position where we are seeing the fourth circle. After this, I'm going to have a question, and after this, I'm not going to count. You are going to count the circles, all right? Fine. So we keep going. We are now at a city level. The Pune city is about 20-25 kilometers across. Yeah, it's bigger than Venice. So we keep going beyond and zoom out, and you see the fifth circle, in which you are seeing a large chunk of the country of Italy. Okay, with Venice there, but there is also a big chunk there. There's a fifth circle. Okay. Sixth circle. Yeah. So that is the country of Italy. That's part of Asia, Europe on that side, England in the ocean there, right? So France and Spain, Portugal, all are on this side. So this is the fifth circle. Fifth, right? Now my question to you, we are going to zoom out, and slowly at some point of time we'll be able to see the whole earth, right? So now after this step, how many more steps do we have to take to see the earth? Can you guess? Someone saying 2, 20, 3. Okay. 1, 2, 3, 4. This is like the elections in India. So you don't know which party is winning. But there has in science, there is no democratic election or something. There is one right answer because that's supported by natural facts. So you would know the answer if you knew the diameter of the earth, right? Does anybody know the diameter of the earth? Our earth, the planet on which we live. Yeah, okay, I'll tell you. So, and you'll be surprised with the answer. There you go. Okay, only 6 steps later, we are already able to see the whole earth. Slightly smaller, the circle is slightly smaller than the earth. The earth's diameter is about 12,000 kilometers. 12 to 13,000 kilometers. It's a big number, so I'm making an approximation. Okay, so it's about 13,000 kilometers across, and the sixth circle can fit inside the earth, just fit inside the earth, right? So one step, whoever said one step, if you actually knew the answer, then you are correct. And if it was just guess, then it's a lucky guess. Not 4 steps. So whoever said 2, 3, 4 steps, now see what all can be there inside the second, third, and fourth step after the fifth circle, right? Let's keep going. Now we have reached space. That's the arena where astronomers play their games. They look around, they find out things in space, then try to know their details. 7th ring. And now you can see the earth is slowly becomes smaller, right? And why is it half? I'm not looking at the moon, right? I'm looking at the earth. Earth is round. Why do you see it half? Yes, sunlight. So the sun, therefore you can guess. See, you're like Sherlock Holmes now. You can't see something, but you're still saying, okay, I can see it. The sun is on that side. The light is falling only on this side of the earth. This side has night. Right? So that's the night side of the earth. It's the day side of the earth. Sun is in that direction. So you have already guessed it. We keep going. And we will come across the closest big astronomical body. And which is that? The moon, this is the moon, yeah? And you'll see that this is, which step will come next? 8th step. So anybody who said 3 steps, you'll already be at the moon if you take 3 steps after where you put your guess. Okay, so the moon is about 3 lakh kilometers away from the earth. 4 lakh kilometers, 3,80,000 kilometers approximately from the earth. So that is a distance, and the next step will be in fact quite farther off. That's actually correct. You noticed it right, because we are going away from it, right? And there's a face of the moon which is always towards the earth. There's a face of the moon which is always away from the earth. It's not called the dark side of the moon because it does get light. That's a wrong thing somewhere. But it is the far side of the moon, and that's what we saw just now. Let's continue. And now you come to the 3rd step after the 5th. So that's the... Now here I am going to stop counting. You are responsible for that. Okay, now where is the earth? Where is the moon? See, at this large distance scale of that many circles, it's basically every time, if you're saying, let's say 9 circles, it means 9 zeros after 1. That many meters, right? At that distance scale, the earth is almost a point. Tiny dot. The moon is also a dot, right? And the line that you started seeing here is the orbit of the earth around the sun. Okay, that also has a size, big size, and you are only seeing a part of it. As we keep going further and further, we start seeing these are imaginary lines showing the orbits of other planets. Okay, these are not there. If you go into space, there is no highway marked like that where the planets will have to go. But this is what we know of the planet, their orbits. We have put it in a cartoon there. So we have the Earth's orbit at the center, then this is orbit of Mars, this is the orbit of Venus, and you can see orbit of Mercury. Where would be the sun? Just after that. You should see it coming in now. Yes. The next circle will enclose the orbit of Jupiter and Saturn. Okay, hope you are keeping count. And the tilted orbit that you see is the orbit of Pluto, yeah, which is a dwarf planet, which was previously called the 9th planet, but it's a dwarf planet classified right now. And this whole circle, okay, which circle is this? 12, 13. Okay, keep a track. So this circle, the 13th circle, can actually enclose the whole solar system, right? And that's 1 followed by, you can figure it out amongst yourself, 12 or 13 zeros. How many zeros? Oh, too bad, you already lost count. So the 13th step is already taken us to the solar system scale. Okay, now we are going to take steps which are solar system sized. Okay, and at this distance scale, we are not using units of kilometers or of meters, kilometers, or even 1,000, 10,000 kilometers. We are using units of what we call, wait, don't go too fast. So, perfect. So we are using units which are called astronomical units. Now that is the distance between the average distance between the earth and the sun. Okay, so that is kind of okay to use within the distance scales of the solar system. Okay, but then beyond that we have to use other units, because even after that there is a lot of empty space until we get to the next star. So we keep going like this, and you see before we reach the next ring, the solar system has become a tiny part of it. Okay, and there's nothing else after that yet. And about this distance from the center where we started, at about this distance, we have reached a distance which, if you travel at the speed of light, okay, the speed of light is tremendous. It is about 3 lakh kilometers in 1 second. Mind-boggling. 3 lakh kilometers in 1 second is the time, is the distance, it's the speed of light. It is the distance that light travels in 1 second, 3 lakh kilometers. So if you were, trying to go to the moon, and if you were light, you could just go like that. 1.25 seconds, you are at the moon. But if you want to go to Mars at that speed, it'll take about 20 minutes. Depending on where it is, but approximately 20 minutes. If you want to go to Uranus, Neptune, you might take a few hours, even at the speed of light, right? And the distance that you have reached now, you will take about 1 year to reach there. Okay, even at that tremendous speed. So that distance is the next unit that we use, which is called the light years. Okay, so we are now going into light years. I'm just making you familiar with the units, but keep a track of the number of circles. We go further again. After that, there's still nothing. Okay, you're getting to see some kind of a cloudy patch at the back. You might be curious about it. Before I skip it, this cloudy patch are other stars. But they are not our nearby stars. They are far away stars, which we can see because their light is coming to us. And there are more stars in some patches where the cloud is more dense on this side and this side. And there are less on the perpendicular side, on this side and that side. Right? Just keep a note of that, and you'll come to know why that is so. Okay, so we keep going. So we have gone beyond a few light years now. And we are so far away that the sun itself is a point. And now you see just these two things went past us. These are our closest stars, nearest stars other than the sun. But these are the nearest stars to the sun. And this is the group called the Alpha Centauri. Okay, that is our nearest star, and this star is in the southern constellation called Centaurus, and that's why it's called Alpha Centauri. And this is that star system. This is about 5.5 light years away from us. So the light that we see coming from that star is about 5 years old if you see it now. And we are still talking about the closest stars. We keep going, and now you'll start seeing after if you make a sphere out of this circle, okay, in that volume there will be more and more stars coming in. So you see all these other stars. They seem to be moving fast. That's because we are moving very fast. We are zooming out very fast, and now you can see that the sun, just a speck of dust, this whole big cloud. Okay, and this cloud is, yes, perfect. You're seeing it coming in. So this, you see the beautiful clouds in your blue skies, right? White fluffy clouds. They are made out of tiny particles of water, okay, frozen water. Now, if you just consider each particle to be a star, then you are looking at a complete cloud made out of it, okay. And now what we are seeing here is that all these, wispy things that you see, they're all stars, but clumpings of stars. Okay, at some places there are less stars, there are more stars, but we are looking at it from a particular direction. And it becomes more and more clear when you go further out. So at the 20th step, we can see a part of what is called the Milky Way galaxy. Okay, and at the 21st step, we can see a representation of our own galaxy, okay, as it is. And this is a collection of more than 100 billion stars, okay, of which ours is one of them. And so at that level, just one star or two stars doesn't matter, it's because these are the clumps of stars. And now what we are seeing that it has a particular shape, okay, and that's why you were seeing the patch, cloudy patch in the sky previously, because it has a shape. It is very flat, okay. So when you look at it from the side, you can see a patch. On the upper side there are less stars, on the lower side there are less stars, okay. But if it was a sphere, it was spherical in shape, and we were inside it, we would see equal number of stars in all directions probably, right? And also note that we as the sun would be somewhere here in this corner. It's not at the center of the Milky Way, okay, which is actually good, because at the center there are many more stars densely packed together. That would be very bad for us. If you go out of this cold AC environment, you'll feel hot. Just imagine that's with one sun. Just imagine if there were two suns, or at the center of the Milky Way there could be maybe 1,000 suns in the sky, right? If at all a planet could form there. That would be ridiculous, and we would definitely not exist there. So we are in a safe patch in a corner of the Milky Way there, and at the 21st circle we are able to see the full Milky Way. Okay. Now what is beyond this? Then we start seeing other things, other big patches. Okay, these two patches at the bottom here and here, and also somewhere here we have various kinds of patches of things which look like the galaxy, our galaxy, but they're smaller. Okay, they're irregular shaped, right? So our galaxy has a shape called the spiral. Okay, a spiral is something which you might have seen in pictures of hurricanes and cyclones in weather forecasts, right? So our galaxy has a shape like that, which also can tell you which direction our galaxy is rotating. It has a rotation also, right? So there are many things, as I said, that if you become like a detective, which astronomers are, because they have to work with very less clues, but they have to find out so much more, right? They can see very little, but they find out so much from that very little information. So from this, after you finish looking at the beauty of the galaxy, you can probably also think of, yeah, it probably turns like this. That's why the shape is like that, right? So that's how science works. You first get some data, find some information from it, then go on and try to wring it more and bring out more information. So this is now going to the 22nd ring. We start seeing other galaxies. Okay, this is our galaxy going into the background, and then this bigger galaxy, see the size scales, the bigger galaxy comes into the picture. This is our closest galaxy called the Andromeda galaxy. Okay, the Andromeda, in India it is called Devayani. So this is our closest big galaxy, and it's actually bigger than us, right? It's somewhere in the northern direction of the sky. And these are, in fact, even over such large distances, which is actually about 2.2 million light years. See here, even light years are becoming difficult to handle, right? So at that kind of distance scales, there is one force which acts between objects, and that force is called gravitation. Okay? Although it's weak, it can still act over large distances, and it's an attractive force, so it keeps things attracted or in place, and sometimes it also makes them come closer. Okay, so you might have heard that somewhere that there is a galaxy going to collide with our galaxy. So this is that galaxy. Okay, but this is bigger, and it's quite far off. It's not going to happen any time during our lifetimes, or a few, maybe 100 generations after this even, right? So this is quite far off, but this is the closest galaxy. It is within the which ring? 23rd ring. And now you see there are other things have started moving. These tiny dots, they've started moving slowly, right? Now each of these dots is a galaxy now. Okay, we are at such a big scale that we cannot see the shapes of these galaxies, but there are these galaxies which seem to be moving. And do you notice that at that large distance scale, we have some clumping of galaxies. There are galaxies which try to clump together, and there are areas where there are less galaxies, just like this auditorium. There are some people here, then there's some gap, there's some people there, and there's gaps in between, right? So therefore, all these points that you see in this picture are not things which I have dreamt up or the cartoonist has dreamt up. Okay, these points have been put into the film based on observations by astronomers. Astronomers have pointed their telescopes in different directions in the sky. They have noted down which galaxy is in which direction. Like we have our own, it is called coordinate system. in which we know which direction has which galaxies, we have also been able to find out how far they are from us. Right? That's also important because I am showing you these galaxies at different distances from the center where we are. Right? And so this has also been taken, this data has also been taken, and that's how this film has been made. So what I'm showing you is not some fiction, but actually a clip based on real observations of real galaxies in various directions of the sky. And you can see that over very, very large scales, these galaxies clump together. These are called clusters of galaxies, right? And in fact, some places the clusters also cluster together, and then they are called the superclusters, right? So if you've ever wondered what is this supercluster stuff, this is it, because superclusters have been in the news. Right? There was, I think about a decade ago, there was a huge supercluster which was found, and then that was in the news for a while, and then we came to know that Indian astronomers have found a much bigger supercluster, and that is called the Saraswati supercluster. Right? It needed some different types of observation, not just observations with the light that we see. If you want to understand what I'm just saying, what do you mean not with the light that I see? Then for that you have to go into the main campus, and there are other posters explaining, and ask those people what did he mean when he said that there are other lights that we cannot see. But I'm not going into that. But with all these observations, we've been able to find these huge superclusters in the sky. And over time, when we collect all this information together, this is somewhat a picture of the universe that we come across. Okay, this is how the universe would look like at the last circle. Okay, if you were to look at it now, if you had some way to see it all together, right, it would be this mind-bogglingly random. Okay, it's not what scientists would call homogeneous. It's got no specific structure, but there is something. It's like a cobweb, but there are clusterings, there are gaps, all pervading gravitation is there, which is putting all these things in place. Okay, so now I will stop at this step and ask you now, because you are going to count for me how many steps we went. Okay, good. So now there's a common ground. Yes, so 26 steps away from the Earth. We started at 1 meter, and now we are at 1, and 26 zeros followed by that meters distance scale, right? And at this kind of zoom, we kind of get to see the picture of the universe as seen by astronomers now with the facilities they have at their hand, right? So I'm very happy that I could share this cosmic zoom with you from the perspective of an astronomer. There are exhibits in the main campus which will explain more about each of the steps. And astronomers don't just study the whole universe. There are some who are called cosmologists who study that part, the universe as a whole and its evolution over a long time scale. But then there are many astronomers who study chunks of it and add their knowledge together to give us a whole understanding of the whole universe. All right. So this has been Cosmic Zoom with all of you. I can take some. I'll finish here. Thank you for participating with me and keeping track. Great. Thank you also for being here and supporting us. There are many beautiful exhibits across the campus. Please go there, enjoy. We are open for a few more hours, so make the best of the day. Thank you so much.
She wanted to talk to you. Turn off the mic.
Yeah. So we will, I hope you enjoyed the Cosmic Zoom. Since we were running slightly late, we'll be going to the next event, which is our astronomers here, researchers here, talking to you about their life in science, in astronomy, right? And we have those astronomers here already. So we'll not be doing the Cosmic Zoom in Hindi right now, but of course I see that all of you were there for the previous one. We'll try to have a run later, and you can come back for that. But let's go on to the next session. You want to put in he has a call in.
I need to log into my email. That's fine, no? For the slides.
Sure. Just a minute. I'm logged into put this off first. Getting a laptop. I said you first, until then you can give this here.
Hello. लॉगिन कर I don't know why it's coming in.
Good afternoon, everyone.
Yeah. I'm not audible yet. Yeah. So you all have gathered here very curious to know how in general PhDs and postdocs are at IUCAA. But I did not have an exciting journey like many of you are witnessing here today. I didn't attend any National Science Day in my childhood. I did not know what are the things which are going on around the world. I was in my own world. So in case any of you are like me here, I thought, okay, if it is even one, I know that most of you know a lot of stuffs which I didn't know then. So I thought in case if there are one or two who are like me, then they can relate to me and they can still have some hope that they can sometime become like me and enter maybe IUCAA or some other institutes and do research. So that's why I changed the title. I made it as an accidental astronomer, right? So my childhood was very normal. I was very shy person. Whenever someone asks to take a photograph, I would just close my eyes. Very shy. So I was a regular school-going girl, but a very punctual one. This is me. These are my cousins. They would try to bunk the classes whenever I go to their home, but I would get ready early in the morning, pester my parents to get back to me to the school. Not because of listening to the classes or something. At the end of the year, they would give best punctual student award for attending all the classes. So I just wanted to take that. So I would always attend the class without, like, if it is a 100-day class, I would have 100 days of attendance. So since I was shy, my mother thought she should work on me and make me a little bit of talkative and I should interact with people better. So for that, she made me do all these things. This is me as Radha, Krishna, Indira Gandhi. Even now people call me Indira Gandhi if I remove my hairs. This is Shiva and this is Snake Goddess. For a very long time I had been called Snake Goddess in my school. So this was how, like, slowly I started coming out of my shell. So, and then there were three major things occupied my childhood, at least till 10th standard. Those were drawing or painting as a first part. I didn't take any formal training, but I used to love painting or drawing. So some are here, sketches, water painting, oil painting, everything is here. So I would imagine myself like I'll be a great painting teacher or an artist when I grow old. This was around 4th or 5th standard. So then my mother pushed me to music. When she pushed me and I started attending the classes, I used to not enjoy it much. So I would say my mother that I'm going to attend the classes, but I would go and play with my friends. I would not attend. So my teacher here, she realized that something is happening and she informed my mother that your kid is not coming. So to solve this problem, my mother joined along with me. So she was attending the classes along with me and she was studying and asking questions more than me, and I was very intimidated by my mother. So I thought, okay, let me also compete with her. So in the name of competition, I started forcibly practicing music, but in time, I fell in love with that too. So I practiced so much that there are Karnataka, I am from Karnataka, so Karnataka like state board examination which conducts 10th exam, the same board conducts music, dance and all other art forms also. So I thought, okay, let me take those exams and make my mother and also this music teacher proud. So somehow I won, and this is a small article written. So once this level of exposure given, I thought, okay, now I'll be a music teacher or a musician. So this was around 6th or 7th standard. So I'm just trying to tell that how a star takes a birth, comes to the main sequence, lights and harbors life, and then I don't know what phase it goes, either red giant or white dwarf or black hole. It depends on how much mass it gathers throughout its lifetime. So in a way, how I used to interact or how my circumstances or surroundings were there, I was also evolving. So and then came side by side dance. So I was practicing Bharatanatyam, and it was much more glamorous than music because I got to wear costumes, I got to wear ornaments and makeup, and also going on stage. It used to, like my friends used to treat me like a little hero, so I used to feel proud. So I thought, okay, I'm a good dancer or something maybe. And somehow I was selected into this group of 6, and we got a chance to dance in front of Shri Atal Bihari Vajpayee when he was Prime Minister then. So then I thought, okay, then this is it. I'm going to be a dancer. So I got some scholarships for studying dance. So I thought, okay, this is going well. It should be it. So meantime, in academics, I wanted to study maths, but somehow maybe I did not have good teachers, or at my home I did not get someone sit behind me all the time and pester me to do things. I used to fear for maths. And whenever I solve few problems, I used to feel very proud. Maybe there is some career path here too. But at the same time, I used to love physics. But for loving physics, you have to learn mathematics. So this was like a unsolvable problem then. So my father thought I'm doing so many of these things and not studying well or concentrating much on my education. So he said, okay, do all these things I'm not telling you not to do, but concentrate on your studies too and keep all these things as hobby. So he thought if I am staying in the same village where I was staying, it was Sagar, Shivamogga district. It's a small village in Karnataka, middle part. If you have heard Jog Falls, I am from there. So he thought if I am in that background, I would just go around and do all this stuff. So he thought he will put me in some little higher district where a lot of college and environment is there. So far you can imagine that till 10th standard, I was not exposed very well to science. So he sent me to a college First time, I was just 16-year-old, far from home and parents, and you can know the difference between 11th to 10th standard book size. So I couldn't cope up with that. I suddenly lost all confidence in me, thought maybe I'll not be able to do anything at all. I kind of, in internals, got very low marks and even failed in few subjects. So I thought maybe this is the end of it. I may have to maybe quit science. I might not be able to do it. So I bore it, I was keeping that inside for 3 months, attending classes, and finally I was having a little explosion, and I told my father, I'm going to come back home. I don't want to do this. So that's when he told, okay, stay for today. Tomorrow let's see. You might feel better. Just for me, tomorrow you stay. So that was maybe the turning point. So I got to hear a series of lectures from Ramakrishna Mission then. A lot of talks were organized for youth especially. And I attended maybe for 3 days continuously all the talks, and I tried to interact with all the Swamijis who gave talks there. So everyone would repeatedly tell me that, yeah, my question was, I want to do something to my country, but I don't know how to do, and I'm failing to do in everything. I left all the extracurricular, and I wanted to do science, and somehow I don't have ideas how to do that. He just said that, okay, you want to contribute and do well in your for your country, then whatever you have in your hand, give 100%. Just, you have come to do science, then okay, give your 100% and study. Okay, then I called back my father and said that, okay, it is fine, I think I'll try to take it for some more time. If not, then please take me back. So that was a kind of turning point. But still not right guidance to do science. So I used to spend a lot of time studying, seeing many books from library, but I didn't know that for becoming a researcher, you have to do projects, visit different institutes, and do a lot of things for that. So I just lock myself up and study and study and study. So I did my BSc in Kuempu and MSc from University of Mysore. So studying for 5 years fetched me a lot of things, but still no research experience. So even now if I'm standing here, it was I don't know how it happened and turned out. Yeah. So I had cleared some of the national level examinations, and I thought, okay, now I should, the regular procedure was to apply to different research institutes, send your applications. I thought, okay, I'll send. But meantime, I was thinking that in every interview they'll ask, which is your favorite subject? What do you want to do? What do you see yourself in upcoming years, etc. I had no proper answer, but I knew that I loved atomic physics. I wanted to do something in atomic physics. I would love spectra and all. You might be listening to a lot of talks today on how Aditya is going to take different spectra or images in different wavelengths, etc. So you can go back and check there. So I thought something related to atomic physics I'll do. Still no direction to astrophysics then. So then while attending interviews at different places and meeting different kids, I came to know that astrophysics is the natural laboratory for studying many atomic physics phenomena. Many atomic phenomena which cannot happen in the labs of Earth can happen in space. Many elements were discovered this way, and many atomic physics, quantum physics phenomena were discovered this way. So I thought, okay, this is a great chance. I also had applied to IAA then, just last minute before the application deadline ended, someone told IAA has an opening, so I applied. So somehow I cleared the interview and I got into PhD. So while attending the coursework in PhD, so PhD has a structure. First year full you have to attend different classes, which will be little advanced than MSc. So we were fortunate enough to be combined with JAP, which is Joint Astronomy Program, which is held by IISc or Tata Institute in Bangalore. So they select different students in their own institute, but also we students of IIA and Raman Research Institute, RRI, ISRO, these students combined, we can attend classes. So I got to visit a lot of observatories and institutes for these reasons, and I got to interact with a lot of students, and I had this biggest insecurity then. In my batch, I was the only university-based student. All my batchmates were from IITs. So initial 2-3 months, it was very hard for me to accept that. And also at the same time, we were 7 of us in our batch, and only I was from South India, and all others were from West Bengal. So most of the times I got to hear even science discussion in Bengali. So it was, again I called my father, and should I think to drop it because I'm finding it hard to continue. So he's like, again, the same funda, stay for today, maybe you'll feel better tomorrow. So I stayed and I made good friends. I learned Bengali, so I could interact with them better, and they were also very sweet. And that's how the journey continued. And meanwhile, we had solar physics course in our curriculum. So while attending that, I got to know that sun is, I mean, we can get highly resolved images of sun, because sun is our nearest star and our star. So we will be getting to know a lot of atomic physics phenomena by observing events occurring on the sun. Here are sunspots, coronal loops, flares, etc. So I joined a group who work on theory of radiative transfer. This is a theory which can tell what happens to a photon when it travels through a medium in presence of absorption, emission, and scattering in that medium. So when a photon passes through this type of environment, for example, when it comes out, it gives a spectral line, and when it comes out, it takes all the information of this region, for example. So you can get temperature, density, magnetic fields informations from by studying the spectral lines which are formed in this type of environment. So I worked on some numerical models. I still did not use observational data then. Okay, so since I did not get to use real data, I thought my next step should be of knowing how to use this data for understanding whatever I have studied. So here I am at IUCAA for doing that right now. So meanwhile, where exactly I developed true love for astrophysics I wanted to show. I attended a lot of outreach programs. So like the event today, which is happening at IUCAA, IIA also had a lot of outreach programs. I was part of many of those teams, and I tried to explain these are teacher training programs. So we tried to train teachers so that they can go back and train their 50, 100 or how many students as possible. So while explaining so many phenomena and by listening the questions and seeing the enthusiasm in the students' mind, I was gaining a lot of energy. Like I thought, okay, so many kids are showing a lot of interest, then I should be really feeling proud that I'm doing this. So it was very late that I got this type of inspiration, but I'm really glad that I got at least in my lifetime. So as a part of PhD curriculum, I also got to visit a lot of observatories. This is Kodaikanal Observatory. Here it is called Tunnel Telescope, which observes the sun and solar activities. and this was at Irsol, Switzerland, which records the polarization of the sun, etc. So gradually I felt that I am at a right place. I dreamt to be a teacher in art form as a kid, but as I grew, I got into science accidentally, but I'm happy that I did so. So currently at IUCAA, this is IUCAA Sun family, Durgesh Tripathi here. We are all working on Aditya satellite here. You can go back and see the models done by Ferguson College students. So this again, SOOT, which is Solar Ultraviolet Telescope, is going to observe sun in the ultraviolet wavelength range. So it is going to observe again a spectral line called magnesium H and K in the following wavelength range. So yeah, I dreamt to study atomic physics in my MSc, but I'm happy that I'm continuing to do so. These are again science related to atomic physics. So to summarize, my life had a lot of twists and turns. I had both laughter and tears, but I'm very, very happy that I'm here. And I'm kind of little jealous that many of you very young kids are getting to see all these things at a very young age. Wish I were also among you in my childhood. But if someone like you, someone like me is there here, in case, maybe one or two, so you don't have to lose hope. There is still better future. You can modify and respond to all the opportunities that get in your path. You don't know when things will change. Maybe today only some of you will be determined to do science, or maybe not to do science. Maybe you'll get to know, no, this is not what I'm going to do. I'm going to do something else. So this is also a process called elimination. So you will tick mark no for many things and then tick yes for something. So you have got a great opportunity to be at IUCAA today, attend many more talks like this or events like this, ask questions, be open, don't fear. So life will take you somewhere, I don't know when. Thank you, that's all for.
Yeah, you have yours ready, you can go with it.
Wow. Let me see if I can do even half of the...
Those you have to put in the box outside at the reception.
So,
I'll just announce you, nothing else. You take your time.
ये हटाना पड़ेगा.
इसको बोलो, हटा दो.
नीचे बंद कर दो.
So we had an excellent recounting of the lovely story of Megha Anand, a researcher at IUCAA who's come through a long journey of evolution in science. So I hope it was inspiring. I seriously found it really engrossing and interesting to see all the steps. And also, it's so revealing that, you know, we always look at scientists in movies and they're like these particular stereotype people, but they're just us. Only that they don't go to work in the office that we go to work. They go to work at some other place. They do some observations. They live a normal life just like us. So we also have another researcher at IUCAA who's again going to put out his lovely story as in the My Life as an Astronomer section. So let's please welcome Divya.
Hey. Right, so नहीं ठीक है मैं इसी से कर लूँगा चलेगा ठीक है मैं देखता हूँ अभी तो शायद ज़रूरत नहीं पड़ेगी.
So unfortunately, we are not taking question answers in this session because we have some things to line up, some things lined up. But these researchers and many others are there in the IUCAA campus. You can talk to them all the time till 5:30. They are around, including both of them. So please find them if you want to have a separate chat about their work, etc.
Yeah. So yeah. I think I should be audible. Yeah. So I'm not really still not a researcher yet. So I'm actually a PhD student at IUCAA. I'm like in my 5th year. So it's like Megha gave a very good talk. So I will just try to tell my story as an astronomer. So right. So I went to this school. So I'm from UP actually. So in my school, you know, it's very standard. You study a lot of subjects. You know, you play with your friends. I never really had any science day actually. You know, you guys have such a good opportunity, you know. And like I studied there for 12 years I guess, and no science day, no clue about what is a researcher, okay. And so my school was inside a Air Force station. So basically in the daytime if you look up you see jets flying, right? So you will think it's better to fly jets instead of, you know, sitting down and do things in the class, right? So but there's something interesting. So my teachers and also my family, I have to say, they encouraged me to learn a bit about astronomy. So in a sense that in schools, in books, you learn a little bit what you see, right? I mean, in this NCERT, CBSE books. So my brother, I have an elder brother, okay, and so he used to come back from college, and so in his college they have an astro club. Now the thing is, he'll come back and he'll tell me about various different terms. He'll say there's some Big Bang and there are stars and they have this telescopes. They look at many different things, right? And I was really clueless. What is he talking about? So, but I used to ask questions, right? So then after a certain point, he said, look, I mean, it's better to learn a bit more of physics than really to answer such questions, right? So what was the right next step, right? So I said, okay, I'll go to this is my institute. This is National Institute for Science Education and Research. It's in Bhubaneswar, Odisha. So they give you 5 years of program to learn a bit about science and generally in physics, right? And it's like both masters and bachelors together. Now, you see, so the good thing about this institute was like they have a lot of courses in physics in a very broad area. So you can touch up on different topics in physics. So, and you know, they also have a very good astro club. I've never even seen through a telescope. So this is the first time I saw through a telescope there. And we saw Saturn and the rings around it. So that was cool. Now, and also given that they have so many courses, you can always study the astronomy in details, right? So I went through the coursework. Sometimes it was easy, sometimes it was not easy because you have to go through all the assignments and whatnot. But the point is, at the end of the day, you interact with the people, right? Researchers who works in the field. So in my time, there was one of the professors who is an associate at IUCAA actually. So at the end of my 5 years of program, I was interacted with him related to my course actually. So he said, look, I mean, there is some problem that I'm planning to try out. So why don't you give it a shot? So I said, okay. I mean, anyways, I had nothing to do. It was 5th year, so you have to do some kind of 1 year of a master's thesis, right? So, and he also didn't know whether you can solve anything in it, okay. So he said, okay, you try, and in the process, you will learn how to figure out things, right? So by the end of 1 year, I gave some partial answer. I don't know whether he was happy with it or not, but he said, look, I mean, after a year or so, now you have an idea how to figure out things, how to look for the right resources and use them in properly, right? So he said the whole point for this whole project was just to teach you this part, right? So that if tomorrow you want to explore more, these things are more useful, and that's what you should do. So I said, okay, cool. So now what should I do now? You know, ho gaya masters, so ab kya karna? So he said, look, if you want to explore more, there's an institute, there's IUCAA, okay. And at that time there was a conference between IUCAA and and NISER actually. This was a school on galaxy formation. So all the faculties of IUCAA was there at that time. And I had brief chat with them. I mean, like Kandu was there, Anand was there, Asim was there actually. And so then he said, look, I mean, this seems to be a good fit for you. And so he said, why don't you try and give some exams and give interviews and we will see. And because you don't know what happens, right? So here I am, okay. So I cleared the entrance exams which were required for this. Also interviewed. Fortunately, I got an offer from IUCAA. And so now it's like, okay, I came to IUCAA with no clue what is a PhD, okay. And so then after 1 year was okay, because you have all the classes, you attend the classes, you give the exams, and it's all okay. So 1 year of the IUCAA thing is a graduate school coursework. So everything is, it's okay. But then comes the PhD part, right? Here, I had no clue, right? So now you have to pick up an advisor to work with, right? I knew I am interested, but I mean, I still have to pick up someone to work with. So I said, okay, how about I pick up a person with whom I can interact very easily, because that's what helped me in masters too, and most of the things I learned was through discussions. So it's better to have a person who I can discuss most. So I picked up my my current supervisor. He's not here, okay. So right. So then he also told me the same thing. Look, Divya, nothing's gonna work for the first time. This is like initial years of PhD. You joined a supervisor, and he says, look, Divya, nothing is gonna work for the first time. So let's see. You in the process, you figure out things, and we'll see how it goes. So it's been like 4 years working with him now. Things are all going fine. We wrote few papers, and it was all okay, right? But the question is, everyone has a similar kind of story, right? The question is, I also wanted, what do I actually do? I mean, so I usually do very simple things, right? If you are working in a certain research field, right? What you do, you look for what are the new research works in that field, right? And you see what you find interesting in it, right? And IUCAA has a beautiful program of having a lot of seminars. I mean, in each week you will have at least 3 to 4 actually. There are group seminars, there are colloquiums and whatnot. So it's given by the experts in the field, and now you can go and discuss new ideas. From my earlier experience, I always thought discussion is much better than sitting in a room and reading by myself. And then I will not tell you what I work on, but I'll just tell you broadly what I do. So in the cartoon here, so let me navigate through this. Okay. So in a cartoon here, you see there's a telescope here. So there are these stars, the galaxies which are shooting rays inside it, right? So what I do is I use the data which is collected by a telescope. It went through so many machinery, right? Each machinery is important. So, and at the end of the day, what I have is a measurements, right? Something like this scatter plot that you see here, like in X, right? Now with the measurements, you also say, okay, we also wanted to infer from the measurements. So you do a mathematical modeling of it. So in this case, there is like a straight line here. So I also do the same thing, but maybe one model is not enough. So like in this picture, you can see there is a huge number of models here, right? Each ball is like one model is sort of trying to understand the measurements. And this will later give you some parameters of interest, right? So I will not tell about my research, as I said, but broadly that's what I do as a PhD student in last 4 years, right? And if you want to know more, please go to the posters. We have beautiful posters made by our friends here. And you should go to cosmology, that's my field of research. But I just wanted to add this part. See, everybody's story when they come as an astronomer is very different, right? Some people, as Megha gave her story, I gave mine. So, but there's one thing is common in everyone's, right? Which is as very beautifully said by Einstein itself, right? So it's important thing is not to stop questioning, right? And curiosity has its own reason for existing. So I mean, this sort of thing worked for me, and I hope it worked for you too. So maybe I can end here. Yeah, sure. Should I remove it or? Okay, sure. हो गया ये
Hello. We will now directly have Ask the Scientist at 2 o'clock. So I request everyone to vacate the auditorium because there will be passes for this event for Ask the Scientist. So if you have not collected passes, you can collect it from the registration desk at the main gate. Your ID is with me. Excuse me, your ID is with me. Yeah. So I ask all of the people who are here to please vacate the auditorium. Ask the Scientist 2 वाजता सुरू होईल. सो त्या कार्यक्रमासाठी पासेस लागतात. सो त्याच्यामुळे आय रिक्वेस्ट की सगळ्यांनी आपण आता ऑडिटोरियमच्या बाहेर पडूया.
हॅलो.
हॅलो 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 ते ना
हां हॅलो 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 हां हॅलो आता ऑन नाही चालू राहू दे ना म्हणजे नंतर बंद करते. आता बंद केला.
hello, 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 hello. Hello, hello.
Hello, hello. Hello, hello. Hello. Hello, 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 hello. इतना कळत नाही. हाँ, hello. Hello.
Microphone check. Hello.
No, I will just hello. Keep it in my pocket.
Yes.
I think once you open it will be open. Hey, isn't it amazing? You said it cannot be done. Hey? They said AC cannot be referred.
हॅलो हॅलो
No, just clean.
ऐकू येतं बाहेर
Huge amount
हॅलो
of money. They said 30-40
हॅलो हॅलो
to change everything. Yes. We just asked them to clean. You see? And it started working. Switched off, right? No, that. No. Can you check? We don't want to switch on and discuss it. So I actually gave a link in this corner, in case something, some Earth's magnetism or something that I can just come back.
We have the winners for the model making competition just today. So after this, we stay back and I will announce the winners and then come and you can also say something encouraging words. Check it out.
Hello. Hello, hello, hello.
Okay.
Okay, welcome to IUCAA's National Science Day celebrations here on the 26th of February. The Science Day is usually on 28th, but we are celebrating it 2 days before because it's a weekend. And we have here a distinguished panel of scientists who are ready to answer some of the questions that you had given. We will have some of the questions answered in Marathi as well as English. So hold tight. Let's start with introductions first. The person who needs no introduction is, of course, Jayant Narekar. He is our founder, director, and he has been doing this Ask a Scientist session for such a long time, and I know that most of you are here to hear from him. In addition, we also have Ajit Kimbhavi, who was also the director of IUCAA formerly, and then we also have Shri Anand, who is also acting as the director of IUCAA. So we have three illustrious scientists here today to answer these questions. So thus far, I wanted to ask you, are you enjoying the National Science Day? Yes? We have missed you so much. You know, the last 3 years, we could not hold this event and ask all of you guys to come over here, and it has been painful. But now it's such a pleasure to see all of you in person here, and especially to see all of you in this auditorium. Okay? So thanks a lot for sending all these questions. We received many different questions on different topics, and we would like to get answers to them. So let's begin. या सो आपण या सगळ्या प्रश्नांची आता सुरुवात करूया. आणि सगळ्यात पहिला जो प्रश्न आहे तो आपण
येस इट्स ओके आय कॅन गिव्ह दिस आन्सर.
हां चालेल चालेल. सो देन let's start the first question. And this is for, okay, so this is from Thorat Sairaj Rajendra. So his question is about the full moon day and the new moon day, and why eclipses happen on these days. And not every full moon day or new moon day has an eclipse, and why is that? So Ajit, do you want to take that? Okay. Mike? In English? Yeah, in English is fine.
So, you know that during lunar eclipse,
सरांची काठी आणतोय थोडं तू मागे.
Mike?
Can you hear?
Yeah. It's on. Yeah.
can you hear me please?
ऐकू येत का सगळ्यांना? हॅलो. So let's first consider lunar eclipse. So what happens then? The light of the sun is falling on the moon generally, and we see the face of the moon, but then the earth comes between the sun and the moon, and the shadow of the earth completely covers the moon, right? And therefore you expect them to be in a straight line. So not every eclipse is a full eclipse. There are partial eclipses, but they are not exactly in the same line. So now why don't we see this all the time, meaning every time you should see it periodically quite often, you don't see that. That is because the orbits of these three objects are not, if you look at the orbit of the earth around the sun and the orbit of the moon around the earth, they are not coplanar, meaning that they are not in one plane. If they were in a plane, then they would always intersect when they are in a straight line. And therefore you don't see them often. So it's the same for the eclipse of a solar eclipse, because then the moon is passing across the face of the sun, and then when they are exactly in a line, you see a full eclipse, which is called a total solar eclipse, which is a very great thing to see, but quite rare. On other occasions, you see the annular eclipse, which you can actually see a ring around the moon, and that is because the moon is just slightly closer to you, as a result of which it does not cover the whole sun. Right?
सो थँक्यू फॉर दॅट आन्सर. मला एक प्रश्न विचारायचा होता, तुम्ही सूर्यग्रहण पूर्ण झालेलं कधी बघितलेलं आहे का, आणि तुमचा जो अनुभव होता त्यावेळेचा तो तुम्ही सांगू शकता का?
आता आम्ही सूर्यग्रहण बघितलं मी फक्त एकदा, कारण माझं गाव म्हणजे हुबळी, त्या गावातच ग्रहण झालं होतं, पण तेव्हा मी इंग्लंडमध्ये होतो, त्याच्यामुळे ते मला दिसू शकलं नाही. पण मग एकदा आम्ही राजस्थानात गेलो होतो, की मला वाटतं की 1995 साली, आणि तुम्हाला सांगतो ते कधी होतं मला नक्की आठवतं. तुम्हाला माहिती असेल की एक DDLJ म्हणून एक सिनेमा आहे, तो त्या वर्षी तिथं, कारण आम्ही तिथं सूर्यग्रहण पाहिल्यानंतर रात्री जाऊन तो सिनेमा बघितला होता राजस्थानमध्ये. तर तिथं आम्ही गेलो होतो आणि अतिशय सुंदरपणे दिसलं, आणि तो बराचसा लांब प्रकार होता, म्हणजे मला वाटतं 5 मिनिटाचा होता तो, आणि त्याच्यामुळे सगळ्या गोष्टी चांगलं अवलोकन करता आलं. मी अजून एक अतिशय सुंदर ग्रहण बघितलं आहे की आपण ॲन्युलर एक्लिप्स सोलार एक्लिप्स म्हणतो. म्हणजे पूर्ण चंद्र तिथं असतो पण त्याच्याभोवती एक अशी रिंग असते, राईट, कारण द मून इज नॉट कम्प्लिटली कवरिंग द फेस ऑफ द सन. तर मी तेव्हा सिंगापूरमध्ये होतो आणि तिथं सिंगापूरमध्ये ते समुद्रावरती गाव आहे आणि ते सगळं एक अशी जेटी होती आणि मी तिथं जेटीवरती गेलो होतो आणि मी आणि आशा आणि फक्त आम्ही 3-4 लोक होतो, दुसरं कोणीच नव्हतं तिथं. म्हणजे आम्हाला फार सुंदरपणे ते बघता आलं.
सो हे अनुभव जे असतात ग्रहण बघण्याचे ते फारच सुंदर असतात. जेव्हा कधी तुम्हाला वेळ मिळेल किंवा तुमच्या जवळ जर कुठे सूर्यग्रहण होत असेल तर तेवढा थोडासा जो प्रवास आहे तो करायचा प्रयत्न करा आणि बघा. कित्येक बदल होतात वातावरणामध्ये आणि काही काही म्हणजे पक्षी फॉर एक्झाम्पल जे असतात ते त्यांना कळत नाही की काय होतं आहे. अचानक अंधार झाल्यामुळे मग ते घरट्याकडे त्यांच्या जायला लागतात वगैरे वगैरे. तर अशा प्रकारच्या आणि तारे पण दिसायला लागतात तुम्हाला अगदी दिवसा. सो हे जे अनुभव आहेत ते फार विस्मयकारक असे असतात. तर ते तुम्ही बघण्याचा प्रयत्न करा जेव्हा शक्य असेल तेव्हा. तर आपण पुढच्या प्रश्नाकडे वळूया. सो दिस वन इज इन इंग्लिश बाय रिजुल कमलेश खांडेकर. Anand, if you want to handle this. So what are rogue planets? So these planets that may be wandering around, why are there rogue planets and why this could happen? Is there any significance to it? Maybe you need to give the mic. Okay, can we test this mic? Yeah. Maybe.
Can you hear me?
Yeah.
So you know that planets are solid objects or some objects of some shape which you can see them big enough. They usually go around stars like our sun in our case. And it is also believed that if you want to form these objects which has some sort of orbits going around the star itself, you should have formed them together. In the sense that whatever process which forms star will end up forming these planets with them. So ideally, if you follow this theoretical idea, you would expect all the planets which are round and look like a star kind of thing in reflected light, it will be always around stars, right? So what happened is that they go around something. Imagine that for some reason they get kicked out of they get additional force from something else, some object passing by or some interactions. Then what happens is that it will lose the control over, it will be no more controlled by the star's gravity and it will start wandering around all over the place. So whenever it goes close to a massive object, it is like a traffic light, right? It will get diverted. It's like a traffic police diverting them into different direction. They can wander around, their trajectories can be changed by the presence of a massive objects. So these are called rogue because they are not confined to any of the parent star. Okay, so this is my understanding. I hope it is.
Yeah.
Okay.
तुम्हाला सांगायचं का काही या रोग प्लॅनेट्स बद्दल, जे ग्रह असे त्यांच्याबरोबर तारेच नाही आहेत असे काही ग्रह असू शकतात?
प्रोफेसर श्रीयादनांनी सांगितलं, त्यांनी पूर्ण ते कवर केलेलं आहे, पण 1-2 लहानशा गोष्टी राहिलेल्या आहेत त्या म्हणजे इंटरेस्टिंग आहेत. की समजा असा ग्रह आहे की तो कोणत्याही ताऱ्याभोवती फिरत नाही, तर आपल्याला तो ऑब्झर्व करणं जवळजवळ अशक्य होतं. जेव्हा तो ताऱ्याभोवती फिरत असतो तर जसं आपण आत्ता एक्लिप्सबद्दल बोललो त्याप्रकारे जेव्हा तो ग्रह ताऱ्याच्या समोरून जातो तर त्यातलं प्रकाश थोडासा कमी होतो आणि त्याच्यावरून आपल्याला समजू शकतं की तिथं ग्रह आहे. पण तो ग्रह असा फ्रीली फिरत असला कारण ग्रहातून काय म्हणजे ऊर्जा आपल्याकडे काहीच येत नाही आहे आणि तो ताऱ्यापासून दूर असला तर ताऱ्याचा प्रकाश पण तो रिफ्लेक्ट करणार नाही आणि त्याच्यामुळे अशा ग्रहांना डिटेक्ट करणं अतिशय अवघड असतं. पण समजा तो ग्रह नसून समजा तो ब्लॅक होल आहे किंवा समजा ब्लॅक होल ताऱ्याच्या जवळ असला तर तो द्रव्य शोषण करतो आणि त्याच्यामुळे तो आपल्याला दिसू शकतो कारण ते द्रव्य गरम होतं आणि त्यातून क्षकिरण बाहेर पडतात. पण जर का एकच असा ब्लॅक होल असला तो आयसोलेटेड आहे आणि तो जातो म्हणजे तो आपल्याला दिसणं अशक्य होतं. पण गेल्या वर्षी काही शास्त्रज्ञांनी अमेरिकेमध्ये कैलास साहू म्हणून आहे म्हणजे आपले भारतीय वंशाचे पण तिथं ते अमेरिकेत असतात स्पेस टेलिस्कोप सायन्स इन्स्टिट्यूटमध्ये. तर त्यांनी एक फार सुंदर पेपर लिहिला होता त्यांच्या सहकाऱ्यांबरोबर की ग्रॅव्हिटेशनल लेन्झिंग वापरून अशा ब्लॅक होलचा शोध घेता येतो. कदाचित ग्रहाचं पण घेता येईल त्या प्रकारे, पण त्याची इंटेन्सिटी कमी राहील एवढंच.
अगदी नाही, अशा प्रकारचे आणि जे ब्लॅक होल्स आहेत त्याचा शोध आम्ही घेण्याचा प्रयत्न करतो अँड्रोमेडा गॅलेक्सीचे तारे वगैरे बघून. आणि इट्स क्वाईट इंटरेस्टिंग की काय काय करायला लागतं एवढे छोटे ग्रह जेव्हा शोधायचे असतात तेव्हा. ओके, सो मी पुढचा जो प्रश्न आहे तो जेवीएन तुम्हाला विचारतो. डज ही हॅव द कागद? हां. सो पहिला प्रश्न होता तो म्हणजे आर वी अलोन इन द युनिवर्स? आपण विश्वामध्ये एकटेच आहोत का?
ह्याचं उत्तर मी मराठीत देऊ का?
हां चालेल, मराठीत द्या.
मराठीत या प्रश्नाचं उत्तर खरोखर म्हणजे बरोबर उत्तर द्यायचं म्हणजे आपल्याला अजून माहीत नाही तुमच्या प्रश्नाचं उत्तर. पण आपण तर्क करू शकतो, आणि जर तुम्ही तर्क करायला लागलात तर परिस्थिती अशी आहे. थोडक्यात 2 गट आहेत शास्त्रज्ञांचे. एक असं समजतो की पृथ्वीवरती जी जीवसृष्टी आपण पाहतो तेवढीच आहे विश्वामध्ये, दुसरीकडं कुठं नाही आहे. आणि बाकीचे त्या ग्रुपमधले लोक म्हणतात की असं काय म्हणून तुम्ही कुठल्या बेसिसवर म्हणता? तर त्याचं कारण असं दिलं जातं, पूर्वी असं द्यायचे की पृथ्वीवर जी जीवसृष्टी आहे ती एका विशिष्ट कंडिशन्स परिस्थितीमुळं झालेली शक्यता आहे. आता सूर्यापासून जर तुम्ही खूप लांब असलात तर फारच गार होते आणि आपलं जीवन तिथं होऊ शकणार नाही नवीन. जर सूर्याच्या खूप जवळ असता तर उष्णता खूप वाढली असती आणि तुम्हाला जीवसृष्टी मिळाली नसती. तेव्हा पृथ्वी एका योग्य अंतरावर आहे. तर अशा तऱ्हेचं वेगवेगळी कारणं देऊन लोक म्हणायचे की पृथ्वीवर ही परिस्थिती इतकी अनयुज्युअल आहे, असंभाव्य आहे की दुसरीकडं कुठं जीवसृष्टी असणार नाही. तर लोकांना असं दिसून आलं आहे त्यानंतर की सूर्याभोवती ग्रह आहेत. लोक म्हणायचे इतर ताऱ्यांभोवती कुठं ग्रह आहेत, तेव्हा त्याचं जीवसृष्टी कशी होणार असं ते म्हणायचे 50 वर्षापूर्वी. परंतु आता आपल्याला दिसून आलं की बरेच पुष्कळच ग्रह आहेत इतर ताऱ्यांच्या भोवती, आणि त्यामुळं असं म्हणता येणार नाही की पृथ्वी ही एक विशिष्ट प्रकारचीच जागा आहे सूर्याभोवती फिरायची. दुसरी गोष्ट म्हणजे आपल्याला एक थोडक्यात सांगायचं म्हणजे अलीकडं आमच्या काही प्रयोगामध्ये इस्रो इंडियन स्पेस रिसर्च ऑर्गनायझेशनतर्फे केलेल्या प्रवेशामध्ये आम्हाला असं दिसून आलं की इथून एक बरंच अंतर वर गेलं, साधारण 40 किलोमीटर वर गेलं तर तिथं तुम्हाला जीवसृष्टी तिथून आपण हवेचे सॅम्पल गोळा करून खाली आणून तपासले तर त्याच्यामध्ये आपल्याला बॅक्टेरिया सापडतात आणि जिवंत बॅक्टेरिया सापडतात. काही बॅक्टेरिया असे आहेत जे आपल्याला पृथ्वीवर सापडलेले नाही आहेत. तेव्हा असं शक्यता आता दिसून येते आहे की इतर ग्रहातून जर जीवसृष्टी असली तर ती थोड्या प्रमाणात आपल्या कॉमेट्स येतात, ग्रह येतात, तर आपले धूमकेतू येतात, तेव्हा धूमकेतू ते घेऊन येतात आणि तिथं जवळपास कुठं ते रिलीज झाले धूमकेतूच्या शेपटीतनं की ते जाऊन ह्याच्यामध्ये अंतराळात आपल्याला सापडतात. तेव्हा ही एक शक्यता आहे की बाहेरचे जीवसृष्टी आहे. तर आमचे पुढचे प्रयोग जे आहेत ते हे तपासायचे आहेत की इथं मिळालेले बॅक्टेरिया ह्यांच्यामध्ये त्यांचे न्यूक्लिअर हे कार्बन किती आहेत बघितलं, कार्बन, ऑक्सिजन, नायट्रोजन यांचे परिणाम काय, प्रमाण काय आहे हे बघायचं. आणि ते पृथ्वीपेक्षा वेगळं असलं खूप तर हे बाहेरचे असावेत असं आपल्याला म्हणता येईल. तर ही तपासणी आमची चालू आहे. तर अशा तऱ्हेनं हळूहळू आपल्याला उत्तर मिळू शकेल. पण ते उत्तर काय असेल, अर्थात मी ज्या तऱ्हेनं तुम्हाला सांगितलं त्यावर तुम्हाला वाटेल मी दुसऱ्या बाजूचा आहे, म्हणजे पृथ्वी पलीकडे जीवसृष्टी आहे असं मी समजतो. ते बरोबर आहे, तुमचा अंदाज बरोबर आहे, माझा तर्क बरोबर आहे की नाही हे आता असं बघायचं. आता ह्याच्या पुढं मी आणखी जात नाही, ह्याच्यात पुष्कळ बोलण्याजोगं आहे.
नाही, सो हा जो प्रश्न आहे की आपण एकटेच आहोत की नाही, अगदी लहान मुलांपासून सगळ्यांना मोठ्यांना पण पडत असतो. मलाही आठवतं की मी लहान असताना मला माहिती पाहिजे होती की सगळी जी जीवसृष्टी आहे ती फक्त पृथ्वीवरतीच आहे की अजून दुसरीकडे कुठे आहे. पण हे जे प्रश्न आहेत ते इतके मोठे आहेत की ते सोडवण्यासाठी खूप वेळ लागू शकतो. तर मला ॲक्च्युली हे विचारायचं होतं, तुमच्यापैकी कोणीही उत्तर देऊ शकता, की आत्ता भारतामध्ये जे काही आपण मोठे मोठे प्रयोगांमध्ये इन्व्हॉल्व झालेले आहोत त्यापैकी कुठले प्रयोग शोधू शकतात का की देर मे बी लाईफ ऑन डिफरंट प्लॅनेट्स or search for life on different planets? Is there any experiment going on, or are we part of some mission which can help find find the answer to this question?
उत्तर देऊ शकेल. So do it in English?
Yeah.
पण त्याच्या आधी एक मला सांगायचं आहे की आता पुण्यामध्ये आपल्या रस्त्यावरती इतकी गर्दी आहे, या ऑडिटोरियममध्ये इतकी गर्दी आहे, पण इतर ग्रहावरचे लोक इथं आले तर काय होईल त्याचा विचार करा. त्याच्यामुळे ते न आलेलेच बरे आपल्याला. आता
एलियन्स आले तर खूप त्रास देतील आपल्याला.
आणि मग आता चल की कोणत्या प्रकारे एक्सपेरिमेंट्स करता येतील. आता प्रोफेसर नार्लेकर यांनी आपल्याला सांगितलं की आता अनेक ग्रह इतर ताऱ्यांच्या भोवती आपल्याला सापडलेले आहेत. 1995 साली अशा पहिल्या ग्रहाचा शोध झाला. आणि त्याच्यानंतर म्हणजे व्हॉट आय एम सेईंग इज दॅट द फर्स्ट एक्स्ट्रा टेरेस्ट्रियल प्लॅनेट, एक्स्ट्रा सोलार प्लॅनेट वॉज फाउंड in 1995. After that, many experiments have been performed, and we literally have thousands and thousands of these planets. And many of these planets have atmospheres. And it is possible to look for signatures of life in the atmosphere. Because when we exhale, we are sending out carbon dioxide, but there are sort of other molecules also which have to do with life, which can be present in the atmosphere. So you may ask, how is it possible to look at the atmosphere of a planet which is so far away? So that is because now we have extremely precise instruments. In particular, you must have heard that the James Webb telescope is present. The James Webb telescope makes observations in the infrared, near infrared, and that is where many of the molecules which are important for life can be detected. So it is quite possible that soon, when I say soon, I mean just in a few years from now, you will be able to see traces of life if it exists around the planets.
हा जो प्रश्न आहे तो त्याचं उत्तर मे बी तुमच्यापैकी जे बसलेले लहान मुलं आहेत ते थोडेसे मोठे होतील, शास्त्रज्ञ होतील आणि शोधू शकतील. आणि त्याचं म्हणजे आम्हाला खूपच अभिमान वाटेल जर तसं झालं तर आणि होऊ शकलं तर. पण त्याच्यासाठी बरेचसे जे प्रयोग आहेत त्याच्यामध्ये आयुका पण इन्व्हॉल्ड आहे. भारतातले बरेच जे मोठे मोठे टेलिस्कोप्स जगभरात बांधत आहेत त्याच्यामध्ये आपला सहभाग आहे. आणि त्याच्यामुळे ही जी काही सुविधा आहेत त्यांचा वापर करून मे बी तुम्ही शोधू शकता. ओके ओके, लेट्स मूव टू द नेक्स्ट क्वेश्चन. पुढचा जो प्रश्न आहे तो दत्ता अर्जुन कच्छवे म्हणून ते विचारतात की दीर्घिका एकमेकींच्या वरती आदळले की काय होते. व्हॉट हॅपन्स व्हेन गॅलेक्सीज कोलाइड विथ इच अदर.
आय कॅन डू दॅट इन मराठी.
या लेटर ऑन यू कॅन डू इट इन मराठी.
Hello. Okay, you know what is a galaxy, right? The galaxy is a collection of stars, and from whatever you have seen, if I ask you what kind of galaxies you know, you will say spiral galaxy, elliptical galaxy, or whatever. And this is mainly because the arrangement of stars in a statistical way, in the sense that the stars are all moving around, like there is no object in the sky which is motionless. Right? They are all moving around, but if you take a snapshot, you see them like this. So if you take two such galaxies and bring them close to each other, the stars which were just going around and producing nice pattern like elliptical or spiral or whatever, they are actually feeling a force coming from the galaxy only in the beginning. So that is set up. Now, for example, you guys have all settled down nicely in this room because we have an equilibrium. We said like till sometime you have to sit here, right? Imagine somebody in the corner gives you an information, there is a fire there. What will happen? You will start randomly move because you can think of an additional force which is being injected into this room, because of which you will start moving around. This is what exactly will happen. If two galaxies start coming, earlier stars will be feeling force from only one galaxy. Now some stars will start feeling force from both the galaxies. Since the galaxies are moving, the distance between them is changing, the force is also changing. It's like saying that you are accelerated car, right? You are not going with the same speed. And your direction is changing this way, that way. So for some time, the stars doesn't know what to do, right? Because they don't know whether to follow this galaxy or the other galaxy, or combined effect. So they will go into some kind of chaotic motion. So you will see, if you look at pictures of two galaxies which are nearby, taken by Hubble Space Telescope, you will find stars distributed all over the place. They will not look like a spiral galaxy, or they will not look like an elliptical galaxy. But the gravity is an interesting force. It is always attractive, right? So you let it for some more time. This like your planets going around star, or two stars going around each other. When two galaxies start colliding, at some stage they will start going around each other and eventually settle into one massive object. It takes some time. Typically it is 10 to the 8 years to 10 to the 9 years it will take, because these galaxies will go like this for some 100 times or whatever. Each time it will take 10 to the 6 years to go. 100 times means 10 power 8 years. This is like, what is that? 10 times 0.1 billion years.
100 million.
So then, if you wait for sufficiently long, we cannot wait.
Yeah.
If you wait for sufficiently long, they will end up being one of the elliptical galaxies. Very massive elliptical galaxies with a total mass will be sum of these two masses.
Yeah. But you know, one thing that I'm always amazed by, like if we see two cars colliding, that is something that I can see, right? And you see like a huge explosion that happens and lots of sound and so on. Does something like that happen when these galaxies collide?
It should happen. I think the only thing is that whenever happens, some sound is created and your ear has a correct thing to detect this sound. So if you have a detector which can detect whatever perturbation, sound is nothing but my tongue is vibrating and I am creating some perturbations, some vibrations in this air, and that is propagating towards you. If this merging thing create vibrations due to various things, I will not go into the detail, that wave can travel towards you. If you have a device which will detect this wave, you will detect them. Is that correct?
Yeah, you should.
That sound is, I'm not sure it will be in the frequency in which we can hear.
But what about stars colliding?
It should be there. Any collision should lead to such vibrations which you should be able to detect. And vibrations will propagate, right?
Yeah.
You should be able to detect.
Although the question is always about whether there are probabilities and whether there is the chances of stars colliding with each other and so on, whether they are small or big. That is something, maybe Ajit, if you
I will tell you something a little bit different from what they said, a different possibility. Just imagine that there is one big group of people who are running in one direction and another big group of people running in the other direction. It is possible for the two groups to pass through each other completely. right, without hurting anybody at all. So that one group from there goes away there, the other group goes there. Exactly the same thing can also happen in the galaxy. There are situations in which two galaxies just pass through each other without creating any problems. On the other hand, it's more likely, possibly, that what Professor Anand said will happen is that the stars will be attracted by two galaxies and therefore the shape keeps changing. Now, then there's also another possibility, is that each galaxy has got a supermassive black hole. Right? So the two supermassive black holes can start circling each other, and then they can merge to form a single supermassive black hole, or they can simply remain as two supermassive black holes. And all this has very great implications for the final shape of the galaxy. So all possibilities are there.
Yeah. And we see them. We often see galaxies colliding. I think you must have seen these images from the James Webb Space Telescope. One of the images was of these colliding galaxies, right? And so it's an interesting thing which happens rarely, but it does happen.
Yes.
But just to add on to it, if you believe in the kind of research which is going on, it says that every galaxy should have gone through a merger.
Yes.
During its evolution,
yes,
it would have gone through a merger. I mean, like, it's very rarely that you would have a galaxy which has been pristine, one object from the very beginning. So.
Yeah. ओके, आपण पुढच्या प्रश्नाकडे जाऊया. त्याच्यामध्ये विचारलं आहे भक्ती अर्जुन पॉल म्हणून आहे त्यांनी, की अवकाशामध्ये हवा नाही आहे, तर मग अवकाशात थंडी का आहे?
आता मी तुम्हाला एक उदाहरण देतो. लवकरच होळी आहे, तेव्हा लोक हे मोठे मोठे जुने काय लाकडं गोळा करून आग तयार करतात. त्या असे समजा वेगवेगळ्या ठिकाणी होळ्या जळत आहेत, आणि तुम्ही इथून तिथं चालत गेलात, तर जसं जसं एखाद्या होळीच्या आगीजवळ जाल तुम्हाला उष्णता वाटेल, लांब जाल तसे तर थंडी वाटेल, पण तोपर्यंत दुसऱ्या होळीच्या जवळ गेलात तर त्याची उष्णता तुम्हाला मिळेल. तर अशा तऱ्हेनं अंतराळामध्ये वेगवेगळे तारे आहेत, त्यांच्यापासून जो प्रकाश येतो त्याची उष्णता असते. सूर्यापासून जशी उष्णता आहे, त्या सूर्याच्या खूप जवळ गेलं, जाऊ नका, पण गेलात तर आम्हाला काय झालं सांगायला राहणार नाहीत, पण ठीक आहे आम्ही बघू. तर मला असं म्हणायचं आहे की इतके तारे जे आहेत पसरलेले, त्यांच्यापासून जी प्रकाश येतो त्यांच्यामुळं अंतराळात वाटेल आपल्याला उष्णता दिसते. एवढंच नव्हे तर याच्यात पलीकडे गेलात तर आपले सगळे हे तारे एका आकाशगंगेत आहेत, आणि अशा अनेक आकाशगंगा आहेत. त्या सगळ्यांचा आपण हिशोब केला तर आणखीन आपल्याला काहीतरी उत्तर मिळतं. आणि असं करत करत शेवटी आपल्याला असं दिसतं की अगदी कमीत कमी तापमान किती तुम्हाला मिळू शकेल. तर त्याचं उत्तर साधारण 3 अंश 3 डिग्रीज केल्विन म्हणजे तुम्हाला जे 0 सेंटीग्रेड म्हणतो, सेल्सिअस म्हणतो, त्याच्यापासून 273 मग कमी केलेत की 0 ॲब्सोल्यूट येतो. तर त्याचे 3 डिग्री घेतले म्हणजे खूपच कमी झाले. तर आपल्याकडं आपण असं म्हणू की विश्वामध्ये सगळीकडं हे तापमान भरलेलं आहे, आणि हे जे काय विश्वामध्ये प्रकाश आपल्याला फिरताना दिसतो तो सगळं एकंदर गिव्ह अँड टेक किती प्रकाश तुमच्याकडे सोर्सेसमधून येतो आणि किती प्रकाश सोर्सेस बाहेर टाकतायत, हे सगळे हिशोब लावून आपल्याला शेवटी हे एक गणित मिळतं. आणि हे जे 3 डिग्री आहे हे 3च का 4 का नाही किंवा 100 का नाही, तर याचं उत्तर अजून आपल्याला मिळायचं आहे. जे बिग बँग थेअरीवाले म्हणतात की विश्वाची उत्पत्ती एका मोठ्या स्फोटामध्ये झाली, त्यातनं पुष्कळ उष्णता बाहेर पडली आणि ती आता पसरलेली सगळीकडे दिसते. आणि ते आज 3 डिग्री तापमान आहे. ते प्रसरण पावत जाईल तसं ते आणखी कमी कमी होत जाईल. अशा तऱ्हेनं आपण या प्रश्नाचं उत्तर देऊ शकतो.
सो पृथ्वीवरती आपण राहू शकतो कारण की वातावरण आहे, पण जर तुम्ही कुठेही बाहेर गेलात तर तिथलं तापमान खूपच कमी असणार आहे, -270. हे नुसतं जॅकेट घालून वगैरे काम होणार नाही आहे काहीच. ठीक आहे, याच्यानंतर आपण पुढचा प्रश्न घेऊ. तो आहे मारुती अमृतराव तारे आहे ते. त्यांनी विचारलेलं आहे की जर मला रॉकेटने सूर्याच्या जवळ जायचं असेल तर मी काय करू शकतो. मला वाटतं त्यांनी पार्कर प्रोब जे आहे नासाचं सोलर प्रोब त्याच्याबद्दल ऐकलेलं असणार आहे. तर त्याला विचारायचं आहे की जर मला रॉकेट सूर्याच्या जवळ जर घेऊन जायचं असेल तर काय करायला लागेल.
आता जर का आपल्याला चंद्राकडे एक यान पाठवायचं तर आपण काय करतो की इथून रॉकेट आपण पृथ्वीवरून बाहेर जातो. तो एका कॅल्क्युलेटेड कक्षेमध्ये त्याचं भ्रमण चालू असतं व हळूहळू तो पृथ्वीच्या गुरुत्वाकर्षणाच्या बाहेर पडून चंद्राकडे आकर्षित होतो आणि मग चंद्राकडे तर यान उतरतं. जर का तुम्हाला सूर्याकडे जायचं झालं तर एक्झॅक्टली तसंच करता येतं आणि पार्कर प्रोब वगैरे तिथे गेलेले आहेत. पण एवढंच की तुम्ही जसे सूर्याच्या जवळ याल, थोड्या वेळापूर्वी प्रोफेसर नालेकरांनी आपल्याला सांगितलं ताऱ्याच्या जवळ याल तर तापमान वाढत जातं. तर त्याच्यामुळे तुम्ही जर का फार जवळ गेला तर पूर्ण वितळून जाणार, मग तुमचा गॅस निर्माण होईल आणि मग तुम्हाला काही समजणार पण नाही. त्याच्यामुळे सूर्याचा अभ्यास अगदी जवळून करणं हे फार कठीण होणार आहे.
यू वॉन्ट टू ॲड समथिंग अबाउट द सन and how to go close to the sun and how to study the sun?
I just said that going there is no problem.
How to go there is easy, but how to survive that?
I don't know how to put it in a simple way, but I can give 2 examples which you would have seen. One is it's very prevalent in South India. In the temples you will see that they put burning coal over something, and the people who are dancing will walk on that. And the people say that for some reason. But if you ask the person to walk very slowly, he will not do it. Right? Similarly, you would have seen in YouTube channels nowadays, it's very famous. These people who are making vada, right? You will see this guy will put and take it with his hand from oil, hot oil. You just ask him to do slowly. He will not do it. So which means the effect which we know, burning or heat being this thing, it depends on some time. It takes some time for us to realize. Even this happens when you go in a hot sun, your shirt becomes very hot after some time. So there is a time scale involved where your object will reach whatever is the temperature you should reach because of the heat coming from the external source. Okay? So you can use this technique. For example, if you throw something into sun very slowly, it will burn before it reaches this thing. If you find an optimum speed, the speed should be such that before it reaches to some distance, it should not melt or it should not evaporate. Right? So you choose a material which will be slowly responding to heat, and you choose the speed in such a way that you can reach wherever you want before it is getting destroyed. If you can achieve this thing, it can be done. I am giving very generic answer.
No,
I hope this is what has happened.
Yeah, it's a material engineering problem, and of course astronomy is such a topic that you cannot just learn about one thing. You have to know about everything and bring it all together in order to study the universe. So indeed, it is an engineering feat that they were able to manage this, and they were able to build this probe which can actually go very close to the sun. Okay.
And this is one of the basic understanding in astrophysics, because everything takes some time, right? So this is one of the things we teach in the beginning of anything you learn in astrophysics, because equation somebody writes, that equation will be valid only after some time. Okay? So this is what we do in Earth is instantaneous. Anything happens immediately. And this is a good lesson for youngsters also, because I know that youngsters want everything quickly. So every process should have some time, so relax and do it over that period.
It's useful to do things slowly, of course. Okay, let's take a third question. So this is for you. How did humans find out about the formation of Earth from the history without seeing it? No, okay.
I think in science what you do is you, to some extent, speculate. But your speculations are based on two things. First is what you see now, whatever observations you make. And the second is what are the laws of physics which govern the behavior of matter. If you know those laws and you know the present distribution of matter, then you could in principle work out how it came about like that, or what will happen to it in the future. But of course this is the hopeful sort of the way to go about it, but we should be aware that our knowledge is very, excuse me. That our knowledge is very limited, and we therefore don't know for sure what will happen. But whatever is known to us, based on that we can say, for example, how did the planetary system form around the sun, of which Earth is part. So you think of a rotating cloud of gas, and what will happen to a rotating cloud of gas? The thing is, because of attraction of gravitation, it will tend to shrink. At the same time, because it is going round, it will tend to flatten also, because things go further and further out if you go round swinging them. So you therefore have a bulge in the middle, which becomes the sun, and a flat kind of disk-like thing around it, which condenses into planets, of which sun may be, Earth may be one. So this is the kind of solution. And then what are the materials of which the Earth was made? What you find today and what you found earlier would have been related by how matter evolves with time. Now there are certain nuclei which decay with time, and from that you can work out the ratio of two different nuclei. If you know from material dug out from the earth, geologic or geophysical information, then you can work out how old that material is. And if you look at various parts of the earth and look at these material, you begin to get an idea of how old the earth must be. So I am only giving you a kind of vague answer because we don't have precise figures to tell you. So I would say that how did they discover? Have they actually discovered? We don't know. They are towards finding the answer. Some progress has been made. A lot needs to be made.
Indeed, yeah. So it is very difficult to know exactly how the Earth formed. But we do also see different planets which are forming around other stars. And now telescopes are good enough to actually observe these things happening right at the moment that there is a star which is born, there is a disk around it, and you can see some new planets forming as well. So we can we can just make predictions or we can build theories about what must have happened such that the earth formed. Okay? Okay. पुढचा जो प्रश्न आहे तो रोहित शरद यादव यांनी विचारलेला आहे. अवकाशात कोणतंच मीडियम नाही आहे, तर मग शास्त्रज्ञ कृष्णविवरांचे आवाज कसे रेकॉर्ड करतात? आवाजाला तर मीडियम लागतं, पण मग व्हॅक्यूम असताना हे आवाज कसे काय? आता मला वाटतं त्यांनी लायगोबद्दल ऐकलेलं असणार आहे कृष्णविवर.
हो, कृष्ण. आता तुम्हाला माहिती आहे की आपल्याला, आता मी तुमच्याशी बोलतोय, तुम्हाला ते ऐकू जातं. कशा प्रकारे ऐकू जातं की इथून माझे कंपन असतात हवेतले, ते इथं मायक्रोफोनपर्यंत पोचतात. मग ते गेट कन्वर्टेड टू इलेक्ट्रिकल पल्सेस आणि मग ते लाऊडस्पीकरकडे ट्रान्समिट होतात आणि तिथून परत एक डायफ्रॅम असा मूव्ह होत असतो आणि त्याच्यावर ते ऐकू जातं. तर माझा आवाज इथपर्यंत पोचायला आणि लाऊडस्पीकरपासून तुमच्यापर्यंत पोचायला या वातावरणाची गरज असते. आणि तसं वातावरण आपल्याकडे आता स्पेसमध्ये नाही आहे. मग आवाज कसे येतात? मग त्याचं अगदी सुटसुटीत उत्तर आहे की तसे आवाज येतच नाही आपल्याकडे. पण काय होतं की जेव्हा ते ब्लॅक होल्स एक आपल्याभोवत फिरत असतात किंवा त्यांचं काय पल्सेशन होत असतं, तिथं ब्लॅक होलचं नव्हे पण एखादं ताऱ्याचं समजा पल्सेशन झालं, तर ते पल्सेशन एका पर्टिक्युलर फ्रिक्वेन्सीचं होत असतं आणि ती फ्रिक्वेन्सी, त्या फ्रिक्वेन्सीचा आवाज आपण इथं काढू शकतो. आणि मग त्याला आपण म्हणजे इट इज अ सॉनिफिकेशन, म्हणजे एक दुसरी प्रोसेस आहे आणि त्याची फ्रिक्वेन्सी आपल्या आवाजाच्या फ्रिक्वेन्सी त्याच रेंजमध्ये असते आणि त्याच्यामुळे आपण कृत्रिमपणे ते इथं प्रोड्यूस करतो. म्हणजे तो खरा आवाज नाही आहे तिथं गेला तर तुम्हाला तो ऐकू येणार नाही. मग तिथे गेला तर तुम्ही लगेच ब्लॅक होलमध्ये पडून मरून जाल. त्याच्यामुळे तो काय ऐकायचा प्रश्न असणारच नाही आहे तिथं. पण हेच उत्तर आहे.
तर बऱ्याच लोकांनी हे जे ब्लॅक होल असतात कृष्णविवर, ते एकमेकांभोवती जातात आणि ते आदळतात याच्याबद्दल ऐकलेलं आहे. तर मग यांची जी जाण्याची फ्रिक्वेन्सी आहे ती आपल्या कानाच्या, म्हणजे आपल्याला ऐकू येईल अशा प्रकारच्या फ्रिक्वेन्सी काय आहे? ती कशावरती ठरते?
आता ती फ्रिक्वेन्सी जी असते ते त्यांचं अँग्युलर मोमेंटम किती आहे. म्हणजे आता दूरवर असतात ते सावकाशपणे एकमेकांच्या भोवती फिरत असतात, पण मग त्यातून गुरुत्वाकर्षणाच्या वेव्ह ज्या असतात, ग्रॅव्हिटेशनल वेव्ज आपण म्हणतो, गुरुत्वीय लहरी त्या बाहेर पडत असतात. त्याच्यामुळे त्याची ऊर्जा कमी होते आणि ऊर्जा कमी झाल्यामुळे ते ब्लॅक होल एकमेकांच्या जवळ येतात. जसे जवळ येतात ते परत जास्त जास्त वेगाने एकमेकांभोवती फिरत जातात आणि असं होता होता मग त्याची फ्रिक्वेन्सी आपल्या साऊंड फ्रिक्वेन्सीची मॅच होऊ शकते आणि त्याच्यामुळे आपण ती ट्रान्सलेट करून त्या साऊंड असं ते दाखवतो.
तर हे जे 100 हर्ट्ज वगैरे आपण म्हणतो ते म्हणजे एका सेकंदात 100 वेळा ते एकमेकांभोवती फिरत
असतात.
सो एवढे मोठे ब्लॅक होल्स ते एका सेकंदात 100 वेळा एकमेकांच्या भोवती जात असतात. ओके, त्यावेळेला आपण त्याच्यातनं ते गुरुत्वाकर्षणाचे ज्या लहरी असतात त्या आपल्याला येताना दिसतात आणि मग तो त्या ज्या लहरी आहेत त्या आपण डिटेक्ट करतो आणि मग त्यांचा आवाजामध्ये त्याचं
परिवर्तन करतो.
ठीक आहे. Okay, good. So the next question is for you. So this is from Arya Sunil Nayak. She wants to ask, how and when the universe will end?
I think you should ask these people here who they have a more recent information on this than I have. I feel the honest answer to this is we don't know the answer. Again, because there are different theories, something which people like to work on. What happens is that at the moment we see the universe is expanding, that is going further and further apart. Galaxies are moving apart. Question is, what will happen eventually? Because you will end with this question means later, what will happen? So the laws of gravitation and motion that we know tell us that the universe will either go on expanding forever or will start contracting after a while and shrink to a point. It is a possibility that something will happen when it becomes like a shrink, and it will bounce. It bounces, it again expands. So you have got this oscillation. So people have different theoretical models which tell you what will be happening to the universe eventually. But we need some more tests to decide what will happen. For example, now we have this new telescope, space telescope. What is it, James?
James Webb Space Telescope.
James Webb Telescope. Now it is telling us about galaxies which we are looking at now, which was light left very long ago. So you can calculate how long ago it was. And then you see that the universe was very, very young, if it was a Big Bang universe. Very young when those galaxies formed and sent light. So then it becomes a challenge for you to explain how did galaxies form and evolve
so quickly
to produce these shapes and this light. So new discoveries will pose new problems to existing theories. And they will have to find out how to correct themselves or how to change to new ideas. So it's an evolving process.
Yeah. Science itself is an evolving process indeed.
No,
Yeah,
I was
sorry.
saying that I wanted to link it with this last question.
Sure, yeah.
Which says, why are the laws of physics the same in the entire universe? I have been talking of laws of physics.
Yes.
Now, the question is, laws of physics, first of all, you can ask this question, why should there be any laws of physics? The universe could be without any laws. Like you have a situation, a society operating under no laws. There's a lot of chaos in that society. Think of a cricket pitch in which the bowler is bowling. The ball bounces. Now, which way the ball will go? If the pitch is cleverly prepared, the batsman will never know which way the ball is going to go. And sometimes he will get hit. So, the thing is, universe is seen over a given distance, looks to be having a less chaotic behavior than what I was just describing. So there may have been laws of physics. But why should they be the same from here to there? This is a very fundamental question. And we cannot answer it at the moment. And one has to say, let us assume that what we see correspond to certain laws, how far those laws will work, and that will decide.
Sure, yeah. So in fact, there are people who are trying to search whether some of these fundamental laws are different in different places in the universe. In fact, Sri Anand has worked on observational data in order to look for these kind of differences. Do you want to make a comment on this?
Yeah, I think I'll make a very jovial comment on the first question.
Okay.
When will the universe end? I will do exactly like the way we do astronomy. So we go and look at something. If you don't find an object, we'll never say that there is no object. We will only say that there is no object brighter than some value. So what if you ask the question how long the universe will be there? My answer it will be more than how long you will live. The second answer I can say is that it will be more than how long Earth can live, because at least this we can calculate conservatively how long Earth will survive under sun. I think that time scale will be very short compared to anything else we can think of about the universe. So That part, let's not worry about it, okay? Let us leave it to the experts to decide what will happen in a billions of years afterwards. Coming back to physics, again, it is my take. I hope you guys will understand or agree to it. As far as I am concerned, physics is a science which was established to understand what you observe. Suppose if you observe something, you write down laws of certain equation which is governed by laws which we agreed upon, so that based on this equation we should be able to explain what is happening. The success of physics is like this: whatever, most of the things which is happening in the earth, we have found out some way of understanding mathematically, right? This is what it is. The question whether this physics is valid at large distances, you can do other way around. If I am looking at something far away distance, can I predict what I see there based on whatever physics I have developed to understand what I am seeing today? Like Professor Nallikar said, it is not necessary that it has to be correct, right? Because Newton's law was created to explain some observations, which miserably failed to explain certain other observation which resulted in quantum mechanics was created. So exactly like this, whatever we think is a law of physics, which is successfully explaining what we see here today, but it is not necessary that all observations you see far away can be explained by that. So this is where the debate is. If you find something far away, either this is a peculiar event or it is a peculiar physics. So we people try to debate on this. I think that is the way it is now.
पण शास्त्र जे असतं ते असंच असतं की म्हणजे तुम्हाला जे काही आत्ता दिसतंय ते तुम्ही बघू शकता, तुम्ही सांगू शकता, त्याचा वापर करून बाकी तर करू शकता, पण शेवटी तुम्हाला जाऊन ते ऑब्झर्व करायला लागतं की खरंच तसं निसर्गामध्ये होत आहे की नाही. जर तुम्हाला दुसरं काहीतरी दिसलं तर तुम्हाला हे जे नियम आहेत ते आपल्याला बदलायला लागतात की आणि ते त्याचाही पाठपुरावा करायला लागतो की त्याच्यामुळे अजून काय होऊ शकतं. That's fine. Okay. Maybe we'll take one more question. And so this one is from Ganga Prasad Kalbande. आणि ते विचारतात की पृथ्वी फिरता फिरता जर थांबली अचानक तर काय होईल? if the earth starts rotating suddenly stops rotating, then what will happen?
अनेक गोष्टी होऊ शकतात. पण पहिल्यांदा म्हणजे आता इथं आपल्याकडे आता संध्याकाळच्या दुपारचे किती 3 वाजलेले आहेत, थोड्या वेळाने 6 वाजतील, अंधार होईल आणि मग 7-8-10 तासांनी परत उजेड होईल. ते काय होतं, तर पृथ्वी फिरत असते आणि जेव्हा आपला म्हणजे हिंदुस्थानाचा भाग सूर्याकडे वळतो तेव्हा इथं दिवस होतो. पण समजा पृथ्वी नाही फिरली तर मग समजा आपण तिथं सूर्याकडे त्या दिशेने आपलं हिंदुस्थान आहे तर इथं फक्त दिवसच असेल. म्हणजे मग कोणाला काही झोप नाही, काही नाही, फक्त काम करत राहायचं. आणि मग सोमवार नाही, मंगळवार नाही, बुधवार नाही, काही नाही, कारण सगळं स्टॅटिक होणार. तर अशा अनेक गोष्टी घडू शकतात. पण एक आम्ही या प्रश्नाबद्दल विचार करत होतो. तर आता प्रोफेसर निशांत सिंग ते एक तुम्हाला फार चांगलं एक उत्तर देतील.
So this is about what will happen if the earth suddenly stops rotating.
Yeah. So yeah, I mean, among many reasons that the life exists on the planet, one of the very important reason is that Earth is shielded by its magnetic field, which is basically shielding us from very harmful radiation particles, very high energy charged particles, which will otherwise penetrate through, and actually the life here on Earth will not be possible. One of the reasons that the magnetic fields are hosted by various astrophysical bodies, in fact, wherever you see in the universe, you always find magnetic field. At whatever scale you observe, you always find a magnetic field. And one wonders why there are so much magnetic fields everywhere you look for, right? One of the primary reasons for the existence of magnetic field, as it turns out, is the dynamo mechanism. Dynamo is a conversion of mechanical energy, kinetic energy that the bodies have due to other reasons. You convert them into the magnetic energy, and that's how the magnetic fields are produced and maintained in any astrophysical bodies, including the Earth. The way the conversion happens, it is fundamentally linked to the rotation of a body, because that is one form of a mechanical energy that you are tapping into and converting to make a magnetic field. once the earth stops rotating, it will happen that the magnetic field of the earth will be switched off. Yeah, not suddenly, of course, because it has its own decay time scale. If you switch off your fan or something, right? So there is a time scale over which anything will be decaying. There is a decay time scale involved, which can be very long, by the way, because the plasma that is driving, the motions in the plasma that is driving these magnetic fields are highly conducting plasma, so the time scales of decay are very, very long, okay? Nevertheless, the consequence will be the magnetic field will be decayed, and the shielding effect that we have will be gone. You could then come to a conclusion that the life will not exist without it.
But life always finds a way somehow or the other.
He explained to you a lot of things. When he said dynamo, I was wondering how many of you have used dynamo in your cycle?
Bicycle,
right? So it's a similar principle. Something is rotating. If you have magnetic field and something happens, you create current, and you can also do the other way around. The rotation can also create magnetic fields. So this is the...
Yep.
I thought I will just explain.
Yes.
So...
Okay, so this was a wonderful session that we had, and lots of questions that you
Beautiful questions, very good, very high quality questions.
Yes, very high quality questions. We also had trouble even trying to answer some of these, and sometimes there were questions which nobody still knows the answer to. So it was a pleasure to host all of you for this. But before we end, Professor Narekar, he had a question for all of you in the audience. So please.
मी तुम्हाला मध्येच एक उदाहरण दिलं तर माझे गुरु फ्रेड हॉयल यांनी एक उदाहरण दिलेलं आहे की आपण विश्वाच्या उत्पत्तीबद्दल जेव्हा आपण तर्क करतो ते बरंचसं असं असतं आपल्याला नियम विश्वाचे माहीत आहेत असं धरून त्याच्यावरून आपण सोडवतो प्रश्न आणि पुढं काय होईल ते सांगतो. तर ते म्हणाले की हे बरंचसं क्रिकेटमध्ये आपल्याला दिसून येतं आणि त्यांनी उदाहरण दिलं आहे की त्यांचे प्रिडिसेसर म्हणजे त्यांचे शिक्षक वगैरे जे एडिंग्टन म्हणून होते प्रख्यात शास्त्रज्ञ, ते क्रिकेटचे शौकीन होते. तर ते युनिव्हर्सिटी क्रिकेट ग्राउंड फेनर्समध्ये मॅच बघायला जात असत आणि विशेष महत्त्वाची मॅच असली तर ते काही 3-4 तास बसून बघत असत. मग त्यांना काही प्रश्न सुचले आणि त्यांनी मग एक प्रश्न बनवला. तो प्रश्न त्यांनी एका पेपरमध्ये दिला की तुम्ही सोडवा म्हणून. त्यामध्ये काय दिलेलं होतं तर एका टीमची दुसऱ्या टीमची मॅच होती. तर त्या एका टीमचं बॅटिंगचं सगळं स्कोअर कार्ड दिलं तर फॉल ऑफ विकेट्स दिल्या त्या आणि दुसऱ्या टीमचं बॉलिंग ॲनालिसिस दिलं तर बॉलर्सचं. आणि तेवढंच देऊन त्यांनी सांगितलं होतं की याच्यावरून तुम्ही प्रत्येक ओव्हरमध्ये प्रत्येक बॉलमध्ये काय झालं हे सांगू शकता. अर्थात ते जरा आर्टिफिशियल गणित होतं पण क्रिकेटचे नियम लागू होते आणि ते करता येत होतं. तर हे मी उदाहरण देतो आणि मी आता तुम्हाला एक लहानसं गणित घालतो. हे मी इतर ऑडियन्सेसना काही विद्यार्थ्यांना पूर्वी दिलेलं आहे. तेव्हा तुम्हाला जर उत्तर माहीत असलं तर उत्तरांना सांगू नका, त्यांना शोधू द्या. नाहीतर एकदम उठवून मला उत्तर सांगाल मग मजा जाईल सगळी. तर प्रश्न असा आहे की एका क्रिकेट मॅचमध्ये एका बॉलरनं हॅट्रिक केली पण त्याचे 3 विकेट्स 3 वेगवेगळ्या ओव्हर्समध्ये होते. हे कसं शक्य आहे? देर इज अ बॉलर हू स्कोर्ड अ हॅट्रिक and each wicket had fallen in a separate over. So how is it possible?
Okay.
To find out.
So who is going to find out the answers? I hope everyone, but don't shout, as he said. It's a question for you to go and think about. Okay? So with that, we will conclude this particular session. Let's thank all the dignitaries here for all the answers that they gave. And thank you for patiently listening. After this, we are also going to announce the winners of the model making competition. So please stay on for some time so that you can also felicitate, we will felicitate these winners. Okay? Thank you.
Thank you very much to the dignitaries. Please stay back. We have a short, just 5-minute distribution of prizes. So if you can please stay back. आपण जरा 2 मिनटं वाट बघूया. एक स्पर्धा आपल्या इथे घेतल्या गेली होती आयुकामध्ये, मॉडेल मेकिंग कॉम्पिटिशन. पुण्यातल्या साधारण 50 शाळांकडनं आमच्याकडे प्रतिसाद आला होता आणि त्या इथे लावलं आवाज तुझा देतो.
LIGO India project. I am also very passionately supporting the cause of women in astronomy and women in science in general. I am also a member of working group for gender equity of the Astronomical Society of India.
So I am Shukonda Mollik. I am a PhD student here. So in the 4th year, I am working on simulating a galaxy in a computer. So I am very, very passionate about singing. So I have been trained classically. So that's it.
Hello everyone, my name is Sanjit Mitra. I'm a professor here. I work on gravitational wave, LIGO India. I'm also the project coordinator for LIGO India at IUCAA.
Hello. You can hear. Hi everyone, I'm Anuprita More. I'm a scientist here. I work on gravitational lensing and gravitational waves, and I'm very excited to see here that there are a lot of young students who are interested in knowing about the role of women in science and how women can contribute more in astronomy. Thank you.
Hello everyone, my name is Siddharth Maharana. I'm currently a postdoctoral researcher at Institute of Astrophysics in Heraklion in Greece. Till last year I was a PhD student here in IUCAA, and I did my PhD here. I primarily work on developing instruments for telescopes to carry out interesting observations. Yeah, that's what I primarily do.
Hello everyone, I am Vishal Upendran. I'm a final year graduate student here at IUCAA. My research interests are generally on sun, so I study the sun and various aspects of it through observations, computer modeling and machine learning. I am also very much interested in science outreach, so I'm a part of I'm part of the editorial team of an outreach organization called Cosmic Varta. So very pleased to meet you.
So along with the panel members, it will be me, Manasa Devi. I am a scientist with the LIGO India project at IUCAA. So to begin with, we'd like to give you certain statistics that show that women are equally good in science and are made to belong in science. I invite Professor Sanjit Mitra to come and give his talk.
Okay, you can hear me loud, right? Okay, first of all, let me ask you. So, you know, we are discussing men and women here, okay? And I see that there are a lot of young students here. So let me ask you some questions, okay? And then we will get into the cause for why such things are happening. So, suppose there are some you know, there are exams happen at, like in class 10 level, class 12 level, etc. And there are many subjects, okay? Let's say there are some language oriented subjects, let's say English, French, German, etc. And then there are these subjects like maths, physics, etc. So now tell me, in which subjects do you think men or boys perform better? What is your guess? Students, yes? Science. That is maths, physics, right? Okay. And which subjects do you think girls do better? Arts. Somebody saying arts. So students will also say, girls, what do you think? Where do you think that girls do better and boys do better? Science? Say clearly, there is nothing like right or wrong. So many of the answers I will tell you, I just learned today when I was preparing for this talk. That is possible, but then we are talking about small children who are like, you know, they have not get into the household thing. I'm not giving any answers yet. Okay, I think more or less people would be thinking probably that, you know, this is the kind of the answer that students, the boys would be better in like maths and physics and girls will be better in let's say languages and so on, right? Okay, so this is, let's see how it goes, but let me first give you a statistics, and this is pretty alarming. Okay, this is what we want to address. These statistics I have got from different newspapers and also reputed journals, but then they may not be exact. There may be some pluses and minuses here and there. Okay, oh, you cannot see probably. So see, this number typically shows the fraction of women in science, in STEM subject, that is science, technology, engineering and mathematics, okay? You see that biology tops in terms of the proportion of women, it's 26, chemistry 11, physics 13, maths 16, computer science 12, engineering 9, and art sciences 14, okay? This is the picture in India, and this is not much different from US and UK. There are some proportional, in the first two, biology and chemistry, they are doing little better, but otherwise physics, for example, which is one of our primary research areas, things are absolutely in bad shape. Okay, maybe some improvement has happened. I mean, I don't know how old this is, but this is interestingly, this article came today in the Telegraph. So I got it from today's newspaper. So this would not be too old. Now, okay, many students are coming, so let's give a minute. But the point here is that this is not how it is supposed to be. And if we are seeing this, there must be some cause, and let's analyze it and then address it, right? This is how you would approach the problem. So let's see where the problem can happen, okay? And then we will get into the discussion after we identify. I give you basically the broad idea that where the primary problem is, and then we can have a lot more discussion on that. Now, let me come back to this question I asked a little bit before, okay? This is the CBSE class 12th results in 2015, right? This purple one is for female, the orange one is for male. And let's see that I asked some things like, let's say, in languages, okay, German, French, etc., okay? Surprisingly, male students did better there, okay? English is a bit different thing, let's not get into that. And let's come to the most important one, physics and mathematics. What do you see? Girls did better than boys, right? So this is how it is, right? So, so the point is that I will come to this in the end of the talk, of this small presentation, that the problem, the primary problem which we will see is that most young girls believe that boys do better in science. And this belief has a problem, so we'll come to that. Now you see that, now you will see that, well, maybe in secondary and at 10, 12 level, students do well, girls do well, and then they don't enroll for higher education. That is not correct. So these are the numbers. You see that the numbers are almost the same, and percentage-wise, actually, the enrollment ratio is in higher education is better for women than men in India. It's slightly better, but it is still more. So clearly, girls not enrolling for higher education is not the problem. They are not performing at class 10 or 12 level in maths and science is not the problem. These two are ruled out, and we are not going to discuss this. This is not the thing. Now, what is then the cause which is often cited? So that is what is often in literature said is that there is something called the variability hypothesis. The variability hypothesis says that on the average, men and women perform equally, but then the distribution has a higher variance for men. That is more men perform much better than the whole population, and in the same evaluation, some men would do much worse than the others, even though they can do better in life in other ways. So basically, there will be more men in the higher, like outstanding part, and there will be more also in the outstandingly bad part. That balances out. Now what happens is that because the science, research, etc. is driven by these outliers, then clearly men would do better. This hypothesis is wrong. And this is actually written by the same paper, same person, okay, who did the full analysis and showed that why this is wrong. And this is a distribution from 1.6. So they did this. I mean, I can read through this, but you will get bored. So I will tell you what exactly is happening here. So there is 1.6 million students data they considered, the grades of those students. You see, blue is for men, and this red one is for women. You see that systematically the average is better for women. But it is also true that the variance is larger. But then how do you know that whether variance is going to play the bigger role or the average? Because on the average, girls do better. But then there is this average, I mean, there are these outliers for men. Maybe that will overtake. So they did a simulation, and the simulation showed this, okay, that basically the performance is very much the same for men and women. There is absolutely no bias there. That is, the intelligence that we have when we are born, plus the education system through which we go through, altogether do not have any significant effect on this. So this is what is plotted here. I mean, many of you would not understand how the plots work, but all I can tell you is that if you take the top 10% performers in let's say STEM subject, that is science, technology, etc., there the performance of men and women based on those grades is basically identical. Okay? You absolutely cannot explain that why there are less than 20% women in science, in these areas like physics, etc., with this explanation. So the explanation, they also say in the conclusion, is something deep, something inbuilt in our society, the way we treat people, and psychology, okay? And that is where we will get into, but this is my last slide. After that, we will get into more this thing. The thing is that there was a survey which was done among 6-year-old girls and boys. 6-year-old, okay? They have no idea about anything else. But they were asked if they think that the smartest people in the world could be girls or boys. They did not think that the girls, 6-year-old girls, did not think that girls can be the smartest people in the world. But boys did. And this is where the bias is coming. So we have to give this feeling to the girls that there is absolutely no reason for them to feel that they are somehow in any way behind boys, okay? But what happens is that through conversation, so different aspects which we will discuss now, this idea becomes engraved in your mind. That idea is the biggest problem here. And there are many other things which are given in Wikipedia, for example. You can go through it, but I will not take more time. But the message we wanted to give you in this first part of the discussion is that this whole thing about intelligence, education, this, that, all those things are absolutely minor. Okay, there may be some minor differences here and there, but let's not worry about it. Let's focus on the problems which are the real problems, which are societal and psychological. Okay, I'll stop here. Okay.
Thank you, Sanjit. So we'll take forward our discussion today based on, we heard some statistics. So clearly, there is no bias in our education system. There is no bias, there's nothing wrong with our brains, right? And then, and the passion for science is also unbiased. I see equal number of men and women in the population, equal number of girls and boys in the population. So we want to see a future where women are strong enough to see themselves in a career in science. And that's what we'll start our panel discussion with. So my daughter is 6 years old, and I asked her to make a picture of a doctor, teacher, scientist, construction worker, and a nurse. And this is what she drew. So you can see her doctor is a male because her pediatrician is a male. And the nurse in the hospital is a female. So the nurse is a female character. And the construction worker is a male. Her teacher is a female because her teacher is a female person in school. She's only come across female teachers in school. And scientist, she drew 2. My husband is also a scientist and I am also. So she didn't miss me out. She's 6 years old. I try to keep her away from all these gender biases as much as possible. And I think parents these days are trying hard to do that in spite of the society giving you different notions of this is how a gender stereotype is. And this is what I get even after that. So gender stereotypes is something that we need to really work on, and that comes from the girls within themselves, the implicit biases we have, and from the support system for the girls in science. And how are we going to break stereotypes, and how do we prove and build the confidence in women and girls that they belong in science? So I'll ask one of you to start the discussion. Debarati?
Maybe we can.
Hello? Yeah. Okay. Thank you very much for these very insightful slides, which start off this very debate about why we think that this is a very inherent feature of our society, that we have this bias about men and women being made differently. This is definitely not the case. So I will just share a couple of researches that I had learned about. So one is from one of my colleagues in Brazil who conducted a widespread survey about the career paths of women and exactly at what point they think that women are quitting careers in physics. And interestingly, they made a survey and they showed that these numbers have a leakage effect. So basically, the numbers beginning in school and colleges, the interest among girls to be in science is still there. But as they progress in career, so the career options become narrower because there's more competition. And then there is mobility, geographical mobility, intellectual mobility. You have to go from one field to another. You have to move. Even if you have a family, you have to move. You have to make important decisions as to where you want a family, as to where you want to move to a different country for having postdoctoral careers and so on. And there is this leakage effect where as you progress in career from PhD to postdoc, and then you hit the glass ceiling where there is recruitment of women involved, and this is where there is extremely hard competition. So this is the point where women start to decrease in numbers. There was also one very interesting survey conducted by CNRS in France, where there was a master's project tracking the lives of women who are in this career. And they were actually following them and seeing at what point in their career they are dropping off, and they very much agree to this leakage effect. So this is something I wanted to say, that there are many surveys being conducted like this, and it looks like this effect starts to kick in later. Although here we are discussing other things like the societal effects and psychological effects, but I also want to say we also want to keep in mind these kind of factors where there are difficulties women face later in life, where they have to make a choice whether or not they want to continue in this career, and this is also a point where these numbers start to drop. Maybe someone wants to continue with.
Hello. Yeah, so maybe I will bring a slightly different angle compared to what Debrati just mentioned. So, yeah, talking about like breaking the stereotypes, as you know, like charity begins at home, and many of the things that Sanjit also mentioned, like it's not necessarily the education system that is playing a role here, but it's also how we are raising our children, how we are raising girls and boys. That plays a very important and subconscious role in the confidence, like as everyone has been talking about, the fact that even very young girls and young boys, they seem to have a slightly different opinion about themselves and people belonging to the other gender, right? And this comes from this implicit bias which is there in the parents, in the people, the family, friends, and everyone around you who are each and every day, each and every time are making these unconscious suggestions by small actions, through small actions that overall leads to this belief in each individual that somehow I am belonging to this one gender, and somehow my choices, my interests, my likes and dislikes are in this way, which are going to be different from the other gender. So these kind of things are starting to, I also have a very young daughter, and I have also seen some things that she ends up saying, which I find very surprising, when she says that she likes the pink color, which like I have never tried to buy any clothes for her that are of pink color necessarily, or are very feminine looking, so to say. But it also like becomes really difficult if I'm going to buy some items for my daughter, for example, like buying a school bag or a water bottle. Even those have these gender differences. Like if they will ask, like, is it for a girl or a boy? Like, why a water bottle or a school bag needs to have a difference for a girl and a boy? So these are the like small things that we do every day. These bring these impinge this kind of notion that somehow girls and boys are different in terms of their likes and dislikes. It is true that there are certain generic, or there are certain qualities that can be generalized between girls, that they may like certain things, but that should not be so much so that it leads to a completely different career profession that they end up choosing in their own life, right? And so there are many such incidences where we are always hearing in the house, it is automatically that things that are to be done in a household, it is automatically that it's a girl's job, or a girl should learn, or the fact that she's learning how to make roti or something. Oh, how wonderful. But that's not something that we ever talk about when there's a boy in the picture, right? And so these are these small things that we have to pay attention to, and these are the small things that we have to make sure that we are teaching not only to a girl but also to boy, to remind them that these differences should not be there, and that a boy is no different from a girl, and vice versa. So these are the point, like to be aware as a parent, as a guardian, as a school teacher, whoever authority, to be aware of this fact that, like, even when I listen to some of the teachers giving explaining certain concepts, they will say, you know what, when your mom makes rice at home, or when your mom is cooking in the kitchen, why does it have to be a mom always cooking in the kitchen? So even like these examples, when they're explaining certain concept, the examples that are given are also these stereotypical examples. When your dad is driving a car, or when your dad is repairing something, these kind of examples are used always to explain certain concepts or teach something to the children. And these again, they impinge the same the bias that women and men are different, and they have different necessarily responsibilities or skills. Again, we all are individuals, and we have different skills. We have different likes and dislikes, and there should not be these kind of biases such that overall, if you look at a huge population, then that one gender somehow is given less opportunities, is somehow not given the opportunity to be in a certain field, or not considered to be skilled enough to be chosen to continue to work in that field.
So I'd like to listen to the male perspective of this. So you grew up in a society, and I know you are really proactive against breaking these gender stereotypes from your side as well. So what would you address to the male population or the boys, young boys growing up? How do they get rid of this stereotype and see women equal to them in any field or any career of their choice?
Sure. I mean, I can only speak from my personal experience about what, yeah. So, I mean, it's there. I mean, of course, all of us know, and being a guy, I also know that. So, what I try to do from my personal viewpoint is, first of all, I think it's very hard to identify the biases being a guy. I think that's the first step. It's usually not so easy to identify, but once I identify something, probably the idea is to see if I can do my bit about it. So, for example, when Anuprita was saying, why should only girls cook or boys drive? So, for example, in my house, for example, now I've learned cooking. So I cook as much as probably my wife does. And so those kind of things. And also, as a scientist who also works with many female collaborators and that as brilliant as male collaborators, right? A lot of questions or a lot of opinions that, for example, I would form about a colleague. Sometimes I ask myself, okay, would I have asked the same question if it was a guy, right? So, for example, how we assess somebody as a good scientist or not, or a good, for example, a project student comes and you want to assign a project and you identify, okay, how smart is this person? Will he be capable or not? Or she be capable or not? So sometimes I ask myself this question, would I have the same question or the same opinion if it was the other gender? And surprisingly, I found that I'm biased in many ways. So it takes a lot of effort for a male, or in this case, I'm talking about a male, but in any overprivileged class, I mean, it can be rich versus poor. Asking the question like, would my opinion or my action be same if this information was not given to me? I think that's, one way in which I try to at least contribute in the way I can, and that has been both a challenge to identify that, but it's also very, very enlightening as well. Yeah, that's where.
So adding to Siddharth's point, so as you said, it's difficult to identify. So there are certain things we do, the certain things we say or way we behave. So let's say I'm talking about science with some of my female friends, so some of my colleagues here. So am I cutting them off when they're saying something? That's the first thing. So generally I speak too much, so only Sanjita can shut me up. So that's generally what happens. So it occurs. So sometimes I just shut everybody up, I keep speaking. But as you grow older also, and you start seeing things properly, so you're not kids, right? We are starting to see things from a new lens. And we see that, so if a girl is speaking, so she's generally being, yeah, right, you're correct, but somebody will interject. Why do you want to do that? Like if some guy was speaking, or I am making the same point, this happens to me. So whenever I do science outreach, it occurs all the time. So I tell the girl, like, you do the outreach. I'm just going to stand here because you can speak this thing. You know the demonstration. Just do it. But they start speaking, and then the teacher or anybody in the crowd, they start to interject. Why would you do that? If I am speaking, you're not doing it, right? So, and sometimes some things we don't even realize. So I am very fortunate that I have good friends who tell me, so these are things we generally face, and then I go and reevaluate. So have I done this thing anytime in my as I converse, as I interact with women? So sometimes it's yes, but thankfully it's not. It's a very a minuscule fraction from what my friends tell me. So that's pretty nice, but. One thing I learned was to just observe and not judge. So we generally, when we are interacting with anybody, we tend to just first judge. And then we listen to what they are saying. So we first form an opinion and then some hypothesis. This guy is like this woman is like this. And then you start putting all the data. Let's not do that. Just listen to what they are saying, just observe them, and then you take a call as to what you want to respond to that person. So we slow down. So that is something I've realized it works very well. That I'm able to listen to them and then I make an informed decision. Sometimes I don't want to respond at all because I don't know what to respond. You can be in that situation also. So from a guy's perspective, I think that slows us down and that lets the girl finish or the lady finish what she wants to say. And then we are able to listen and then give a response, which then drives the conversation forward in a very nice manner. It's not just some lame conversation we are having. It's a very deep conversation we have. So that is something I have noticed. Sukanya?
I just can add a few points that I have a elder brother in my home. So when I was little, I never know that I was a girl. So my parents never treat me like a girl or treat my brother like a boy. So outside world, I sometimes get that kind of notion that you should study biology or something. But in the home, I was always said like that you also have to earn for yourself. You have to study as hard as your brother. So I think that things help me. So I never knew that there is a gender bias inside my home. So when I actually interacted to the outside society, I was really surprised. Oh, acha, why should I be different from my brother? So that thing actually helped me. So I have some friends who has faced severe difficulties for being a girl student, but luckily I have not. So I hope that kind of future for every girl in my country or in the world.
I think I agree with all the panel members that stereotypes, if you break them at home, then at least it rises in the minds of the young children when they see something different outside, and they at least have the opportunity to question why is it different and why it should be different. Yes, please.
So I'll add some funny anecdote to this. So there was one survey which identified, so this bias, that societal bias we're talking about is very deep, right? Even I as a woman don't realize when I'm doing a discrimination against a girl. This is extremely deep. So they were trying to find several of these, how deep these are, and they made a survey of the literature that we read as a child. So it's really funny. So we grew up on fairy tales where girls are being saved by princes and things like that, which make us think like, oh, we can't defend for ourselves, we have to wait for somebody to come in. So funnily, there was one panel which actually rewrote these stories from the point of view of a girl being the savior. And it was really funny, the reaction. Even I was shocked to read them, because how deep is our bias about these. They even wrote this Indiana Jones kind of story where the woman is a scientist and goes out in the world. She writes letters to her daughter and she's always away and the father takes care. So how shocking is it for us to listen to something? So I think we have to pay attention really to identify at what point we imbibe these biases, from the very literature we are reading, the stories we are reading, and everything that gives us this picture of the distinction between men and women, right? So yeah.
Thank you for that point. So moving forward, I think we have a couple of more points to discuss, so we'll just push through following. We can discuss this all day. But the second point that has a serious impact is the visibility of role models and mentors for young girls as they grow up. And there are several studies, this is just one of them, that when the young girls get to interact with a future themselves that they're envisioning to be, then it has a really positive effect and builds up, so the implicit biases break. So I'd like to ask the panel members if they've had any role models or if they've acted as role models which has inspired anyone.
Can I suggest something, if it's fine?
Yes.
So maybe we can ask them to name a couple of scientists, famous scientists, like men and women, and how quickly they answer. Can we start from that? I don't know if it's...
We can try.
It's going to take some time. So 3 scientists...
I think we've tried that a couple of times and I've been disappointed, so I didn't want to bring it up this time.
Sure, then we can proceed. That's fine, yeah. Yes, so I sort of wanted to allude to that.
So policies are being made to make role models more visible, especially as things have improved a lot. Women gain more visibility now, and equal visibility, I won't say more visibility, equal visibility as men when they make breakthroughs. But we see all this in the newspaper, but a role model for yourself, someone you have interacted with, a mentor for you, that plays a very crucial role in seeing yourself in the future, how you want to look at yourself in the future. Yes.
I think, sorry, can you hear? I think many of you, I guess many of you must be watching the T20 Women World Cup. I don't know how many of you watched. Now, the matches were, of course, very exciting, and unfortunately, we just lost in an unfortunate way. But the thing is that there was a lack of role models for cricketers, right, in the country. But still, the whole team came up, and then they played wonderfully well. So I think, even though there is a lack of role models, just because by the love for the subject or whatever it is, people can get motivated as long as there is support from surrounding. That people, you always don't hear the negative things. This kind of thing, if you start hearing, then of course you will get demotivated. But I am very sure the parents of those cricketers did provide positive support.
So I've heard from young girls who are in college, because they hear about this work-life balance all the time. But then until they come to see a person who is really handling the work-life balance and seeing how it really is in real life, that makes a lot of difference, because it's your future. It's not something that we've been through. And if you see biases, how you deal with, how have people dealt with it and came through successfully. So that really matters a lot. So have you had any mentors who have helped you, or at least like push through all the barriers in the past?
Okay, I can also add a few things to this. So this is something that is, I have myself seen very often. So exactly like you said, your daughter drew these pictures, right? So this is something because she has seen these images in front of her and had this idea in the head. So myself also, so I remember when I was in master's, so I taught my university, a lot of girls came to me and said, oh, we are very proud to have a woman gold medalist. And I remember from that year on, every year we had a woman topping. So that means that there was this bias that women cannot be heading the university in physics. And then when this happened, so it was like something possible. And then women push through it, right? So we need to have these role models. So I was also an ambassador for science, and also now that I'm doing LIGO India outreach, I see when we showcase women like Mansa and like Anuprita, so there are women who come forward to us, talk to us and say, okay, what are the fields are you studying? I would like to do the same. I would like to be like you. So this definitely helps, because when you have a role model who has surpassed these obstacles and stood up for themselves, that gives courage to women. So we definitely need to portray these. So now, thanks to social media and so on, women can actually identify such role models, and we are also organizing these kind of mentoring sessions and so on, where these young girls can ask questions on how to overcome these kind of obstacles that they face. So I think this is something I have definitely seen for myself is very important. Yeah, so.
So next is the role of family and society. So usually for a woman to succeed, she needs a support system. Even for a man to say, I don't think anybody can do it by themselves. You need a support system. And the support system for a woman is very different from the support system for a man. And usually the woman has to either become a superwoman, try to do everything all by herself, or she has to fight against gender biases within the family itself, or she has to make personal compromises. oh, I should probably leave this, let this be, and then move forward. So these are the three choices that she usually has. And as Sukanya mentioned, her family has never seen a bias inside, she's never seen a bias inside the family, and they've been a very strong support system. And I think moving forward also, it is important that the pressure on the woman to maintain the work-life balance doesn't rest only on her, but the support system helps it. And I'd like to ask the panel members, how can the support system help a woman get through this instead of her being forced to become a superwoman or forced to fight her own war all by herself?
Maybe I can just talk about one change that I'm seeing in over the last few years of being in this field. When I was a PhD student and I was attending conferences and going here and there, at that time I did not have my own family or a child and so on. And those are the times when people were still talking about these issues, and there was not as much awareness about these issues. And at the time I had not seen, during that period I had not seen that many conferences, for example, where there would be support for like child support, like to enable families where the husband and the wife both are scientists and they have a child, to have some facility to take care of the child, so that both the husband and wife can attend the conference, can give talks, can be engaged in scientific discussions and so on. But over the last few years I am seeing this awareness being there more and more, not just globally but also it is starting in India. I am seeing that there are certain conferences where they do make such facilities available. There is some support to take care of the child. There is also some sort of funding available at times to allow for families to travel and to make sure that women don't have to compromise in these kind of situations, and that they can also contribute, be there and make themselves visible and engage in scientific discussions and so on, without having to worry about this other aspect, which should not have been only the woman's responsibility in the first place.
So I'll probably ask a question to the women panelists here. So what sort of support would you expect, like from your parents, from your spouse, from your extended family, let's say? What sort of things make your life easy? Is it some things that maybe we do to make your life difficult, so you can tell that, and things that you would expect that, if these things are there's somebody to take care or somebody to share the burden, it makes it very easy for you. So could we have some examples from you? It's like Anuprita ma'am gave an example, so some other examples from you people.
So I'll give my own example. So when I moved to India, we had a very small baby. My parents were there with me for 5 months to take care of the baby and get back to the job. And then 5 months later, I don't want to trouble my parents. They have with small children. So I called my spouse back. I told him to quit his job. He quit his job. I didn't tell him to quit his job. He quit his job. And then he came back and he was taking care of the baby at home while I went for work. He didn't have a job. And this seemed startling to the entire population. Like whoever came across this, everybody was startled, telling, you quit your job and came back to take care of a kid at home. And I think that's the wrong sort of impression that the society gives to the male gender. The child is equally his and mine, right? And the society looking at it differently makes you feel that you've done something wrong. And that should not be imposed on women, that they've done something wrong. Should not be made to feel the guilt of having the father at home. That sort of a thing happened multiple times, multiple encounters that had happened. And it's equally, so we had decided whoever gets the job first goes first and the other comes over. So if he had come over and then I had quit a job, nobody would have asked a question. Nobody would have turned their heads behind and see anything surprising. It would have been the norm. But why was it abnormal to see it the other way around? And that sort of vision has to change.
Okay, so I get this question very often. So whenever I say, okay, I am a professor and so I have these achievements, so immediately I get the question, so are you married? How many children do you have? So it doesn't matter how many publications, how many awards I have, but very funnily, when we talk about women scientists in India and what women have achieved in India, then how many women do we quote? So nobody is asking those kind of questions, like how many women, I mean, all women are not born to be child bearers. There are also women who have to take the country forward. I mean, why do we put these things in the head of children or in a question a woman who is trying to achieve something in science? These are two separate things. A personal life and an academic life is very different, right? So, I mean, I would say this is also a very, very...
And interestingly, nobody asked me this question ever, that are you married and how many children you have. So that I think is quite understandable. There is a difference in the society about this. But in general, I just wanted to add... Yes, go ahead. Can somebody bring the mic? Yeah. Concentration, yeah. I will just say one thing. It is also not just boys and girls. Just one thing. I just want to mention one thing. So since we are only discussing about girls, it is not just about girls and boys. To me, what feels the most important thing is freedom. As soon as you get freedom, then you can, and the support accordingly. You know, only freedom does not mean that you will be able to achieve something. This problem is there also for boys, because family expects something from the boys and they are pushed in that direction. Similarly, family expects something from the girls and they are pushed in that direction. This freedom is lacking for both men and women, and I think freedom and corresponding support is what actually is necessary. Yeah, sorry. Please go ahead.
मला तुम्ही जेवढं इंग्लिश बोललं मला तेवढं फार कळत नाही, पण जेवढं तुम्ही बोललं मला एवढं कळालं की मुलींनी वगैरे गर्ल्स सायन्स घेऊ शकतात आणि त्याचं खूप उपयोगी पण होतं. पण जिथं मी वस्तीमध्ये राहते मला हा शिक्षण एवढं पडत नाही. म्हणजे मी जिथं वस्तीमध्ये राहते आम्हाला शिक्षण हा अवघड पडतो. मग तुम्ही जे बोलला तुम्ही मला शिक्षण जेवढं तुम्ही इंग्लिश फार बोलला मला खूप कळालं. मग तुम्ही येऊ शकता का मग आमच्या इथं वस्तीमध्ये आम्हाला शिकवायला?
I'll explain. She is my student. We are from the NGO which is working for the street kids and underprivileged. The kids who are, sorry. The kids who are beggars on the streets or those stay in a tribal area or an underprivileged area. So she thinks कि हमारे यहाँ पर स्कूल सीखना ही बहुत डिफ़िकल्ट है और साइंस कहाँ से लेंगे हम. और अगर आप जैसे मतलब प्रोफेसर्स इनको पढ़ाने वहाँ पर आते हैं, सो शी थिंक्स कि वो आगे बढ़ पाएगी. बिकॉज जहाँ पर ये रहते हैं वहाँ पर ये खुद ही कुछ ऐसी चीज़ें हर रोज़ करते हैं जिससे साइंस पता चलता है. सो उसको ऐसे लगता है कि आप वहाँ पर उनको पढ़ाने के लिए आना चाहिए. थैंक यू.
This is a really nice question, and I would like to tell that we have a small science center here at IUCAA, and we always get these questions and we actually go to such centers. मी मराठीत बोलते तुझ्यासाठी की आपल्याकडे एक छोटं सायन्स सेंटर आहे आयुकामध्ये. बाहेर जे पोस्टर्स लावलेली आहेत त्याच्यावर आपला ईमेल ID पण लिहिलेला आहे. तर त्याच्यावर तुम्ही ईमेल करू शकता किंवा आत्ता जितके व्हॉलेंटियर्स आहेत त्यांना भेटून तुमच्या शाळेचं किंवा संस्थेचं नाव लिहून देऊ शकता. आम्ही नक्की तुमच्याकडे येऊ, कारण आम्ही अंडरप्रिव्हिलेज्ड ठिकाणांमध्ये, आंबेगाव तालुक्यामध्ये, रुरल रिजन्समध्ये सुद्धा जाण्यासाठी वेगळी टीम डेडिकेटेडली आयुकाची आहे. सो आम्ही तुमच्याकडे नक्की येऊ आणि यातल्याच कोणाला तरी एकाला तुमच्याकडे नक्की घेऊन येऊ शकू. थँक्यू.
So this was my last slide. So you see, whatever you see here, self-confidence, curiosity, creativity, patience, persistence. These are the traits of a scientist. These are not male qualities, these are not female qualities. So what's inside you, what's in your brain is not very different. So you can see yourself as a scientist. Nobody stops you. So we'll take questions from the audience. Yeah, you can make your comments. This is our first panel discussion, so we would like to hear your feedback as well, if it was useful for you.
Hello. As you said that there should not any kind of school bags for girls and school bags for boys. So there should not be any type of difference. But in the school there are separate uniform for girls and separate uniform for boys. So should it or how it?
Clothes are for comfort.
Yeah, but isn't it making gender difference?
I mean, I cannot speak for everyone whether, and if I give one answer, suddenly everything is not going to change. But I can give you my opinion. For example, they have, if you see, for the sports days, what do? They choose shirt pant for girls as well. So what is the purpose of choosing a skirt for the other days? What are we trying to achieve by showing that this is a girl and this is a boy? I personally don't understand the difference. I don't see why there is need to be a skirt for a girl. What it serves, I don't know. So I would have just chosen the same uniform. If I were a school principal and I had this thing, I would have chosen the same uniform for everyone.
So this is something my sister faced. So when she was in school, she had to travel some distance and go to school and come back. So it was really problematic to cycle, for example, while wearing a skirt. She would be like, I would rather wear a pant and then, a pant and shirt. It's so comfortable. You can just travel. It's perfect. But for whatever reason the school wanted, and that's a problem. That's absolutely.
That's the reason why we bring it forward, because the support system, the teachers understand the children better. They see them day in and day out. Are they comfortable sitting in the classroom? Are they comfortable doing things equally, whether they are a girl or a boy? And that's what we would like to address.
I think that the point here is that, people should have freedom to wear whatever they want. School uniform is maybe not a concept which I like, but on the other hand, this is there. But on the other hand, you may also like a situation where there is no uniform and people just want whatever they are comfortable with. That may be a better model, and maybe we will reach there at some point. The thing is not just about the dress, right? I mean, it is the colors, etc. do stereotype, that is true. And I can say that we gave a pink cycle to my son, and then he was worried that his friends are going to tease, but nothing happens. After some time, it all becomes fine. But on the other hand, the point, I think, the thing is much deeper. It is not that if you use the same uniform, this difference is going to go away. Because, in fact, a uniform is probably the easiest change to make. But the expectations of that children are more important than science. It may be, but it may not be for somebody. This part is very, very difficult to change. It is the person, the person who is involved, concerned, should decide what is better for me. Of course, I may love children, but I may love science more, and that is absolutely fine. But this, I am sure in this auditorium also there will be a large number of people who would find it very difficult to believe. And this is where the problem comes. This we have to change.
Anybody has any? Yeah.
Hello, so I'm not very good with names, so I've kind of forgotten everyone's names. And my question isn't directly related to this topic, but the ma'am in the pink said that she works something regarding LEGO, so I was wondering if you could tell us more about that.
LIGO, right?
Yes.
Yes. So we have a stand just outside in Bhaskara, and we have plenty of people to explain everything about LIGO. The people on stage, we are like 1, 2, 3, 4 of us are from LIGO.
Yeah, you can visit the LIGO India stand, which is just outside Bhaskara. So yeah,
we are very much pro-women, you see.
Yeah, please visit the stand. Yeah.
So there's no discrimination. And the pictures that you see here, these are from our own labs here in IUCAA. So we have students working with us, and you can see we are not biased. So everyone is welcome to come and equally enjoy science.
And they are standing there.
Yeah, they are there at the yeah, they are poster girls. They are there.
There is a
I think girls would teach the self-defense. Because girls had to do up and down sometimes.
Everyone should know self-defense these days. Yes.
मेरा क्वेश्चन ये है कि मैं जब कुछ लोगों को बताती हूँ कि मुझे साइंस में जाना है, मुझे डॉक्टर बनना है, तो वो कहते हैं डॉक्टर ही क्यों बनना है? इसका आंसर
डॉक्टर बनना है, so it's yours, your choice. And everybody around you, their duty is to support you, but the choice is always yours.
But you should still ask the question that why I want to become, or do I really want to become? That is a valid question, but you should make the decision.
Yes, ma'am.
Hello everyone. First of all, our school is in a rural place, that is Paur Murshi side, and usually what happens, we are trying to make science interesting through experiments and different activities, but usually what happens, at a certain level the students are taking interest, but at a particular level it might be the family background that they are coming from, and they stop doing that. So as a teacher, how we can motivate them in order to get interest in that particular subject? Now as per science has been increasing day by day, because during our time it was not there, but these students are getting very much interest in that particular subject. So how we can support them? Now as we are finding you all over here, we are thinking like our family members should also have supported us to be in this particular stage which we had not got. So how we can give them this particular stage?
Sanjit or Devara?
No, I think one way to motivate, even irrespective of the family background, is to tell the students to think everything they are doing, what science is involved. So like whatever they are doing at a given point, if suppose say family member said that, okay, you do this, okay, there will be some science involved in that part. Like when they are taking water, when they are like, like let's say everyone uses some kind of water pump. I can give one example. So they are how to take water, how to carry it easily. Every part has very interesting science involved. So that is one way to sort of forget about how my family is supporting or not supporting, whatever it is. But I am trying to, my mind is focused in the science part in each step I have to do. So that way, then of course this is not the ideal solution, but that way you can at least keep motivated.
So this year for a model making competition, our theme was science from your kitchen. So we made both the boys and the girls enter the kitchen for once. So I think teachers can motivate them to go. So I think teachers are really important, and more than the family, it's the teachers who can motivate the children to pursue what they want to do.
I will just add one more point. So when I was in school, so some of me and my friends were very keen to asking question, but unfortunately some of them were not encouraged that you should not ask that kind of question. I mean, not that kind of question, that so many questions about this. So I think what we really wanted, that teachers encourage us to ask more and more question. To some, even if the questions are very naive, they are not probably related to our syllabus, but asking questions and trying to find the answer by myself is the biggest motivation for joining science for me. So.
We'll take a last point from Siddharth.
Yeah, I mean, how I can talk for myself. I was not interested in science for a long time, right? I wanted to do history or something. But it also helped me because my family was okay with me not doing something particular. I think what I also find is especially with this, when I talk to my cousins, it's already decided like you have to get 95% and all. So that kind of limits what they can do, what they cannot do, right? It's very important to give children, also younger people, to freedom to do what they want and fail also. Yeah. At one point in my life, it was pretty sure that I was not going to do anything in my life, and my parents still supported me. I think that is also important. The ability, the freedom to do what I want and fail as well. And that's something that we really lack in our system, I think.
Thank you. We'll wrap up the panel discussion for today. We have the next session, which is much more interesting, Mythbusters. So we'll prepare the stage for that. Thank you, everyone. Thank you, panel members.
Okay, so we are going to have a session starting in 5 minutes or 2 minutes. So how many times have you had some questions in your mind which you wanted to ask scientists? This is the great day. You've come to IUCAA. There are several astronomers, astrophysicists in the campus who you can talk with, ask questions. But then there's another place people try to find answers, and that's on WhatsApp. The WhatsApp University, there are so many forwards coming all the time to you, and you think, wow, I mean, this should be the best encyclopedia. But then sometimes there's no source and backup to whatever information you get there. And that's one of the fastest way of spreading rumors. So I'm so happy that governments have some limitations on spreading to counter spreading of rumors. But then there are some myths which are also going around, myths in science, myths about astronomy. So those myths do not get usually answered because you cannot just talk to some social scientist or psychologist or doctor as easily. So today we have with us a team of Astro Mythbusters, and they are here to point out to you some of the things which you may have thought it's true, or you may know that it's not correct, but you didn't know the reason behind it. So a few of the selected myths will be presented by our team here, and we hope that this Mythbusters team, which is starting today, will be able to bust a few more myths over the coming time. But it's a great start today. So please welcome on stage to start with Shivraj Kandaswamy and the Astro Mythbusters.
Hi everyone. Can you hear me okay? Hi everyone. I hope you are enjoying the Science Day activities here at IUCAA. So this session we are going to look at some of the myths and misconceptions in astronomy. Some of these myths you might have heard before. Okay. Some of these myths or misconceptions you might have heard it before, but anyway we are going to go through them, and we hope that in that way you will learn something new. So myself, Shivaraj, a scientist here. So myself and Shaurabh and Apratim, our colleagues here, will also go through these myths. So we will start with this one, eclipses are bad. I think most of you probably already heard about it. At least in old days, people used to think that the times of eclipses are bad or something bad happens during that time. So in many cultures around the world, not just in India, people used to think that both solar and lunar eclipses are bad things. It's mostly because the things suddenly changes during that eclipses. For example, the light reduces and the temperature decreases. So these sudden changes that we can't control, when we see them, we get afraid. So it is natural that people develop some theories that something bad is happening. So in ancient times, people used to think that these eclipses are related to some like mythical creatures, some animals eating the sun or moon, and depending on the part of the world, it could be like a dog, wolf, dragon, frog, bear, snakes, demon. So there are many different animals. They also thought that, since people know that the eclipse doesn't last long, they know that these animals capture this sun or moon and they leave after some time. But from our astronomical observations, now we know why these eclipses are happening, and you probably know how these things before. But I'm just, for the sake of completeness, I'm showing this. So, hello. Okay, so hope you can hear me okay. So now the eclipse, solar eclipse happens because the moon comes in between the sun and the earth. The moon revolves around the earth in an elliptical orbit, not a circular orbit. Because of that, the distance between the moon and earth changes over time. And due to that, whenever an eclipse happens, depending on the relative position between the moon and earth, the eclipse can have different properties. It could be a complete, like total eclipse, as you see here at the top. Or it could be an annular eclipse. That means the moon was not able to completely cover the sun, so you have a surrounding ring that you can see. Or it could be a partial eclipse where you see some part of the sun but not the other part. In the lunar eclipse, what happens is that the earth comes between the sun and the moon. And here also you can have different scenarios depending on what is the relative positions. One interesting thing that happens here is that even if the moon is completely in the shadow of the earth, sometimes the moon can have colors, like usually red and orange. This is because of the atmosphere, the effect of the atmosphere on earth that refracts the high wavelength light, basically orange and red, and they pass it to the moon. And usually we call that as a blood moon. So what are the myths that we generally associate with these eclipses? One is that during the solar eclipses, we say that there are more harmful radiations are produced than usual. But this is not quite true. Sun emits intense visible light and also invisible UV and infrared lights all the time. You've probably seen across in our main building about the Aditya 1 mission, which is going to study the sun. So it's going to look at these different wavelengths that sun is emitting. So looking at the sun at any time, not just during the eclipse, is bad for eyes, even for like a few seconds. So there is nothing special about the times of the eclipse. On the contrary, if there is total eclipse, people suggest that you can in principle see the sun with naked eyes. But the problem is that even the small time before or after the eclipse, where even a small part of the sun is visible, that can damage our eyes. So because of that, it is better to use special lenses, special glasses, or use some other methods to look at the sun. The other myths are like people say that there is harmful radiation that comes during the eclipse that can affect the food, children, pregnant women, and all such. This is basically comes from the previous fact that there are additional radiations are produced. But what just happens is that just as moon blocks the sun, so there is nothing additionally produced. So the same radiation exists even before when there was no eclipse. So we don't expect that there is a change in the effect. And the third thing is people say that bad things happens during the eclipse. Usually this is attributed to like a psychological effect called confirmational bias, where we tend to remember things that when bad things happens during the eclipse, but we forget things that are good or something normal that happens during the eclipse. This is confirmational. Because of this confirmation bias, people tend to believe that whenever there is an eclipse, something bad happens. So this is not quite true. So that means it is very safe to come out during the eclipse and actually even look at it, because we are looking at the solar system in action. Usually we just look at some sun going around, but here two different objects interact. That is how the solar system works. So we are able to experience that thing during the eclipse. So we should be able to like come and experience this. And also because of the relative orbital plane of the moon and between Earth and Earth between sun, these eclipses doesn't happen that often. At least it's not visible from the place where we are staying. For example, the last solar eclipse happened in 2022, and the next solar eclipse will happen in 2027, the partial solar eclipse. The complete solar eclipse will take another few decades. That means they don't happen that often, at least if you are staying in Pune and if you're not traveling somewhere else. So when that happens, that means you should go and experience it. It's once in a lifetime or once in like a decade experience. IUCAA organizes many events during these eclipses times, so you can come and visit here. We have like a special setup that you can look at these things a bit better. So you should be able to participate. So here I am showing a picture of the eclipse that happens on Mars. This was captured by one of the rovers NASA sent out, and you can see because of the moon size of the moon Mars has is much smaller, so it doesn't cover the full sun, and you can see that the rock shape in front of the sun. So all other planets also has this eclipse. So we don't have to worry about what happens during the eclipse. There is nothing special happens during the eclipse. The second myth that I'm going to talk about is navigating through the asteroid belt is hard. How many of you know about asteroid belt? Can you raise your hand? Okay, yeah, quite a good number. So what is the asteroid belt? Asteroid belt is like a collection of small rocks that are revolving around the sun. They are situated between Mars and Jupiter, and their radius is like 2.2 astronomical unit, between 2.2 and to 3.2. So astronomical unit is the distance between the Earth and sun. So we believe that these are like a rocky remnant that are left over from the initial formation days of the solar system. I think there was some discussion during the Ask a Scientist question, formation of the solar system. So we believe that during the earlier formation time, these small rocky remnants formed, but because of the mass of the Jupiter, they were not able to convert into a bigger planet. So they remained as a small rocks, and they are now revolving around the sun at that orbit. They vary in sizes. They go from micrometer to like thousands of kilometers. And the picture on the right side actually showing the number of the such rocks versus their size. We know we have some measurement, but the other regions we are just extrapolated based on our experience. And you can see that if you go at higher sizes, the number of rocks reduces significantly. The largest rock that we see is probably like 1 kilometer, 1,000 kilometers, which is called the Ceres. So we estimate that there is probably around like 1 to 2 million asteroids with a size greater than 1 kilometer. And some of them even have small moons, not just one. Some of them even have 2 moons. Because of this large number of asteroids, we would generally think that it would be difficult to get through this asteroid belt. So for example, if I want to go to Jupiter or other planet, then it will be difficult because we have to cross the asteroid belt. So this is in many movies you would see this scene. This is from the Star Wars, one of the science fiction series. Maybe, okay.
Sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell me the odds.
Okay. Okay.
Sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell me the odds.
So this is a scene in the Star Wars, the fiction movie, if a fiction series. So there, this on right tells the pilots that the possibility of successfully navigating the asteroid field is around like approximately 3,000 to 1. That means it's very, very difficult to travel through this asteroid. But the hero says that I can do it. Hero always can do that. But the point is that here the estimate that they quote in the movies is very, very small. That means it's very difficult to traverse through. So when the first spacecraft, the Pioneer 10, that flew past this asteroid belt and was traveling to the farthest planet, and even the scientists at the time thought that maybe there might be some collision will happen with the asteroid, one of the asteroids in the asteroid belt. But after that, it successfully flew past the asteroid belt, and after that there are many spacecraft that have flew past this asteroid belt, Pioneer 11, Voyagers 1 and 2, which you might have heard before. So that means that the probability of collision is much smaller than what we usually think. Currently the odds of this collision is less than 1 in a billion. So we can probably get this number from an order of envelope, the back of envelope calculations. The area of the asteroid belt is like 10 to the power 23 meters square. We know that the size it covers in the solar system, so it turns out 10 to the power 23 meters square. And if you assume that the 1 meter size asteroids in that asteroid belts are like 100 trillion, then you just have to divide these two numbers to get the possibility of hitting one of the asteroid, and it turns out that it will be probably order of 1 in billion. So it's much smaller, so we don't have to worry about hitting one of the asteroids when our spacecraft go through this asteroid belt. And these asteroids are expected to be, since we said that these were formed during the initial days of the solar system, though they expected to have information about how the solar system formed. So people do send, NASA has sent many satellites to study these asteroids. Specifically, one of the spacecraft they sent to study these two of the asteroids from the asteroid belt, the largest asteroids, Vesta and Ceres. The Dawn spacecraft went there and it studied the two asteroids in 2011 and 2015. The Dawn spacecraft still revolving around this Ceres asteroid since then. And they are also planning to, they have already sent another spacecraft, Lucy, which is also going to study these asteroids, and the launch was in October 2021, and it's going to reach one of the asteroids in the asteroid belt in November 2023, so you might hear about this in late this year, so you would know what's happening there. I think these are the two myths that I wanted to cover, and I asked Saurabh to go through the other ones.
Hello everyone. Hello everyone. Can you hear me? Yeah. Okay. So my name is Saurabh, and I'm a research scholar at IUCAA. And as you can see from the screen, I'm here to bust some of your myths. Okay. And so I personally think that myths arise when you have a very superficial understanding of a phenomena. But if you dig a bit deeper into that phenomena and try to understand it more, you will see that if it is a myth or not. And by proceeding that way, we will bust some of the myths. Okay. So one myth is that X-rays and gamma rays or gravitational waves from space will affect us. Now all of you know that if you have an excess dose of X-ray or gamma rays, then it can cause cancer. And there are various astrophysical scenarios where the source actually emits X-rays and gamma rays. As you can see from that diagram, we have a black hole and it is eating up the matter. So when the matter is going around the black hole very close to it, it emits X-rays. So now we have a source which is at X-rays, and it is bombarding X-rays all the time. So are those X-rays harmful to us because they are bombarding all the time? So at surface we see that we are always bombarded by X-rays and all. So if it is true that such these X-rays are affecting us and like are causing a cancer in our bodies, okay. So first let's take an example of a star. Okay, so this is a star. Okay, now the star emits light in all directions, right? And so when the light travels out, light travels from the star, it say reaches a certain say a length, and it carries energy with it. Okay, so as you can see, light has traveled some distance and it has carried energy from the star. Okay, and what happens is that this energy is basically distributed over the entire surface of this star, of this area, as you can see highlighted in the blues. Now what we do is we put an observer at that point. Okay, so we put an observer at that point and we find that the intensity of light is 100 watts. Okay, then after a while the light will travel some extra distance, and this time again the area at which the energy is distributed by the star is actually greater than the area which is it was earlier. Okay, so at that point we put another observer and we find that the intensity of that light at that point was 75 watts. Now we do it another time. So, okay, so light travels even more distance from the star, and again the energy from that from this star is actually distributed over the much bigger circle than the earlier two. And we put another observer here and we find that the intensity was around 40 watts. So all in all is that the further we are from a source, okay, the light becomes less intense. Okay, that's because the energy of that source is energy from that source is basically spreaded out over the entire surface. So this is what I said is with an example of light, which is a visible light that we see. But X-rays and gamma rays are just basically electromagnetic radiation. It's just a part of light which we cannot see. Okay, so these are the part of light which you can hear through this device called radio, which are radio waves. This is the part in between called visible, which we can see with our eyes. And this is the frequency at which X-rays and gamma rays operate. Okay, so what I've said here for light is also true for X-rays and gamma rays. Okay. So if we do say a rough calculation and say figure out what is the nearest source of X-rays to us, it turns out that the nearest source is this Milky Way galaxy, and this is the image of Milky Way galaxy in X-rays. If we look at through X-rays, this is what we will see. Now if we do some small calculation at what is the intensity of X-rays that we see from Milky Way as compared to a normal X-ray that we get in the hospital, so it turns out that the intensity of X-rays from Andromeda galaxy is 1,000,000 times smaller than the single X-ray of a chest. So the amount of intensity of radiation that we get from this physical sources is way less as compared to what we are exposed in day-to-day life. Okay, so we have busted one myth today. Okay, so again, earlier we have a superficial understanding of that particular topic, but once we dig up a bit deeper, we can actually bust that myth. So another myth is that the Hubble and other space telescope see the universe as we see it with our eyes. So these two images are from the Hubble telescope. So one of the common question is that are these images like the telescope sees exactly these images as they are presented right here? So we will take a look at it. Okay, so the first thing is to understand like what is a color image. Okay, so the color image is basically made of 3 bands. Okay, there is an R band, there is a G band, and there is an blue band. Okay, B band. Now when you basically stack these channels, the R band, G band and B band together, we will get a color image of something. Okay. Now various telescopes, even like the space-based telescopes or land telescopes, they operate at different wavelengths or different frequencies. Okay, and they are usually collecting light from different bands, and by basically combining the information for like combining the image of different bands, we basically create a composite image which we see as a color image. Okay, so this is an example. So this is the JWST image. This is just a single image, but captured in different color bands. Okay. So what we'll do is we will make a color image from the real data of Hubble Space Telescope. Okay. So this is how the real data of color of Hubble Space Telescope looks like. Okay, these are the 3 images, and these data is collected from 3 different bands. Okay. Now what we will do is we put this data in different bands. So we know it is R band, it is G band, and it is B band. Okay. Now what we do is basically combine these images together. So we put this R band first, then G band in between, then the B band at back, and we stack them on top of each other. And finally, here we get the final color image. Okay, this is looks much more beautiful and colorful than these individual images, but it is basically made from combining all the different images from 3 different bands. Okay, so I have one question to the audience. So can you guess what this image is called? This is a very famous image. Yeah, you are correct. It's called Pillars of Creation. Okay. So we have busted another myth, right? So this is not how the images of this is not how the exact image of a Hubble Space Telescope it looks like. We actually make them by combining different bands of the telescope. Okay. Thank you.
Hello. Thank you. Hello everyone. Can you hear me properly at the back? Okay, great. So Saurabh, so I'm Apratim, I'm also a scientist here, and Saurabh started by saying that myths come up because of superficial understanding. This is a myth which comes out of sheer belief or disbelief of something. So that's another reason, I think, for a myth. So fortunately, I was not aware of this myth for a really long time, and I'm really curious how many of you are aware of this myth. When I went abroad for my PhD, and let's say for this audience, I went to have coffee, and I met a few people, and they got to know that we are doing our PhD in astrophysics, and they started asking this question, and I got to know that there is a group of this flat earthers, as they call themselves, and they have a regular conference about this. Okay, so what they really believe in? They believe in the fact that, and I'm guessing most of you believe in that Earth is spherical or oblate. They don't believe in that. Okay, and what they believe is the North Pole is basically at the center, and then you have the continents and the land masses and the water bodies till you reach the edge, which has some sort of a ice wall or a barrier, and nobody knows what's on the other side of that. Now, the other thing is, what they claim is that the horizon that we see appears flat, and gravity is just an illusion. So it's not like the gravity is pulling us down. It's the fact that this disk is going up, and that's why we are not flying away. Okay? So let's, if you meet someone like that, what you have to say is, in the 1970s, we already have this picture of our globe taken by Apollo 11, which is taken from around 29,000 kilometers away from the Earth, which shows that Earth is more or less spherical. That's one of the reason. But I have tried this, and they've said this picture is fake. So let's move on. we actually know about this from a really long time. So from the 3rd century BC, say Pythagoras had already told about this, and this was followed by other philosophers called Aristotle and Eratosthenes. So what Eratosthenes did is, what he did is he tried to see the shadows at the same point of time in Alexandria and Cyrene, which are around 800 kilometers apart. At the same point of time, what kind of angles the shadows are making. And from that, you can find out what should be the circumference of Earth. So that's why we already knew about this from a really long time. The third is obviously gravity, okay? And so if you know about Newton's law, you know that the force between two objects is proportional to the mass of the objects and inversely proportional to the distance squared. And so if it was a flat Earth, the gravity should have been uniform everywhere. But what we find is, because the shape of the Earth is not exactly spherical but oblate, so this pull at the poles are much more than at the equator. So I think these are some of the reasons why we can believe that Earth is not like a pizza. Okay, so the other is about tides, and I was looking at the Wikipedia description of tides. Sorry. Let me read that. Tides are the rise and fall of sea levels caused by the combined effects of the gravitational forces exerted by the moon, and are also caused by the Earth and moon orbiting one another. And this is the myth that I want to break here, and this is why we should stop believing Wikipedia. So some of these myths that I've pointed out here are that tides are caused due to gravity, and tides are caused only by moon and not by the sun, as Wikipedia says. And also tides affect human body, and so you must have heard, like, during high tide, people tell you not to eat something, or it might create some problem in your body. Okay, so the thing is, if tides are created due to gravity, the force of gravity, and we learned what force of gravity is a couple of slides back. So the sun, which is much heavier, should, and which is, it's true that it's further away, but if we calculate the force due to the sun on Earth, it's around 178 times more than the force exerted by the moon on Earth. So the tides should have been created by the sun more and not the moon, right? So that's really not the case. So tides are caused by both the moon and the sun, and which is shown in this picture, but I will come back to this picture later. But what it says is, when the sun and the moon is aligned, the high tides are higher and the low tides are lower. So these are called the spring tides, and this has nothing to do with the season spring, but this has to do with the verb spring, so it springs more. And the other case is when it's at an angle of 90 degrees, the sun and the moon. The tides are, the high tides are not very high, are lower than the normal. And these are called the neap tides. Okay, so, but the most important thing is, it's not the force of gravity, but the difference in the force of gravity, or the gradient in the force of gravity at the different points of, say, an ocean, that creates the tides. Okay, so and this gradient goes as it's not inversely proportional to r squared, but r cubed, and that's why if you calculate, you will find that this gradient, or this gradient of this gravitational pull, is more for moon, around twice than that for the sun. So say if the moon was around 2 times more distant than what it is currently, then the pull due to this gradient due to the sun would have been more than that of the moon. Okay, and I'll come back to this slide again. So, this particular plot, what it shows is this tides over a month, and you can see that this top here are basically your high tides, which happen, say, twice a day, and the low tides happen twice a day. But this is the profile over a month, which shows that this is the time when you have this kind of an effect, or the spring tides, and this is the time when you have this kind of effect, which are the neap tides. Okay? Okay, let's see. I don't know who has put this, so I will let you guys bust this myth, and this is a good time to end this session. Thank you, and I hope you will look for other myths which you can bust in the future. Thank you.
Okay. Audience, now we will have Reasons for Seasons show. In another 5 minutes, we'll start. So please maintain your seat.
ये चश्मे पहने वाले
नहीं.
हेलो एवरीवन, हमारे इस सेशन में आप सबको सुस्वागतम। ये सेशन हम हिंदी में करेंगे। तो इस सेशन में हम बात करेंगे सीज़न का पीछे क्या क्या कारण है उसके बारे में। तो ये प्रेजेंटेशन हो रहा है ऑफिस ऑफ एस्ट्रोनॉमी फॉर एजुकेशन की टीम के तरफ से। ये एक नया खुला है, इंटरनेशनल एस्ट्रोनॉमी यूनियन बोल के एक संस्था है, जो एक आंतरजातिक संस्था है जिसमें सारे प्रोफेशनल एस्ट्रोनॉमर्स मेंबर होते हैं। तो ये संस्था एजुकेशन पर भी काम करते हैं और अभी एक साल पहले ही उन्होंने कुछ ऑफिसेस खोले हैं और इन ऑफिसेस में बहुत सारे कंट्रीज़ में हैं। तो इंडिया का ऑफिस, मेन ऑफिस इज़ होस्टेड हियर इन IUCAA। तो हमारा इस ऑफिस का मकसद ये है कि हम ज्योतिर्विद्या को व्यवहार करके शिक्षा व्यवस्था को और भी थोड़ा अच्छा करें। तो हम एस्ट्रोनॉमी को कैसे करिकुलम में और भी लाया जाए, कैसे उससे साइंस एजुकेशन और भी बेहतर बनाया जाए, इस पर हम रिसर्च करते हैं। तो आप सबको ये सेशन अच्छा लगे, यही हमारी इच्छा है। ये सेशन प्रेजेंट करेंगे तिशांत एक स्टूडेंट है फिजिक्स का, वो फर्गूसन कॉलेज में है और यहाँ पे आज वॉलंटियर कर रहा है। तो वेलकम तिशांत। एंड उनको सहयोगिता करेंगे मैं हूँ मूपिया माझी, मैं हूँ यहाँ पे एक पोस्ट डॉक्टरल रिसर्चर, और भी सहयोगिता करेंगे दुष्वंत जो है एक मास्टर स्टूडेंट फर्गूसन कॉलेज से। शुरू करते हैं।
हेलो। हम सब साल में विभिन्न प्रकार के मौसम एक्सपीरियंस करते हैं। ये सीजन्स हमारी डे टू डे लाइफ में काफ़ी इन्फ्लुएंस डालते हैं। इवन अगर हम प्रकृति को देखें तो प्रकृति भी मौसम के हिसाब से अपने रंग भी बदलती है। तो हम सबके मन में कभी ना कभी सवाल आया होगा कि सीज़न के चेंज होने का कारण क्या होता है। तो अगर हम सबसे पहले सीज़न के चेंज होने के कारण जानने से पहले हम देख लेते हैं कि हमें साल में कितने कितने प्रकार के सीज़न देखने को मिलते हैं। शुरू करते हैं समर सीज़न से। हम गर्मियों के सीज़न इंडिया में जून जुलाई के महीने में एक्सपीरियंस करते हैं सबसे ज़्यादा। तो जून जुलाई के महीने में अगर दोपहर में तो बाहर निकलना भी मुश्किल हो जाता है और अगर सूर्य की रोशनी तो बहुत ही तीव्र एकदम गर्म महसूस होती है। और समर सीज़न के बाद ऑटम सीज़न आता है जिसे पतझड़ का मौसम भी बोलते हैं। पतझड़ के मौसम में हम देखते हैं कि पत्तों का रंग भी फीका होने लग जाता है और पेड़ से झड़ने लग जाते हैं। फिर पतझड़ के बाद हमारे पास विंटर सीज़न आता है। विंटर सीज़न में कई जगहों पे हम स्नोफॉल भी एक्सपीरियंस करते हैं और कुछ प्लेसेस में तो टेम्परेचर 0 डिग्री से भी नीचे चले जाता है। अब विंटर सीज़न से टेम्परेचर धीरे धीरे इंक्रीज़ होता है तो हमें स्प्रिंग सीज़न मिलता है। स्प्रिंग सीज़न में हम देखते हैं कि पेड़ पौधे फिर से हरे भरे होने लग गए हैं और जो फूल हैं वो फिर से खिलने लग गए। और स्प्रिंग सीज़न के बाद फिर से समर सीज़न आता है। सो अगर हम इस साइकिल को देखें, ये लगातार हर साल हमें इसी प्रकार की देखने को मिलती है। हमारे सबके मन में ये क्वेश्चन कभी ना कभी आया होगा कि साइकिल बिल्कुल इसी पाथ को ही क्यों फॉलो करती है और इसके असल में चेंज होने का ही कारण क्या है। सबसे पहले तो गर्मियों में हम देखते हैं कि तापमान 40 से 50 डिग्री भी पहुंच जाता है और सर्दियों में तो 0 डिग्री से भी नीचे पहुंच जाता है। तो तापमान का इतना ज़्यादा अंतर कैसे हो सकता है? क्या इसका रीज़न सूरज से कुछ लेना देना है? क्योंकि तापमान का अंतर तो हमें पता है कि सूर्य की किरणों से हो सकता है। सूर्य की किरणें सतह को गर्म करती है जिससे तापमान का अंतर पैदा होता है। तो क्या इसका लेना देना अर्थ और सन की डिस्टेंस का कुछ ना कुछ है? आइए वो जानने की कोशिश करते हैं। तो हम सब ने किताबों में देखा होगा कि अर्थ का जो ऑर्बिट है वो देखने में कैसा लगता है। क्या वो देखने में बिल्कुल ऐसा लगता है? ये ऑर्बिट देखने में बिल्कुल अंडाकार, कितनी इलिप्टिक दिखाई देती है, राइट? असल में क्या ये इतनी इलिप्टिक होती भी है जितनी हमें दिखाई देती है? क्योंकि पुस्तकों में हमें इलिप्टिक ऑर्बिट को समझाने के लिए इसे बहुत ही ज़्यादा इलिप्टिक दिखाया जाता है। एक्चुअल में अगर हम देखें तो ये जो हमें दिखाया जाता है ये एक्चुअल में ऐसी नहीं होती। इसकी शेप देखने में कैसी होती है? तो इसकी शेप देखने में बिल्कुल ऐसी होती है। पर अब आप बोलेंगे कि ये तो बिल्कुल सर्कुलर है और हमें सिखाया गया है कि हमारी ऑर्बिट इलिप्टिक होनी चाहिए। तो अगर हम ओवरऑल ये देखें तो अर्थ सन का सबसे जो क्लोजेस्ट डिस्टेंस होता है वो 147.1 मिलियन किलोमीटर है और अर्थ सन के डिस्टेंस सबसे फार जो पॉइंट है वो 152.1 मिलियन किलोमीटर है। अगर इस चीज़ का अंदाज़ा लेने के लिए हम एक उदाहरण लेते हैं। हमें पता है यूनिवर्स में सबसे तेज़ गति किसकी होती है? प्रकाश की, राइट? लाइट की स्पीड को सबसे तेज़ माना भी जाता है। तो जो अगर यही लाइट सूर्य की सतह से निकल के पृथ्वी तक पहुंचने में इसे 8 मिनट लगते हैं, तो सोच के देखिए दूरी कितनी बड़ी है। और ये जो हम सबसे शॉर्टेस्ट डिस्टेंस और फार डिस्टेंस के बीच का जो डिफरेंस है वो केवल 3% है। जैसे कि मैंने आपको बताया था कि गर्मियों में तापमान तो 40-50 डिग्री तक चले जाता है और सर्दियों में 0 डिग्री से भी नीचे चले जाता है। तो इतना ज़्यादा अंतर क्या केवल ये 3% से हो भी सकता है? क्योंकि अगर हम इस मॉडल को देखें तो हम सब यही सोचेंगे कि अगर अर्थ सबसे ज़्यादा सूर्य के सबसे नज़दीक हो तो पूरी अर्थ पे गर्मियों का मौसम होना चाहिए और अर्थ अगर सूर्य के सबसे दूर हो सो विंटर का मौसम होना चाहिए। पर क्या ऐसा एक्चुअल में होता भी है? क्योंकि हमें देखने में मिला है कि अर्थ सन का एक्चुअल में अर्थ और सन की सबसे क्लोजेस्ट जो डिस्टेंस है वो जनवरी में देखने को मिलती है। और इस मॉडल के हिसाब से अगर ये क्लोजेस्ट डिस्टेंस जनवरी में देखने को मिलती है तो अर्थ में तो विंटर का मौसम होना चाहिए, समर का मौसम होना चाहिए। पर इंडिया में हम देखते हैं कि विंटर सीज़न चल रहा होता है जनवरी में, राइट? और अगर सबसे ज़्यादा दूरी जुलाई के मौसम में होती है, अगर अर्थ सन से सबसे ज़्यादा दूर जुलाई के मौसम में है तो फिर तो विंटर सीज़न होना चाहिए क्योंकि ये बहुत दूर है। पर हमें इंडिया में क्या देखने को मिलता है? जुलाई में गर्मियों का मौसम चल रहा होता है और हमें पता है कि अर्थ में एक टाइम पे 2 सीज़न देखने को मिलते हैं क्योंकि जब हम इंडिया में गर्मियों का मौसम चल रहा होता है तो ऑस्ट्रेलिया जैसी कंट्रीज़ में सर्दियों का मौसम चल रहा होता है, और जब इंडिया में सर्दियों का मौसम चल रहा होता है तो ऑस्ट्रेलिया जैसी कंट्रीज़ में गर्मियों का मौसम चल रहा होता है। तो क्या आपको लगता है कि अर्थ सन का जो डिस्टेंस है वो इस चीज़ को जस्टिफाई भी करता है? बिल्कुल भी नहीं। सो इसका और क्या कारण हो सकता है? तो अगर आप देखें, हमारी जो अर्थ है ना केवल उस पर इलिप्टिक ऑर्बिट है, इसके साथ साथ एक और चीज़ जो बहुत बड़ा कारण है वो है अर्थ की टिल्ट। अर्थ, हमें पता है कि अर्थ की जो धुरी है, एक्सिस है, वो 23.5 डिग्री से झुकी हुई है, और इसी झुकाव के साथ साथ ये हमारे सूर्य का चक्कर भी लगाती है। और इसी को अगर हम देखें तो अलग अलग पोजीशंस पे हमें अलग अलग सीज़न देखने को मिलते हैं। आइए इसी चीज़ को अब एक डेमोन्स्ट्रेशन से समझने की कोशिश करते हैं। तो मान लीजिए ये सूर्य की रोशनी है और हमें ये सतह पे सूर्य की रोशनी देखने को मिलती है। अब अगर ये सतह बिल्कुल स्ट्रेट है तो सूर्य की रोशनी हमें बहुत ही कम एरिया में मिलेगी देखने को, और इससे हमें बहुत इंटेंस दिख रही है अभी रोशनी, राइट। और यहीं अगर इसी बोर्ड को अगर हम टिल्ट कर दें तो आपको देखने को मिलेगा कि ये जो रोशनी है ये थोड़े बड़े एरिया में स्प्रेड हो रही है। स्प्रेड होने के कारण इसकी इंटेंसिटी कम हो जाती है। और फिर से अगर इसको स्ट्रेट करके देखें तो ध्यान से देखिए, अभी इंटेंसिटी बहुत ज़्यादा है, राइट। अब इसे टिल्ट करके देखते हैं, और टिल्ट या तो इधर से अभी देखिए इंटेंसिटी बहुत ज़्यादा है क्योंकि छोटे एरिया में पड़ती हुई दिख रही है। अगर हम इसे टिल्ट करें तो यही रोशनी हमें बड़े एरिया में फैलती हुई दिखाई देती है, और अगर ये बड़े एरिया में फैलती है तो इसकी इंटेंसिटी कम होगी। कम इंटेंसिटी की वजह से तापमान ज़्यादा बढ़ ही नहीं पाता। और अगर स्ट्रेट में देखें तो अभी इंटेंसिटी बहुत ज़्यादा है और इसी वजह से टेम्परेचर्स बहुत ज़्यादा इंक्रीज़ होते हैं जल्दी। अब इसी चीज़ को हम अर्थ के साथ देखते हैं। इधर से हमारे पास अभी मान लीजिए ये अर्थ है और ये इसकी एक्सिस है। अब सूर्य की तरफ अगर ये एक्सिस झुकी हुई है नॉर्दर्न हेमिस्फीयर, तो सूर्य की रे सबसे पहले नॉर्दर्न हेमिस्फीयर में पड़ रही है, जिसकी वजह से इंटेंसिटी बहुत ज़्यादा है। यही रेज अगर सदर्न हेमिस्फीयर में हम देखें तो ये बहुत ही बड़े एरिया में फैल जाती है। इसी चीज़ को एक दोबारा देखते हैं, पोजीशन। तो सबको दिखाई दे रहा होगा यहाँ पे नॉर्दर्न हेमिस्फीयर में अभी कितनी ज़्यादा इंटेंसिटी है, क्योंकि लाइट डायरेक्टली नॉर्दर्न हेमिस्फीयर में पड़ती है। और अगर हम ये सदर्न हेमिस्फीयर में देखें तो बड़े एरिया में स्प्रेड हो जाती है। बड़े एरिया में स्प्रेड होने के कारण जो सदर्न हेमिस्फीयर का अभी टेम्परेचर है वो बढ़ ही नहीं पाता। वहीं नॉर्दर्न हेमिस्फीयर में इंटेंसिटी ज़्यादा होने के कारण ये टेम्परेचर बहुत तेज़ी से बढ़ता है। अभी हम इसी चीज़ को देखते हैं कि बाकी सीजन्स में ये कैसे वर्क करती है। तो शुरू करते हैं सबसे पहले समर सीज़न से। समर सीज़न में जैसा कि हमने देखा, जो नॉर्दर्न हेमिस्फीयर है इसकी पोजीशन आप यहाँ पे देख सकते हैं। इसकी अभी हमारी ये जो एक्सिस है ये सन की तरफ झुकी हुई है, जिस वजह से जो सूर्य की रोशनी है वो डायरेक्टली नॉर्दर्न हेमिस्फीयर में पड़ रही है। और जो सदर्न हेमिस्फीयर में हम देख सकते हैं कि ये बड़े एरिया में स्प्रेड हो रही है, जिसकी वजह से सदर्न हेमिस्फीयर का टेम्परेचर ज़्यादा बढ़ नहीं पा रहा और नॉर्दर्न हेमिस्फीयर में बहुत तेज़ी से टेम्परेचर बढ़ता है। अब इसकी पोजीशन को ध्यान में रखते हुए अगला सीज़न देखते हैं, जो कि है ऑटम। ऑटम की पोजीशन देखने पे आपको पता चलता है कि अब ना ही तो इसमें नॉर्दर्न हेमिस्फीयर और ना ही सदर्न हेमिस्फीयर सूर्य की ओर झुके हुए हैं, राइट। इस वजह से हो क्या रहा है कि जो सूर्य की रोशनी है वो नॉर्दर्न और सदर्न हेमिस्फीयर में बराबर मात्रा में स्प्रेड हो जाती है, जिसकी वजह से टेम्परेचर डिफरेंस बन ही नहीं पाता। और इसी एक्सिस में इसी ऑर्बिट में आगे बढ़ते हुए नॉर्दर्न हेमिस्फीयर में विंटर सीज़न आता है। विंटर सीज़न तब आता है जब हमारी जो एक्सिस है वो सूर्य से दूर झुकी होती है, और दूर झुकी होने के कारण अब तो सदर्न हेमिस्फीयर जो है वो सूर्य की ओर झुका हुआ है, जिसकी वजह से सूर्य की रोशनी अब डायरेक्टली सदर्न हेमिस्फीयर में पड़ रही है। ज़्यादा इंटेंसिटी का मतलब है ज़्यादा टेम्परेचर्स बढ़ेंगे, और जो नॉर्दर्न हेमिस्फीयर में ज़्यादा एरिया में स्प्रेड हो जाती है, जिसकी वजह से टेम्परेचर तो बढ़ेंगे ही नहीं ज़्यादा। इसकी वजह से सदर्न हेमिस्फीयर में इस वक्त समर है और नॉर्दर्न हेमिस्फीयर में विंटर है। अब इसी में आगे बढ़ते हुए हमें मिलता है स्प्रिंग। स्प्रिंग भी बिल्कुल ऑटम की ही तरह, ना ही इसमें नॉर्दर्न हेमिस्फीयर ना ही सदर्न हेमिस्फीयर सूर्य की ओर झुके हुए हैं, तो सूर्य की रोशनी बराबर नॉर्दर्न और सदर्न हेमिस्फीयर में स्प्रेड होती है, जिसकी वजह से टेम्परेचर डिफरेंस नहीं बन पाता। और सिंस हमने देखा कि अभी हम जो नॉर्दर्न हेमिस्फीयर था वो विंटर से निकल के समर की तरफ जा रहा है, तो इस नॉर्दर्न हेमिस्फीयर में हम इसे स्प्रिंग सीज़न बोलेंगे, और वही सदर्न हेमिस्फीयर जो हमने देखा वो समर से निकल के अब विंटर की तरफ जा रहा है, तो इसी सीज़न को हम ऑटम सीज़न बोलेंगे। इन दोनों का डिफरेंस बस नेमिंग के ऊपर है कि हम किस सीज़न से किस सीज़न की ओर जा रहे हैं। अब हमें तो अब ये देख के तो अब हमें एक चीज़ क्लियर हो जाती है कि कहीं ना कहीं इसका रीज़न टिल्ट हो सकता है। आइए इस चीज़ को एक छोटे से डेमोन्स्ट्रेशन से फिर से रिकैप करके देखते हैं। मान लीजिए ये जो स्टूल रखा हुआ है ये सन है, और अभी आप देख के बता सकते हैं कौन सी पोजीशन है। नॉर्दर्न हेमिस्फीयर में अभी क्या हो रहा होगा? समर, राइट, क्योंकि नॉर्दर्न हेमिस्फीयर सूर्य की ओर झुका हुआ है। अब हम ऑर्बिट में आगे बढ़ेंगे और अब समर के बाद आएगा ऑटम सीज़न। अब इसमें तो नॉर्दर्न हेमिस्फीयर और सदर्न हेमिस्फीयर सूर्य की ओर झुके ही नहीं है, और अगर ये रोशनी आती है तो दोनों में बराबर डिस्ट्रीब्यूट हो जाती है। वहीं ऑर्बिट में हम आगे बढ़ते हुए हमारे पास नॉर्दर्न हेमिस्फीयर में विंटर आएगा। अब इस केस में सदर्न हेमिस्फीयर में समर चल रहा होगा, क्योंकि वो डायरेक्टली सूर्य की तरफ पॉइंटेड है। अब आगे बढ़ते हुए विंटर के बाद स्प्रिंग आएगा। अब हम देख सकते हैं इसमें भी सेम नॉर्दर्न हेमिस्फीयर और सदर्न हेमिस्फीयर कोई भी सूर्य की ओर झुका ही नहीं है। सेम यही साइकिल हमारी कंटिन्यूसली चलती रहती है। थैंक यू। तो अभी हमने ये सीखा कि हमें जो पहले मन में लगता था कि डिस्टेंस की वजह से हमारे सीजन्स चेंज होते होंगे, पर ये बिल्कुल भी सच नहीं है। इसका मेन कारण टिल्ट है, राइट। तो हमारे मन में अब ये क्वेश्चन ज़रूर आएगा कि आखिर ये टिल्ट आया ही क्यों है अर्थ पे। अगर ये टिल्ट ना होता तो हमें सीज़न बिल्कुल देखने को नहीं मिलते, राइट। तो ये टिल्ट आखिर अर्थ पे आया ही कैसे? इसका रीज़न जानने के लिए हमें सौर मंडल के निर्माण की ओर देखना होगा। 4 बिलियन ईयर्स अगो उस समय हमारा सन काफ़ी यंग था, और हमारी जो सौर मंडल था उसमें केवल डस्ट और गैस के पार्टिकल्स ही थे, और वो डस्ट और गैस के जो कण थे वो आपस में मिलके अपना आकार बड़ा करते गए। उन्होंने अपना आकार जैसे जैसे बड़ा करा वैसे ही उसमें गुरुत्वाकर्षण बल भी बढ़ता गया, और ग्रेविटी के बढ़ने से वो और भी ज़्यादा डस्ट पार्टिकल्स को अपनी तरफ और अट्रैक्ट करता गया। ऐसे ऐसे करके उनका साइज़ किसी ग्रह जितना हो गया। इसी से हमारी ग्रह बनने की प्रोसेस, यही हमारी ग्रह बनने की प्रोसेस है। ऐसे कई सारे ग्रह बने, और जो रिमेनिंग जो डिब्रीज थी वो उनका कोलिजन स्टार्ट हो गया। ऐसे बहुत सारे ग्रह अब आपस में कोलाइड होना भी स्टार्ट हो गए। तो क्या हुआ, जो हमारी अर्थ थी, वैज्ञानिकों के माने तो हमारी अर्थ ने 10 मेजर कोलिजन्स फेस किए हैं, जिसमें से हर एक कोलिजन ने हमारी अर्थ की टिल्ट को थोड़ा थोड़ा चेंज किया। आखिर में जो कोलिजन होता है वो सबसे इम्पॉर्टेंट माना जाता है, जिसे थिया कोलिजन भी बोलते हैं। इसी कोलिजन को हम देखेंगे। इस कोलिजन में मंगल जितने आकार का कोई ग्रह हमारी अर्थ से टकरा जाता है, और इसको समझने के लिए अब हम एक नासा की सिमुलेशन देखते हैं। सो जैसे ही मंगल जितने आकार का कोई प्लैनेट हमारी बहुत ही यंग अर्थ से टकराता है, हम देखते हैं बहुत सारी डिब्रीज स्प्रेड हो जाती है, और हमें ये कोलिजन बिल्कुल देखने में तो ऐसा लग रहा होगा जैसे लिक्विड आपस में टकरा रहे हैं, राइट, क्योंकि इनकी ऊर्जा बहुत ज़्यादा है, जिससे इतनी हीट जनरेट होती है कि लिक्विड की तरह बिहेव करने लगते हैं। हम देखते हैं जो डिब्री सब स्प्रेड हुई वो धीरे धीरे कलेक्ट होना भी शुरू होते हैं, और इसी टकराव के कारण हमारी जो अर्थ है उसमें उसकी रोटेशन जो एक्सिस है उसमें टिल्ट आता है। और अब हम देखेंगे ये जो जितनी भी डिब्रीज हैं वो इवेंचुअली कलेक्ट होके हमारा मून भी बनाती है। इसी कोलिजन्स, इसलिए ये कोलिजन इतना ज़्यादा इम्पॉर्टेंट है क्योंकि इस कोलिजन से ना केवल हमें हमारा टिल्ट मिला जो कि 23.5 डिग्रीज है, और आखिरी में जाके हमारा मून भी इसी से ही बना। सो इसलिए ये कोलिजन देखने में तो कितना वायलेंट सा लगता है, और हमारी डे टू डे जो सीजन्स हैं, सीज़न जैसे चेंज होते हैं उसका मेन कारण ही इतना सबसे ज़्यादा वायलेंट कोलिजन ही है। ये ना होता तो ना हमारे पास मून होता और ना हमारे पास सीजन्स होते। No, this is not Big Bang. Big Bang explains about the origin of our universe. ये हमारे एक्चुअली टिल्ट को एक्सप्लेन करता है। ऐसे कई सारे कोलिजन्स होते रहते हैं, पर ये जो 10 मेजर कोलिजन्स हैं ये हमारे लिए इसलिए इम्पॉर्टेंट है। तो आपने जो सिमुलेशन देखी उससे तो समझ आ ही गया होगा कि इस कोलिजन ने कैसे हमें हमारा टिल्ट दिया और मून भी दिया और उससे सीजन्स भी बने। सो थैंक यू। अब अगर आपके कोई क्वेश्चंस है किसी भी लैंग्वेज में, इंग्लिश, हिंदी, मराठी, आप पूछ सकते हैं।
आपको कोई सवाल है इस प्रेजेंटेशन के बारे में? Want to have questions? No? Yeah. नाही, ॲक्च्युली ते जर सिम्युलेशन बघितलं तर त्याच्यामध्ये दुसरा जो मोठा भाग होता तो पुन्हा पृथ्वीमध्ये जाऊन आदळला. बघितलं का? बघा, आपण परत एकदा बघूया. हां, हे बघ, हे आलं. त्याच्यानंतरचा एक जो भाग आहे तो इथे गोल फिरत राहिला, पण हा जो दुसरा भाग आहे तो नंतर जाऊन पुन्हा ह्याच्यावरतीच आदळला. ठीक आहे, आता बघू शकतो हा जो आहे पुन्हा त्याच्यावरती आदळला त्याच्यामुळे. ठीक आहे, या. ओके, हां, दॅट्स राईट. या, सो हे जे अँग्युलर मोमेंटम जे असतं ना, जसं आपण एक भोवरा बघतो आणि त्या भोवऱ्याला जेव्हा आपण आपल्या याच्यावरती टाकतो, फरशीवरती टाकतो, त्यावेळेला त्याची जी अक्ष असतो तो असा असा गोल फिरत असतो, त्याला प्रिसेशन म्हणतात, प्रिसेशन मोशन. तर हे जे मोशन आहे ते पण आपल्या अक्षाबद्दल होत आहे, पण त्याचा सायकल जो आहे तो जवळजवळ 23,000 वर्षांचा आहे. तर त्याच्यामुळे आपल्याला आपल्या आयुष्यामध्ये जिथे दिसतो आहे ध्रुवताऱ्याला पॉईंट करतो आहे आपला अक्ष, तर तोच राहतो. पण जर तुम्ही खूप हजारो वर्षांपूर्वीचं जर बघितलं, आणि 23,000 म्हणजे खूप हजार वर्ष होतात रे, तर त्यावेळेला ते दुसऱ्या ठिकाणी असणार. हां, हो, ऑलमोस्ट सगळ्या ग्रहांचे जे ॲक्सिस असतात ते दे विल कीप प्रिसेसिंग. या, पण त्यांचा जो पिरियड असतो तो वेगवेगळा असू शकतो.
कॅन यू एक्सप्लेन अबाउट झिरो शॅडो डे?
हो, झिरो शैडो डे, यू अंडरस्टैंड?
हाँ, उसमें वो भी एक्सप्लेन करना होगा.
यू नो,
हाँ. सो जीरो शैडो डे हमें कब देखने को मिलता है? ये बेसिकली कुछ ही स्पेसिफिक प्लेसेस में देखने को मिलता है. आपको ट्रॉपिक ऑफ कैंसर और कैप्रिकॉर्न के बारे में पता होगा. 23.5 डिग्री पे हमें लैटिट्यूड्स देखने को मिलते हैं. जो सन की पोजीशन है वो इससे हाई जाती नहीं है, और सन की पोजीशन हम ऑल इन द ईयर अगर देखें तो मैक्सिमम ट्रॉपिक ऑफ कैंसर और सदर्न में मैक्सिमम ट्रॉपिक ऑफ कैप्रिकॉर्न तक जाती है. तो अगर ज़ीरो शैडो डे सब प्लेसेस, इनके बीच जो भी प्लेसेस हैं सबके लिए अलग अलग होगा, क्योंकि हम ज़ीरो शैडो डे तब देखते हैं जब अगर हमारे नून में सन की पोजीशन परपेंडिकुलर हो, और ये तभी पॉसिबल हो सकता है इनके बीच कुछ स्पेसिफिक पर्टिकुलर डे अगर सन की पोजीशन इनसे पास हो रही है। तो अगर हम ऑल अराउंड द ईयर देखते हैं तो सन इन लैटिट्यूड्स के बीच ही ट्रैवल करता है, जिसकी वजह से हमें किसी ना किसी पॉइंट पे सन हमें परपेंडिकुलर देखने को मिलेगा। सो उससे ज़ीरो शैडो रे एक्सप्लेन हो सकता है। इसकी काफ़ी थ्योरीज हैं। एक मेन थ्योरी हमें कॉमेट से मिलती है कि हमें एक थ्योरी ये है कि इनिशियली अर्थ में कोई वाटर नहीं था, पर कॉमेट्स की बॉम्बार्डमेंट्स की वजह से, कॉमेट्स इनिशियली जैसा मैंने बोला बहुत सारे कोलिजन्स होते हैं, उसमें से कॉमेट्स की भी काफ़ी कोलिजन्स होते हैं, और कॉमेट्स हमें बताइए आइस के चंक्स होते हैं, उनकी बॉम्बार्डमेंट्स की वजह से पानी आ सकता है। ये एक बहुत फेमस थ्योरी है।
This last collision that we talked about, what is the timeline of this, and does it have anything to do with, like they say that when dinosaurs used to roam around, there was some sort of cosmic activity which made their extinction possible. Is there a timeline coinciding or there is a difference?
No, we are talking about the formation of our tail, और उस टाइम पे तो लाइफ की फॉर्मेशन हुई भी नहीं थी। हम 4 बिलियन ईयर्स ओल्ड की बात कर रहे हैं, उस टाइमलाइन की। डायनासोर्स बहुत ही बाद में फॉर्म हुए अगर हम टाइम स्केल में देखें।
अच्छा, मीन्स आफ्टर दिस, आफ्टर अ लॉट ऑफ टाइम लाइफ गॉट फॉर्म्ड ऑन अर्थ, राइट?
जैसे कि अभी मैंने बताया, इसके बाद अर्थ में और भी छोटे मोटे कोलिजन्स होते रहे, जिसकी वजह से वाटर भी आया, उसकी वजह से आगे लाइफ भी पॉसिबल हो गई।
सो दिस टाइम स्केल इज डिफरेंट। ऑल्सो द वो जो whatever comet or anything that came and then wiped out the dinosaurs, that was not as big as this. So this is like a Mars-sized object, and so that must have been even smaller. This kind of a thing, if it happens, it will cause catastrophe over the entire planet. Again, I mean, if it happens.
Excuse me. As you said that the Earth's orbit is not exactly ellipse and it is kind of circular. देन हमें स्टार्टिंग से टेक्स्ट बुक में ये क्यों पढ़ाते आ रहे हैं दैट इट इज़ एलिप्स?
एक्चुअली पे उसकी ऑर्बिट एलिप्स ही होती है, बट हमने जैसे देखा डिफरेंस बहुत ही कम है। इतने कम डिफरेंस में अगर हम ओवरव्यू देखें तो बहुत क्लोज सर्कल की होगी हो। एक्चुअल में इतनी ज़्यादा इलिप्टिक नहीं होती, इसलिए। और हमें टेक्स्ट बुक्स में दिखाने के लिए कि अर्थ की ऑर्बिट इलिप्टिक ही होती है, इसलिए उसे बहुत ही ज़्यादा एक्जेजरेट करके दिखाया जाता है।
ओके,
इसलिए।
हॅलो, हे 3 सीझन आपण म्हणतो आपण टिल्ट आहे ऑर्बिट त्याच्यामुळे, पण आता हे क्लायमेट चेंज चाललं आहे, सडनली कुठे पाऊस येतोय, कुठे सडनली दुष्काळ पडतोय, हे कशामुळे होतं? हे बिकॉज ऑफ
हे जे आहे ते थोडेसे लोकल चेंजेस आहेत. जर तुम्ही पूर्ण गोलार्धांना जर ॲव्हरेज केलं की काय होतं आहे नॉर्दर्न हेमिस्फिअरमध्ये आणि सदर्न हेमिस्फिअरमध्ये, तर हे जे सीझनल चेंजेस आहेत ते तसेच होत राहतात. पण त्या सीझनल चेंजेसवरती अजून जास्त व्हेरिएशन्स होतात आता, आणि ते व्हेरिएशन्सची जी मात्रा आहे ती आता वाढत चाललेली आहे क्लायमेट चेंजच्या परिणामामुळे. ठीक आहे? नो, आय मीन एक्स्ट्रा हे जे स्टोकॅस्टिक गोष्टी आहेत जे जास्त वर खाली जे होतं आहे अधूनमधून, ते दॅट इज नॉट बिकॉज ऑफ द टिल्ट. पण तो जो मेन की उन्हाळ्यामध्ये तुम्हाला जास्त तापमान दिसतं पूर्ण उत्तर गोलार्धात आणि मग हिवाळ्यामध्ये कमी दिसतं, तो जो आहे तो प्रकार टिल्टमुळे होतो.
Hello. Just like you showed in your simulation that moon may have formed from earth only. So did we find the same elements present in the ground on the moon just like we have on earth? Did we find that?
Yeah, I think there is a similarity between what we see. It's just that the surface of the moon is constantly being bombarded, right? Because it does not have a protective atmosphere.
But then if we drill a hole inside the moon, say not a very big hole, but even if say 20 meters or 30 meters, will we find the same metals?
It is very hard to dig a 20-30 meter hole. So people are trying this, and that's the reason why we have all these rovers trying to go to the moon. But they have not done 20-30 meter holes yet.
Okay, thank you.
But ideally you would like to do that, yes.
Hello.
Okay.
First of all, thank you very much for your nice presentation. It really looks very good for all of the audience, I guess. My question is like that. Since you told that because of the tilting has been happened because of the different collisions, right? So this are you expecting any collisions in near future, or will that affect the tilting of the Earth axis? And also, I think if it is the tilting will be affected, in that case, the seasons will be also shifted, right? So will you expect any collisions? Because I think the collisions has already stopped for some durations. So will you expect any collisions in near future or something like that? Any input? I mean, if you have any sort of things.
I don't know about it.
Okay. Yeah. So typically, such large collisions happen very early on. Now there are also smaller collisions which are happening. So once in a while you will see, for example, Jupiter in the 1990s or so, it was hit by a big comet, right? This comet Shoemaker-Levy. And so these kind of collisions are quite rare, and the reason why they are rare is because Jupiter is kind of shielding us from them. Okay, many things get just spurt out by Jupiter and the presence of these massive planets which are around us. But there are nevertheless tiny collisions which happen of smaller objects, and these can also be deadly. And unfortunately, it is also very hard to predict when they are going to happen. So right now, there is a question about, like people do ask this question as to what is the frequency of these foreign objects coming and hitting the Earth. So tiny objects, they come many times. Okay, so you would have seen these asteroids, sorry, not asteroids, meteorites. So meteorites do fall on the Earth all the time, right? So if you just go on the Earth and you take, in the night sky, you try to take a long exposure picture, once in a while you will see this meteorite going down, okay? So we are constantly being bombarded, but not with big particles. But big particles do happen once in a while. Once in every 100 years, there are like big chunks of rocks which fall down. I think there was recently one thing which happened in Siberia, which was quite interesting. And nobody had predicted it to be happening. But then there were lots of videos which were captured on dashcam, the dashcams of cars, right? And so you can take a look at some of these kind of events.
Thank you.
Yeah, and thankfully, they have not been deadly yet.
Yes, I understand.
But if it was as big as Mars, then it would definitely wipe out life on Earth.
Yes. And since the talks has been based on the season, so just it's a little bit away from your topic. Just it's kind of a general things I can say. So is the global warming will affect these season changes along with the axis? I mean, is it going to happen? Something will...
Yeah, no, so this global warming and climate change, it actually produces fluctuations around this mean pattern. Okay, so there is a mean pattern which is happening because of the tilt. That is the major effect that you see. On top of it, you will start to see ups and downs. And the number of these ups and downs that are happening, they have started to grow. So you are starting to see more and more extreme events. Okay, so the frequency of these extreme events has increased, but the overall pattern that is because of the tilt of the Earth, that still remains.
Okay, thank you. Yeah, thank you very much. Thank you.
Hello.
Oh, sorry.
सर जरा सन ब्रोकन ऑफ कन्सेप्ट जो आहे तो जरा सांगता का व्यवस्थित?
पुन्हा एकदा सांगू शकतो काय?
सन पीस ऑफ सन ब्रोकन ऑफ आता रिसेंटली इंटरनेटवर दिसतंय.
Oh, I see. So, Nishan, do you want to handle this? Okay. Yeah. No, I know. That's why you are better suited. Okay. So, once in a while, what happens is the surface of the sun is quite unstable, and once in a while, you will see that some part of the sun gets ejected. But it's a very small part. I mean, don't think that it's a big thing as such. Compared to the mass of the entire mass of the sun, it is quite big, it is quite small. Okay, and then that thing it just travels outside with a large speed. Okay, and then we are just lucky that we are not in its path. I think there was an event which happened in 2022 where we missed it. If the Earth was say a few days ahead of it in its orbit, then we would have been hit by such a coronal mass ejection. So these kind of things happen, and it is also fairly difficult to predict. but people try to monitor the sun to see when such events happen.
I wanted to ask you, like, how are we able to calculate the tilt of the Earth?
How are we able to calculate?
The tilt of the Earth.
Oh, the
axis.
tilt of the Earth. How do we calculate the tilt of the Earth? Okay. So I think one way to do this is if you just look at this picture, right? Sorry, we went the other way around. Let's go here. Okay, let's go to this position, right? Oh, sorry. The previous one. Okay, so what you can do is you can try to find out what is the latitude. So do you know what latitudes are?
Yeah.
You start at the equator, that is 0 degrees. So you sit at the center of the Earth and you measure the angle away from the equator. Okay. So what you can do is you can try to find out what is the point on the Earth where you start to see that the sun rays are falling on what northernmost latitude do you see the sun rays to be falling perpendicular, and then what will happen is this day will change. So initially when you are at equinox they will fall on the equator, and after you go to the summer solstice then they will fall perpendicular at a particular location. So if you can measure that latitude then you will be able to also find out the tilt of the Earth.
Okay, thank you.
There are multiple other ways to do it, but that's one of the ways.
Good evening,
Yeah,
sir.
there is also-
Why do we get global warmings?
Huh?
Why do we get global warmings?
Global warming. Okay, so look, if the Earth did not have an atmosphere, it would have been a big problem, right? We would not exist, we would not be able to breathe and so on. But the reason why we actually exist here is because of the atmosphere. Within the atmosphere, there are certain amount of gases which are called greenhouse gases. Okay, so they take the light from the sun and they trap that heat inside this atmosphere, and that's why we have such pleasant conditions on the Earth that life can survive. Now what happens is if you keep on adding these greenhouse gases more and more into the atmosphere, then they keep on trapping this heat. Okay? And this trapping of heat is what is causing global warming, okay, because of the excess presence of greenhouse gases. So typically all these gases, they go through certain cycles, okay? But human beings are like going through this industrial revolution, we have been putting more and more greenhouse gases into the atmosphere of the Earth. And then that is causing a problem. Remember, this amount that we are putting in is still small, but it's large enough that it causes these problems that we are seeing.
Okay, sir. Thank you, sir.
Okay. Oh yeah, he had a question. He's waiting from such a long time.
How meteorites form?
How do meteorites come? You want to answer this?
Meteorites are basically the leftover debris of some other collisions. We know that there are many asteroids in asteroid belt. They continuously collide with each other. And what left is the chunks of rocks, right? और वो chunks of rocks किसी भी collision के बाद हमें देखते हैं कुछ ना कुछ chunks टूट जाता है और वो chunk की orbit मतलब जैसे पहले जो original orbit होगी उससे भी change हो जाती है. ऐसे कई बार होता है कि हम देखते हैं asteroid belt में कई सारे जो objects हैं आपस में टकराए और उनकी orbit change हो गई. क्या बताओ inner solar system की ओर बढ़ते गए, अर्थ की तरफ भी बढ़ते गए और वो जो डिब्रीज हैं उनके कई ज़्यादा चांसेस होते हैं अगर वो इनर सोलर सिस्टम की ओर बढ़ रहे हैं कि वो अर्थ की ऑर्बिट को इंटरसेक्ट करें और इससे थ्रेट भी हो सकता है. अगर कोई मेजर ऑब्जेक्ट हुआ एस्ट्रॉइड जैसा तो वो अर्थ में कैटास्ट्रॉफी ला सकता है. पर बहुत सारे हम देखते हैं छोटे छोटे जो चंक्स हैं वो फॉलो करते हैं ऐसी किसी एस्ट्रॉइड की ऑर्बिट को और उससे अगर अर्थ की ऑर्बिट पास होती है तो ये जो छोटे छोटे ऑर्बिट्स हैं ये अर्थ की एटमॉस्फेयर से एंटर होते हैं और फिर बर्न होते हैं, जिससे हमें मीटियोर और मीटियोर शावर्स भी दिखते हैं.
Okay, I think we should.
And,
okay, one last question.
Sir, actually I got to know that the Mars, which is planet behind Earth, so in the atmosphere of Mars, some bacteria and some air particles have been found, which are only present when there is some life form. So the sun is more far from the Earth. So means Mars is more far from the sun as compared to Earth. Then why did the life did not exist till now?
Well, so I mean we don't know whether life did not exist on. I mean, as far as we know, there is no life on Mars. We have not found any traces of it yet.
No, means as per research by ISRO or NASA recently.
No. There was something which was found in the atmosphere of Venus. Okay. And there were some signs of certain no, I don't remember what was it. There was something which was found which suggested that there may be a biological markers there which are present in the atmospheres of Venus. Okay, but then it has been disputed. Okay, this particular claim has been disputed.
Okay.
So science always progresses like this, that there will be some claims which will be made and they will have to be verified by other teams, and sometimes they may not be able to verify it, or they find another reason why you could see such a thing.
Thank you.
Yeah, thanks. Okay, so with this we will end our session. In case you have not done it, please scan this particular QR code and help us by filling out an astronomy research survey that we are conducting as well. Thanks a lot.
We will be back in 10 minutes. So, yes.
Studying the sun with Aditya L1. हे पॅनल डिस्कशन सारखं आहे ना, कारण हेलन दुर्गेश
हो लावून त्यांना पॉवर कोड आहे, माझी पॉवर कोड सापडत नाही.
Hello. Yeah, so in few minutes we will be starting with our next session, which would be studying the sun with Aditya L1. So Aditya L1 is the upcoming ISRO mission, which is like a really great thing for us. So we would be discussing about that with a great group of panel. So please stay in your seats.
We won't start in 2 minutes.
Two questions.
Yeah.
Good questions though.
Very good. काय ग
You too. Like think on your toes, yeah. Think on the spot.
How do you measure the thing? I know at least one way.
After doing my PhD in Germany and postdoctoral research in Cambridge with Dr. Helen Mason from Cambridge. And we are currently doing a lot of research in trying to understand sun. And in doing so, we are also developing new generation mission. It's Aditya L1, which will facilitate it even better to understand the sun and its impact on our geospace environment.
Professor Nishant Singh.
Thanks, Amir. So I'm Nishant Singh. I'm also faculty here and moved here recently about 3 years ago after completing a set of postdocs in Stockholm and Germany. And now I'm working in solar physics, essentially looking at solar convection and its magnetism. So, thanks.
Thank you so much. Lovely to have all of you here and presenting this wonderful mission and this wonderful study of the sun to all of us. So I'll begin the interaction with a basic question from all of us. So Helen, why do we study the sun?
Good question. Why do we study the sun? The sun is so important to us here on Earth, and it's our nearest star. So if we can understand the sun, and we can see it in great detail, but if we can understand the sun, it helps us to understand other stars, other astrophysical bodies. So it's really important because it's so close. It's really important for life. So I've worked on, we've got some pictures here, so I should explain them before we click through them too fast. Okay, that's just, the sun is enormous. I hope you've had the opportunity to interact today with some of the teams that have been showing various research around IUCAA, in particular the sun. But the sun is enormous, so you could fit 1 million Earths. 1 million is how many lakh? That's 10
lakhs.
Yeah, inside the sun. It's huge. Okay. Yeah, so the sun, I've studied the sun for many decades, but using spacecraft, because we don't just look at the visible light that comes from the sun. Some of you, I hope some of you, did you have an opportunity to see the sunspots today with the sunspotter? Hands up if you saw you saw the sunspotter. Brilliant. Yeah, there's some nice big spots, and you could fit about 3 Earths inside those spots today. And they had a telescope, I think, at one stage. But we don't just look at it from the ground. We want to look at the sun in ultraviolet light and in X-ray light. And in order to do that, we need to go into space. So I've been fortunate enough to work on many space missions with NASA, with the European Space Agency, with Japan, and also with India. So each mission is different, and we'll come on to that a little bit later. But the sun is not constant, and you might have seen those sunspots. And when there's a lot of sunspots on the sun, sometimes we get explosions on the sun. And those explosions can shoot material out towards the Earth. Oh, we've gone back a bit. Go back one more. No, wait a minute. I want to see the aurora. Yeah. And they can cause the beautiful northern lights. Has anybody heard of the northern lights or aurora? Hands up. Yeah, aurora, beautiful. I've never seen them, but I would love to see them. So these are caused by the sun. Okay, if you go to the next one now, I'll see what's happening. Now this is a very, very special event. I wonder if anybody knows what this event is. Oh, someone's got their hand up. Do you want to shout it out? Oh, okay. There's a little girl just behind you as well. What were you going to say? Shout it out. It's a total solar eclipse. How many people here have seen an eclipse of the sun? Yeah, it's more frequent to see perhaps one of the moon, isn't it? But in a total eclipse of the sun, the moon exactly blocks out that very bright disk of the sun. So it's exactly blocked out. And we see this beautiful crown of light that we call the corona. Can you see how structured it is? How beautiful it is? Well, that's because it's ionized and it's tracing out the magnetic field. So the magnetic field on the sun is really important. And that the magnetic field is where the sunspots are, where the magnetic field is very strong. So the surface temperature of the sun is 6,000 degrees. But this corona is over 1 million degrees, and that's something that we've been trying to understand. We've got quite a good idea of what's going on, but we haven't really got all the details worked out just yet. Is that any more? Is that it?
Definitely. So is there a effect that the sun has on the Earth other than the aurora?
Yes. In fact, the aurora is a very beautiful effect. Okay? But the sun can have other less beautiful effects because we use technology. How many people have got a mobile phone, for example? Yeah, not many of you. Okay. TV, I don't know. You know, all sorts of things. Computer. Yeah, getting a few more. We use technology so much now. If you've ever flown in a plane or got a car. I mean, how many of you got a car? Yeah, you've got GPS, you've got all sorts of things that depend on technology. And if we have one of these big storms, sometimes it can affect that technology in different ways. It can affect the height at which satellites orbit, and that can change the GPS signal and things like that. So it can be quite detrimental if we have a big storm suddenly hitting the Earth's environment. So we need to understand that interaction between the sun and the Earth.
Right. In fact, in the last session, somebody was also curious about a piece of the sun breaking off. Does that happen, or?
Well, the explosions can be very large compared to the Earth, but actually they're quite small in mass compared to the whole mass of the sun. You don't have to worry about pieces of the sun breaking off, because although they seem very large to us, actually it's a small little, like a mosquito bite really on the sun. It's not going to be a huge problem for it.
Okay, thank you for putting that aside, that worry aside. Excellent. So I'll just ask Professor Tripathi that we are studying the sun, but why do we need to go to space to study the sun, and why, including this mission?
Right. Before I go there, I just wanted to add to what Dr. Mason said. I mean, there are two kind of effects, right? So one is called weather, right? And there is another effect which is called climate, right? So long-term weather monitoring, that defines the climate, right? So you have weather today which is bad, which is good, but if you look at 100 years or so, that will say that the climate pattern is changing and so on and so forth. Now, and to relate to the question I'm going to answer to you.
Definitely, please.
It's, so when you look at the sun, there are two kinds of things coming to you, right? One is that just the radiation, right? So any light you have, light source you have, is just going to give you radiation, which is in form of heat, for example, all the sunlight coming to you and so on. And the other is charged particles, right? Those charged particles are coming in form of solar wind, if you like. So there is always a wind which is coming out of the sun, and which are those producing these beautiful aurorae that Dr. Mason mentioned. And when you have these really large scale eruptions, as somebody mentioned that the piece of sun is breaking out, a little tiny thing is breaking out, but it's giving you a lot of charged particles which are coming all the way into the atmosphere. And when they interact with the Earth's atmosphere, which has magnetic field, they get into direct connection, they penetrate through the pipeline, then eventually they travel to the transformers and they burn, right? So that's the kind of space weather effect you get. But these radiation which is coming in, that can get absorbed, or that do get absorbed when you are talking about X-ray and ultraviolet radiation. The visible light comes to you because that's how we sustain. But the hazardous part of the radiation does not come to you, right? Because that gets absorbed by the atmosphere of the Earth. Now, it does a lot of things in the atmosphere of the Earth which we don't realize right away, but it has many other effects, like, for example, ozone ionization, ozone layer formation, oxygen ionization, and so on. And also, it produces it gives away heat in the atmosphere, so the atmosphere shrinks and expands. Right? Now we talked about satellite, the GPS technology, GPS satellite is sitting there. You have to maintain the orbit, but the gas is just sinking and expanding, right? So that is also a space weather effect, which is a little longer term space weather effect. And this radiation is going to change over the solar cycle if you figure out. It's about 11 years. So that's a long term, and it will keep building up and so on and so forth. Now, since we are so much technologically dependent, and we know that X-ray and ultraviolet, which is going to affect all these orbits and so on with the upper atmosphere, they're absorbed by the Earth's atmosphere. We have to go out in space to look at those radiation. Visible light you can do from ground, but to try to understand the whole radiation spectrum from the sun, you have to go out into the space to catch those radiation which is not coming to you, and then try to understand that how and why does that vary, and can we predict that variation on a time scale which we can then control our satellite orbit, monitor our satellite orbits and so on, so that the effect which sun is producing can be minimized. Right?
That's great. So you would say in a way that we are quite lucky down here on the Earth to have such a huge atmosphere in between us and space that the harmful rays which come from the sun cannot reach us. So I just want to clear, so does the sun give, what kind of rays does the sun give out?
So sun,
just to know, I mean.
Right. So if you know what electromagnetic spectrum is, right? So the highest energy electromagnetic radiation is in gamma ray. Then you have X-ray. Then you have ultraviolet. Then you have visible. Then you have infrared and radio, right? So you start at gamma ray and finish at radio. Visible, infrared, and radio you can observe from ground, because they come all the way to the ground. And for example, you know, the GMRT is there, right? NCRA, National Radio Telescope.
The Giant Meter Radio Telescope.
Right, and GMRT is the telescope which is run by this Giant Meter Wave Radio Telescope. And that actually look at the radio part of the spectrum. So it studies not only the sun, but that is the one kind of wavelength which you can use to study stars in the daytime, the other stars, right? Because the radio signals are coming and they are not dependent on day and night. But when you are looking for the high energy ones, starting at gamma ray, you have to go to space, because everything till ultraviolet is by and large absorbed by the Earth's atmosphere. So for sun, gamma ray doesn't come very often. In very small events, I mean really large events, sometimes you see these gamma ray radiations coming in, but mostly it's X-ray and ultraviolet. And these are the two most important radiation part of the radiation spectrum which are essential to understand this sun-earth connection.
Okay, that's good to know that there's so many things coming from the sun which thankfully don't reach us, but then we still need to study them. So I'll move to Nishant, and I'll ask you if you want to add to some of the effects that you know the sun has on the earth, and also would like to know that I mean maybe first you mentioned.
Yeah, no, I mean, one of the major effects are already covered. Space weather is, of course, an event and effect that one wants to predict. I'm generally interested in studying ways to predict the space weather events by not only, looking at some observational data or information, but by looking at the oscillation patterns of the sun. You know, one way one can think of the sun is actually like a musical instrument. It's more like a tabla or something. And while it may seem somewhat unreasonable, but it is actually like that. Sun is after all a spherical ball of plasma, which is like a fluid. Fluid motions are there, which excite all sorts of waves that are trapped, forming what is called a standing wave eigenmode, standing waves. Just like when you blow a flute or tabla and you hear a particular frequency that pleases your ears, right? Sun is a very complicated guitar or very complicated tabla. And by looking at the effects and their frequency, their amplitudes, one can then be able to understand the structure, the thermodynamic conditions of the star, sun in this case. Yeah. So if you just play your tabla in water, you'll find the difference in the sound. You just damp it. You make it too dry, you notice the difference. You break one of the strings of your guitar, you notice the difference, right? Similarly, the conditions, and by making any of these experiments, you are actually ruling out or understanding one or two effects of the conditions of the sun. You know, the sound speed in this medium is measured by so-called organ pipe experiment, right? That one can blow some organ pipe with some known frequency tuning fork, and then one determines how fast the speed sound travels in this medium. So similarly, by characterizing and looking at the effects of oscillations, one can perhaps, so far these are work in progress, magnetohelioseismology is still a field that is emerging and not yet very much matured, unlike the standard classical helioseismology, where you study the waves to predict and understand the interior conditions of the sun. The hope is that to advance some of these techniques to include the magnetic field effects, and not only study the interior conditions, but also study the solar atmosphere. Because after all these waves that are being generated by motions inside the sun, generating certain waves that are traveling through the solar atmosphere and perhaps also contributing to the heating of the corona, all these waves. So, yeah. And of course, if one is able to understand the magnetic properties through these waves, one hopes that one is able to predict these sunspots, which are ultimately the foot points of all these major events, like the coronal mass ejection, solar flares. All of these events are rooted into the sunspots, which are intense localized regions of magnetic fields. Having predicted the magnetic fields, one may be able to predict in advance these space weather events. So that is one.
Thank you. So that's given me a lot of note points to ask details about. So thank you for sharing that short, perspective of your field of study of the sun. So Durgesh, you just mentioned that there is some cycle of the sun which happens, and I do have a picture here which is after this. So we see some sunspots which were mentioned by you, and there's a date changing at the bottom, which shows that the sunspots are actually slowly moving across the face of the sun.
Yes.
So do we infer that the sun actually rotates?
Yes.
And so what is
So essentially period? What it shows, and it was actually discovered by Galileo, right? When he pointed telescope to the sun, he discovered those, like, sun guard was not so neat and clean anymore. Sun guard has spots, and he got into trouble because of that, but that's a different story. But he did discover those sunspots, and later on we found out that these sunspots are really, really highly magnetic regions. And so Galileo discovered it in 1600 something, and we discovered that these are really strongly magnetized region in 1919 because of George Hale, who was an American astronomer. And he was actually looking at the sun and trying to understand and pointing slit of the spectrograph at different places. And he pointed at one place, he found that the spectral line, if you know in your lab, that it split it. And that is splitting of the spectral line actually tells you the magnetic property of that. And that was same year, Zeeman had discovered this Zeeman spectroscopy by splitting of these spectral lines. So now we know that these regions are strongly magnetized. Why do they form, and how do these sunspots form, and where does the magnetic field come from? And I was going to point to Professor Nishan Singh. He mentioned all this tabla and basic physics into it. So he tries to put in all the fluid dynamics knowledge and concept of something called magnetohydrodynamics to try to understand how these sunspots form and how the sun's magnetic field originates. Because if there was no magnetic field on the sun, then sun would be a very boring star, because all the activities which you are seeing, that wouldn't be there. Because if you go to your next slide, these are radiation coming in extreme ultraviolet, right? And what we know that most of those bright regions you see, right, where you have the stronger radiation in ultraviolet coming, they are the region with the strongest magnetic field, right? And I mentioned to you that these are the ones which are creating a lot of problems in the geospace environment because they're getting absorbed, and they're all related to the magnetic field. And as it happens that those sunspots which you saw, they appear and disappear with a time scale of 11 years. So today, for example, there is no sunspot. you will see that the number of sunspots will start increasing. In 6 years, it will go to maximum, and then it will start coming down and go to no sunspots again after about 11 years. Now, it is not always 11 years, and that is also a big open question. And that's where you have the generation of magnetic field, and it's called solar dynamo. And that again, Nishant works on. And its effect on various other properties like magnetohelioseismology and so on can be figured out. So that gives you solar cycle. And if you count these numbers, it goes from 1996 to 2006. So that's 11 images. And that essentially shows you going in the anti-clockwise direction. So 1996 was the time when the sun was at minimum. There was almost no sunspots. And then you saw that when the sunspot number increased, sun was at maximum in about 2001 when you have really strong brightening in ultraviolet. And then it goes back again to 2006 when there was almost no sunspot. So that essentially defines the solar magnetic cycle.
Lovely. So I'm just summarizing the thing that, so we see some dark areas on the sun. That is because of some changes in the magnetic field on the sun's surface where the temperature goes down and it looks darker. But although it looks darker in our visual light, it might be emitting higher energy radiation and not the visual light, which makes it very bright in other rays, which we need space to go to space to find. And these are pictures taken actually by a spacecraft.
AIA on SDO, Solar Dynamics
on the Solar Dynamic Observatory over maybe Soho. A decade. Soho has taken these pictures, and the bright spots that you see would be darker if we saw it just visually?
In the visual light, yeah, that's right.
Okay, so that's quite revealing that,
So whatever you see from ground, which is very, very dark, if you go to space and see it in different wavelength at high energy, it will really appear bright.
Amazing. And that has been studied over years, and you realize that those bright spots increase and decrease over a cycle of 11 years. And the sun itself has a rotation as well, which we saw in the...
right, so sun itself rotates, so it differentially rotates, right? So it doesn't rotate like a solid body, like if we take a ball and rotate, it doesn't rotate like that. The equatorial part, which is at the center, if you put a line at the center, there if you measure the rotation, it completes one rotation in 27 days. And when you go towards the North Pole or South Pole, then at the pole it takes about 35 days, right? So it rotates faster at the equator and slower at the pole. And that is actually a fundamental thing which essentially generates the large scale magnetic field on the sun. And that you can tell more about it if you like to add. But that is the main reason for generating the magnetic field and amplifying it to a level that it can produce big sunspots.
These are mind-boggling facts that we are coming across, and in fact, I think even realizing that the sun itself has an axis along which it rotates and then rotates at different speeds, it's amazing. So I'll ask Nishant, so why is this rotation different at different places? Because the Earth, when it rotates, I think it's 24 hours at all places on the Earth. So why would the sun have a different rotation?
So this actually leads to a very complicated problem. Why in general any shear is produced? It's not just the sun. If you look at any astrophysical body, pretty much, I mean, by and large, say galaxy, your Milky Way galaxy, even that is basically differentially rotating. By differentially rotating, one means is that if you go outward in radius and measure the azimuthal velocity, so you remember that you measure azimuthal velocity as you go outward, the velocity changes at each radius. So that basically produces a shear-like motion. So I can depict it by just making a motion like this, a shear-like motion. Sun is also rotating differentially. The way it comes...
If it was like an onion, then the center would be faster and it would be slower outside in outside layers.
Yeah. So sun's differential rotation is actually very complicated in the sense it is not only rotating differentially in latitude, it is also differentially rotating in the radius. So you have to imagine it a little bit. Yeah. The way it happens, of course, this is another area of active research. How do you produce differential rotation, or how do you produce motion to begin with? A star could be born by simply a uniform rotation. Yeah, you can start off as an initial condition a fluid body with a solid body rotation. At each point on the surface, the gravity is pointing towards the center. So at each different latitude, your gravity vector is making an angle with a rotation axis, solid body rotation axis, right? This seems to put a force and leads to a redistribution of angular momentum of each different layer of the sun, and redistributes in such a way that the differential rotation is produced. It's a very complicated effect. It goes by a name. At least one popular theory to produce is called a lambda effect, which has now been somewhat confirmed in a bunch of stars. Pretty much all stars are expected to rotate, differentially rotating. Yeah? And that is the key to produce the magnetic field, as Professor Durgesh just said, because shear naturally stretches out the magnetic fields that are there by other reasons. Some small scale magnetic fields you can produce by mechanisms that are operating at a very small length scale, but on a scale of the entire sun, you find that the magnetic activity, it's like a magnetic field line going all around the sun, like entire toroidal belt. So such large scale magnetic field, how do you produce? That's a key question, and differential rotation helps in producing such very large scale magnetic fields. In basically, after all, you are injecting energy. You see, where are you producing the magnetic field from? All you have is a plasma which is electrically conducting, and you have motions in the plasma, which in the case of sun or solar like stars comes in terms of convection motions. You know that there are convective motions that are helping escape the radiation that is produced well within the star, and that radiation passes through a zone called convection zone, and then it leaves at the surface and reaches us. So that's basically roughly the trajectory that the radiation takes from within the sun. So the convection zone is a zone where there is a lot of plasma motion. You must have heard that if there are charges in motion, it produces electric currents. Those currents can be thought of as sources of those magnetic fields. This is all self-sustaining, right? This is entire thing is self-sustaining process, and that's why it's called a dynamo mechanism. So all of this is somewhat linked to the rotation of the star and differential rotation of the sun. Yeah. Yes, it's exactly like that. If you go even radially inward, you will find that the layers are rotating differently. If you go in latitude, you'll also find the layers are rotating different. It's a very complicated motion you have to imagine.
So if you think of a ball, the layers are the surface rotating differently, but if you go inside, then you can look at it from center, you go to different heights, radiuses, then you see they are rotating differently. So it's onion layers.
It's quite a complex system. So
And so then these rotations basically, so I just didn't complete the story that this motion, the energy from this motion goes into the magnetic energy. That is where the magnetic fields are produced. The fields that you see are producing those very interesting effects in terms of coronal mass ejection, solar flares. These are reconnecting events taking place, but reconnection of magnetic field lines that are produced by the dynamo that is operating well within the sun, and effects that are seen outside in the solar atmosphere and reaching us and affecting our terrestrial atmosphere and us.
Wow, I can also hear some words in here which are like dynamo, which is already, we study in school that, something rotating charge can cause a magnetic field, moving charge is a current. And all these things are actually, at a much bigger scale happening in the fluid plasma of the sun, and then causing all these wonderful effects which we are studying through various ways. So I'll come to Helen again. So can you describe to us over the history of solar study and how we've grown in strengths and advancement in studying the sun?
I don't think we've got enough time for that.
Well,
history of solar study. Well, Durgesh mentioned Galileo and looking at the sunspots. I'll say a little bit about recent satellites. I've worked on quite a few different solar satellites, and earlier we saw some images from the SOHO satellite. That's the Solar and Heliospheric Observatory, which is one of the most comprehensive observatories that we've ever had, but Aditya will be the next, I think. But that was launched in 1996 and is still operating now. So it has a whole suite of different instruments. So people have to work together on different instruments or within each instrument. So that was operated from the Goddard Space Flight Center, where I had to go because I was part of the team to operate one of the instruments, or to put the science for one of the instruments on the SOHO satellite. The instrument I worked on was in the ultraviolet, and it was a spectrometer. But we all worked together to study the sun in different aspects. And the interesting thing about SOHO is that it was at this very special point called the Lagrange point, which is a balance between the Earth's pull of gravity and the sun's pull of gravity, that Aditya will also be at. So in some ways, Aditya is taking some of the historic content of what we did with SOHO, but improving it a great deal, and different instruments, different ideas, different targets coming for it.
That's great. So
one thing I should say is that I'm sure Dergish will say a little bit more about the instruments, but we saw that beautiful eclipse. Well, you can simulate an eclipse with an instrument called a coronagraph, and SOHO has a coronagraph, and it's still operating after all this time because it's the only one that we have to get very good. I mean, an eclipse, I don't know, you've seen it, lasts 2 or 3 minutes at most. Okay, you can get a lot of information, but it's only 2 or 3 minutes long. You want to observe with that as much quality as possible continuously. So you use an instrument called a coronagraph.
So you cause an artificial eclipse.
An artificial eclipse.
Wow.
And I think Aditya has a very special one, but Dergish Tripathi can say more about that.
Move to the hero of the story and ask Dergish, who's in charge of part of that, and then can you please describe to us what this is and how important this is to solar astronomy across the world, not just in India?
Right. So as Dr. Mason mentioned, the first solar satellite, which went, a comprehensive solar satellite, which went to the first Lagrange point. If you just go back to that, this L1 point, so that bright thing is the star, sun, and we have Earth. And if you go to L1, then you have a continuous view of the sun, because when the Earth moves around its orbit, then that point will also move along with it, because that is the point where the gravity or the gravitational force balances out, right? So if the body moves, then that point where the force balances out will also move, and you put a satellite, then it will keep observing the sun 24/7. And that is why the Solar and Heliospheric Observatory from ESA and NASA was put there to get a comprehensive view of the sun. Now, there was a coronagraph there, and which is still working, which is creating artificial eclipsing. But there were a number of things which we learned from that we could do further and go beyond. There are a lot of discoveries made with SOHO, but as I say, there are known unknowns, and that's why you design an experiment to figure out what you don't know. But then there are a lot of unknown unknowns which you discover, and then you keep studying further. So there have been huge advancement in our understanding towards the sun since then, and there have been a number of satellites after the SOHO, and that was stereo, which was 2 spacecraft and going one in the one direction in the Earth orbit and the other in the other direction, and trying to look at the sun as if you are looking from your 2 eyes to look at the things in 3D. Right? You need to have 2 vantage points to look at objects in 3 dimensions. And the idea was that when this eruption is coming towards the Earth, then you will be seeing it from 2 directions, and you can map and monitor whole thing. Unfortunately, it was launched in solar minimum and nothing happened, the timing and all. But still, they got some really good data which made them understand and understood things better. Then we had Hinode satellite from Japan. That was also ESA and NASA collaboration. And then recently we had IRIS, again NASA, and then Solar Dynamics Observatory. But none of these are on L1 point, right? And all of these are carrying instruments which are complementing to each other. So we decided, or rather ISRO decided, to go back to L1 point and have a suite of instruments which are complementary to all these instruments which are there on all these satellites which we mentioned, and some looking into a little more into details. So for example, this Aditya satellite is going to be at L1 point and is going to carry 7 different instruments, right? So yeah, one of them is essentially creating artificial eclipsing, right? And the idea there is like Solar and Heliospheric Observatory SOHO had 3 coronagraphs, right? Creating 3 instruments, creating artificial eclipsing. One was going very close to the sun and trying to look at the nearby area. The other one was making a bigger moon and looking at the further out region, and then even bigger moon to look at the further out region, because you see the intensity drops out very fast. So you cannot see everything with one telescope, right? Unfortunately, the one which was very close to it, it did not work very much for a very long time, only for 2 years, and there were some technical glitches which happened and it failed. And that, the limited data set it provided, it was very useful to find out that that is the region which is one of the most important regions if you really want to understand the dynamics of the solar atmosphere. While the other 2 are still there, and they are going to be relevant even after this is launched, because that kind of observations are never there. So we are still banking on SOHO to work for another 20 years, which has already worked for more than 25 years now. So that is going to create eclipses as possible, as close as possible to the way the moon creates, and that will look at the radiation. And what we will also do with that, which has never been done from space, is to measure the magnetic field. So if you go back to your eclipse structure here, so we're going to cover this region, and we are as Dr. Mason mentioned, that's magnetic field. At the moment, we don't know what is the strength of this magnetic field is, right? So while we know the sun's surface is magnetized, and from there we produce some mathematical modeling to try to figure out what the magnetic field is. But first time we will be measuring that directly from one of the instruments, that is coronagraph on Aditya L1. Then the second one is to, as you saw, there are a lot of images over the 11 years in ultraviolet. This is in extreme ultraviolet. This covers a region in the atmosphere which is very, very important. But now we know that this information is not complete unless we combine this with something else. And we only discovered it after we looked at this, because we know there is something missing. And that is why we thought that with Aditya we should provide that complementary information, which has never been done. Image the sun in the wavelength range, which is not extreme ultraviolet, but rather ultraviolet, right? Which is coming, so this is absorbed in our ionosphere, but the ultraviolet comes all the way to the stratosphere. So that is, for the first time, we will be imaging the sun in that particular passband. And that has 2 effects, or 2 advantages. One is that it will cover the range, the height range in the solar atmosphere, which has not been mapped so finely, and that will be complementary to what is being provided now with already existing satellites, to map the atmosphere all the way from, for example, if you're looking at the Earth, from Earth's surface all the way to the ionosphere. If you have satellites looking at data, then you have a complete coverage. And the second thing is that it is going to provide the study of the radiation, part of the radiation, which is coming into your stratosphere of the Earth. And that part of the radiation is used as a catalyst for ozone and oxygen layer formation and ionization. So then we are complementing 2 different sub-areas of heliophysics, if you like. So solar physics is one area, and the sphere of influence of the sun is called heliosphere, and the physics which deals with the whole sphere is called heliophysics. So we are providing that complementary information for geospace, which is governing the Earth's atmosphere and the sun's radiation and the sun climate relation.
That's amazing. I mean, managed.
Am I right in thinking that that instrument was built here?
Right, yeah, so that instrument is called Solar Ultraviolet Imaging Telescope. And if you saw on the other side, there was a model put there. That instrument is being built here. We developed all the design, and we have some people, because to develop such instruments, you need to have a very sophisticated laboratory. You cannot get into that laboratory unless you have covered yourself with 3 layers of clothing. Only eyes are open with 3 layers of gloves. You cannot wear the same shoes. You have to change that. You cannot use the same pen which you use outside as well as paper which you use outside. So these are specialized labs, and ISRO has kindly provided that laboratory for us. And we have some people from here. They are working in the ISRO labs. And as of now, the box of that telescope is being tightened up to be given for vibration test. Because when you put a satellite or instrument on a satellite, and the satellite eventually puts on the rocket, you want to make sure that when the rocket flies, nothing should fall off, right? So you have to do this level of vibration, like the rocket goes and it vibrates like that. So you have to shake your instrument before you give it on the rocket to even more level of vibrational amplitude, so that you make sure that nothing falls off, and then you give it away. So at the moment, the box is being tightened, and we will deliver it very soon for this vibration test to ISRO.
Wow, so that's also an engineering feat. It's not just a science goal, but an engineering feat which has been achieved. And
I can add that into this.
Sure.
Now you started me off, so I can't stop.
That's what we're here for.
So when you build these kind of instruments, as an astronomer, as a scientist, you can envision an idea that what actually I would like to study, which will help me understand the sun, for example, in this case, sun, and to study how it is going to affect our life. But that is just a conceptual level. And to be very honest, when I proposed this, I didn't really know that what level of detail one has to go. Now, I tell you that you need to have a bunch of mechanical engineers, bunch of thermal engineers, bunch of electronics engineer, bunch of computer engineers, and all those working in the periphery of any engineering subjects are involved. And before you start cutting metals for these things, you have to decide what kind of screw you are going to put in at what place. Everything has to be neatly planned so that you can design it. These are going to be really, really far away, right? These instruments, they're 15 lakh kilometers, 1.5 million kilometers away at L1 point. You have to regulate it through computers. So you have to, in some way, build robots on those payloads that you can give a command and the robot will execute your observational sequence, right? And remember, the Earth is rotating, the L1 point is there, so we don't have 24 hours contact with the satellite. The satellite will keep taking data. It will send us only during the time when we have contact. So we have to plan everything, upload the program, and you have to rely on that robot which you have designed up there to execute your observing sequence. It's not like going to the observatory and focus your telescope somewhere, but rather depend on what computer software you have written. And so you can imagine the vastness of requirement for designing any such payload and instrument and experiment.
Excellent, and thanks for informing all these things, because I'm sure in the audience there are people who are not just into science, but they might be engineers also, and thinking of how can I contribute to astronomy. So this is one contribution that is already there, and in the future there might be some great missions planned by the present scientists for whom you will be the future provider of talent and skills. So lovely to have that information here. There's a picture of Aditya as a whole unfolded out here in space that we have. So what is this long thing which is here? May I ask?
Right, so I mentioned that there are 7 instruments. I only spoke about 2, otherwise you'll have to stay. If I keep speaking all of them, then you have to stay till midnight, and sorry. If you want me to do that, I'll do that. But this is an instrument which is called magnetometer. So what it's going to do is, like, sun is doing this ejecta all the time with different time scales, of course, depending on which phase of the activity it is in. But all those is not going to be geo-effective, if you like, right? They are not going to connect directly to the Earth's magnetic field and then creating Hazardous effect on the ground. Only those ejecta with given direction of magnetic field is going to be connecting with the Earth's magnetic field. How do we know that? So we have put this boom, and on that we have put 2 magnetometers, right? So what they will do is, when the ejecta is coming, you are sitting at one point. If it is crossing through here, then you measure the magnetic field. And if you have that kind of direction, which we know that what kind of direction you need for it to be geo-effective, then we can give space weather modeling. That, 15 lakh kilometer ahead of the Earth, there is this ejecta which is going to go, and it can be geo-effective, right? Now, why this boom we could have put on the satellite? There is something called magnetically clean environment, right? In our satellite, so there are a number of magnetometers up in the space, they are doing it. But those are magnetically clean because there are no magnets in the satellite itself. There are no current, there are no motors, and so on. But since this satellite is carrying 7 different payloads, and each of them, they have different requirement. There are a lot of motors. For example, in suit, we have 2 different motors. One is to rotate the filters which you are using, and then there is a shutter which is controlling the exposure time. So as we talked earlier, like, the current generation and the motor, moving magnetic field, moving charge, creating magnetic field. So that is all happening internally in the satellite. So how do we know that the magnetic field we are measuring is not because of our own satellite and it's only because of the sun? Okay. So what we do is put a boom and put 2 magnetometers. One is nearer to the satellite and one is far away. And we can model what the magnetic field of the satellite is going to be and see if the magnetometer is going to measure that, and then the other one, which is further away, and we can subtract off the magnetic field generated by the satellite, and then we know that what we're getting is from the sun. So that is why that long boom.
Wow, that's quite smart. So you have to, and it's good to know that all these things are thought of. These are such fine, yes, practical things which have to be thought of to design a spacecraft which is going to be 15 million kilometers away from us and operating almost by itself with commands from you. It's amazing. So I think we've got so much information now, but we have to, of course, end the session. And towards that, I would ask each of you, that what is one thing that you are, excited about from Aditya? You might have answered, but it's great to know it again. So starting with Helen.
Let me think. Well, I want to understand better the storms that come from the sun. So Aditya is able to observe the sun and then sample what comes off the sun. And it also has, Durgesh hasn't had time to mention yet, it's got X-ray instruments on it, which will see the X-ray radiation that comes from the sun. So I'm quite excited to see that connection between what happens on the sun and what Aditya samples.
Thank you.
You go ahead first and then.
Yeah, so far I have essentially focused on the interior of the sun, and Aditya will provide me an opportunity to actually engage with the solar atmosphere. So that is what I'm looking forward to, that the data there, I'm looking to basically test various ideas that are still in mind, but based on the data, we'll try to see if more information about the magnetic fields can be. I'm generically interested in the magnetic fields. So yeah, I'll continue to engage, but more towards the outer layers of the sun now. Thank you.
To me, there are various reasons. One is professionally, of course, I want to be ambitious with this and see whatever, but there are also emotional ambition, right? So I have 2 kids. I consider this to be my 3rd kid, and I wanted to do well and do everything which we have planned for.
Okay, so that's So I also want to ask you, so we have known about ISRO's and IUCAA's contribution. So just to end, would you like to mention all the other contributors who are part of this mission and how it's a collaboration, nationwide, international kind of collaboration?
Right. I mean, see, as I said, any building of any of these instruments requires wide expertise. So of course there are 7 payloads and 7 different institutes are leading each payloads. So for example, the coronagraph is being led by Indian Institute of Astrophysics. Then the Solar Ultraviolet Imaging Telescope, we are leading it here at IUCAA. There are this hard X-ray and soft X-ray, and one of the particle instruments is being built at ISRO. Then one instrument is being built at Physical Research Laboratory, Ahmedabad, and even the magnetometer is being built by ISRO. But we have, building instrument is one thing, but we also need to have scientific ideas and scientific discussions and all that. And whole country is somehow, some way or other, our partner to it. In suit, we are leading it, but a lot of people from ISRO, of course, are collaborating. But we also have hardware collaboration from Indian Institute of Astrophysics and ISER Kolkata, and as well as from PRL. So the people involved in helping us build this. And eventually, we would like it to be a mission of international standard, and therefore the whole international community is invited to look at the data and do science and make the best use of it. And that's the way the solar and heliospheric physics has worked, and we are following that path.
Yeah, I just wanted to say in that regard, the instruments on Aditya are amazing, so they'll provide a lot of information. But we often combine those with other instruments that are in space. But the thing I want to say is that this satellite is built almost entirely by India, designed everything. So India is really leading the world in this technology. It's the first solar satellite of this sophistication dedicated to this, studying the sun. But it will bring in collaborations with other, NASA or European Space Agency who can complement and who will hopefully work with India to join the observations and understand the sun better together.
Thank you so much. So one last question, which everybody must have. So when are we seeing it go up in space and getting operational? Approximately. When do you expect it?
This year, 2022.
Oh. Great. I'll take that short answer as valid. And so we are looking forward to this happening soon. And please look ahead, look at the news, and we'll keep you updated. There's a lot of outreach happening at IUCAA where you'll get to know more about this. We've had a longish session, but we can still take a few questions if you're not tired throughout the day.
I think we could, yeah.
So we'll open up the floor if the volunteers are there. You have a mic? Okay. So let's say 3-4 questions from the audience. Let's have some lights on the audience. Some light on the audience, and we can start taking questions from the back. Let's say 4 questions. Oh, you stood. Okay.
Yeah. Sorry. So, sir, this mission of Aditya L1 particularly is manless, right? So we don't have any astronaut or someone is sitting in the this. So what is the pros and cons of if we do a mission with man or with astronaut? What are the pros and cons we look while designing this kind of mission? I just want to ask to you.
So what are the pros and cons? Oh, sorry.
Well, it's expensive and somebody's life is involved. So you have to be extra careful. But before you do that, you really need to understand when the solar eruptions are coming. Right? So manned mission you cannot do, you cannot send it to L1 point because it's too far away. Gaganyaan, you probably have heard, ISRO is planning to have a man on moon very soon, and this Gaganyaan is being planned. Number of training sessions have happened, I think, for the astronauts, and there is some time, but it's expensive. It's more expensive than you think. You know, putting a robot with this satellite is much easier than putting a human. And going to moon, how does it help also is not really clear.
I have a basic question. Like they said, our sun is a second or third generation star, yellow star. But when it's going to end its life, it's going to end as a white dwarf. So why it's going to end its life? Whereas, I mean, will there be another sun after that, or?
I could take the sun. The question is whether the sun would be ending as a white dwarf, and if so, why? I don't think.
Yeah, the sun will end its lifetime expanding out to be a red giant, and then it will explode off as a planetary nebulae, and a white dwarf will be left in the core. Was the question as to whether there will be another sun after that? Yes, I thought that. Yes, I mean, I think that the universe goes on. The only reason we're here now is that, in fact, there was a giant star before the sun, which was bigger than the sun. If the sun were 10 times more massive, it would end its life in a very spectacular way as something called a supernova, as you've probably perhaps heard of, biggest explosion in the sky, and that then the core would be either a neutron star or a black hole. So that happened before the sun formed, and that's what produced all the elements: carbon, neutron, nitrogen, oxygen, and we wouldn't exist. So that's why they say we're made of stardust. So it's possible that when our sun ends its lifetime, another star will form after that. It's possible. We won't be here to tell.
I have a too far in the future. Yes, please.
So, is this a myth that there is a there's a hole in the ozone layer towards western side of the US? That's why it causes a lot of skin cancer. So, is that the myth or is it reality?
The ozone hole.
So it's not really relevant to this talk, but the question is there a ozone hole on the west of the US which is causing a lot of cancer?
The ozone hole, as you're probably aware, was discovered in Antarctica. Yeah. And that's because the polar regions are very special in the way in which the atmospheric circulation goes. So that was the first warning that we had, that basically we were destroying the ozone hole. And since then, a lot has been done to reduce CFCs and the gases which are causing that. And I believe the ozone hole is recovering. It's not there all the time, it's a seasonal thing, but I believe it's recovering. I'm not aware of one over Russia, but that would be over the Arctic, and the Arctic conditions are not quite the same as Antarctica. Antarctica is a landmass, and the circulation is rather particular to Antarctica. I haven't heard about that, but I'd be surprised if there was.
So it's probably I
have a question. As you mentioned in the beginning, solar flares or solar storms do impact our lives, and Aditya 1 is geared up towards giving us advance warning against this. So my question is, currently without Aditya 1, how prepared are we to get these kind of advance warnings, and how much will the picture or how much is the picture expected to change once Aditya 1 is stabilized in Lagrange point 1?
Right. So the two questions, right? So first is, how prepared are we? So
there have been. How prepared are we currently? Is Aditya the first of its kind, or?
Right. So there are two ways of doing it, and I think at the moment we can give about looking at the sun itself. So there are a number of satellites which are looking at the sun, like GOES satellite. They are essentially geostationary satellites. They're looking all the time at the sun and monitoring what the sun is going to do. And based on that, looking at the complexity of a given region, you can say that, okay, there is a probability of this region to be going to give flare of this energy by 50%, or something like that, right? You can never be 100% sure that it's going to produce a flare or not, but that kind of probability can be given. And if you're interested, there is a website called solarmonitor.org. You can designed by Peter Gallagher. You can look at that. What it does, it looks at different wavelengths images of the sun, and below it gives, okay, this region is going to have a probability of 20% to give a flare. Now there is another part of it is something called machine learning and deep learning, if you're a computer scientist. What it does is it looks at, because everything is created by the magnetic field, it looks at different properties of magnetic field, feeds the data into their model, and tries to figure out that what conditions are changing, which will give you flare. So these are much more advanced. They are giving you warning when the region are seen on the surface of the sun itself. So it could be 1 week long warning. When we're talking about the warning in real time, that is when you need at L1, because once it is at L1, it doesn't take very far to reach to you, right? I mean, it has already traveled from sun to L1, and from L1 to here is only 1/10 of the distance between the L1 and the sun, right? So that is giving you real-time warning that, okay, it has come, and it has a magnetic field like that, right? So there are two aspects to it.
I'll just add to that. With regard to warnings, certain things can be done to put satellites into safe modes or to correct for the GPS and things like that. So what's really important, as Durgesh has said, is to know maybe the probability that something's going to happen, and then the severity, because there's these particles shooting out and then there's clouds of gas coming towards us. And it's kind of an international effort, the space weather, which is first of all understanding what causes this on the sun and then tracking it and predicting it. So I think Aditya will play a very important role in that regard. And then there's also as Durgesh has said, the numerical modeling of that. It's a little bit like space ordinary weather predictions. You know, it takes a huge amount of effort to measurements, but also modeling in order to be able to predict the weather. And then that's not always completely accurate in that regard. So it's an international effort of which Aditya will play an important role.
And given that we are also going to start being a spacefaring race again and going through Artemis missions where humans might be going to moon and further off, space weather monitoring and prediction will become very important.
Yeah, what I didn't mention when I was mentioning the effects is, of course, the radiation effects on astronauts is severe. Yeah. So basically, I think between Apollo 16 and 17, there was a large solar flare, which had the astronauts actually been on the moon, they weren't, fortunately, they would have got a fatal dose of radiation. They can, of course, take protective measures by going inside or cover whatever, but it is important for any people on the moon that they also have very good space weather warnings.
Sure, thanks. We'll do that. Is the mic there already?
Yes.
We'll take that and then come to you.
Yeah.
Then we'll finish.
Good evening, ma'am, and good evening, sirs. My question was, why aren't spacecrafts put in the Lagrange point 4 and 5? I mean, there's a very less amount of spacecrafts put in the Lagrange point 4 and 5. 3 is understandable. It's directly opposite to the directly opposite to the position of the Earth in the orbit. But why aren't there a lot of spacecrafts in 4 and 5?
That's a very good question. And it's not that they are not being put. It's really far away and it's expensive. And to tell you, one mission, Vizier, has recently been approved by IUCAA, which will go to L5. We have a proposal pending with ISRO to put a satellite at L5. And the beauty of going to L5 is we will be looking at the sun, which is still behind, which is not facing towards the Earth. So if you go to L5, we will look at these regions which could produce effects which are geo-effective much earlier, so we could give even better warning for the space weather. The reason we are not, people have not gone there is like you need to have technology developed and it's expensive. And the other reason is that is more mathematically involved, is that while you go to L1 and you can orbit around it, at L5 the potential is very deep. So all the things you put in space, there is something called space debris, right? If it gets into a potential which is deep, it doesn't not get enough energy to go out, right? So a lot of debris just gets inside that potential. And at L5 is such a location that the potential is very deep. So a lot of the debris is there, so you really have to also make sure that your satellite doesn't get hit by one of those debris.
Yeah, can I add to that? Yes, I think it's a really good question, and as Degesh says, there are plans for Europe to put one at L5, and I think also plans for India. But what I wanted to mention was at the moment there's 2 satellites which we haven't mentioned, which are going very close to the sun. One is called Parker Solar Probe, which was launched in 2018, and one is called Solar Orbiter, built by NASA and ESA, but also with Indian participation, I think. And they are actually going very close to the sun, so that satellites are sent in different orbits for different objectives, and they again are wanting to study the sun and the solar wind that flows off the sun.
I'd just like to add one thing on the time scale for the Parker Solar Probe. So it is named after a scientist, Professor Eugene Parker, and he discovered solar wind, and he gave actually a theoretical model, and the discovery came later. And it was envisioned that to really figure out what the solar wind and what those particles and properties are, you really have to go as close as possible to the sun. And the first idea of designing Parker Solar Probe started in 1958. And eventually, because you had to go so close to the sun, finally the technology was developed over the years and years and years, and finally it was launched in 2018. So it took so long from envisioning an idea to eventually working it out in technology and then making it happen, right? So
that's great. And I think there's also an undercurrent that all these need public support a lot, because I'm hearing this word expensive quite a few times, and there's so much spending by each government on so many things which may not really be so needed, but and these are very important things. So I'm just putting this out. It's not a.
Can I comment on that, Samir?
Yes, please.
Because I think yes, they are expensive, but all of these things we've been talking about, even going to the moon or the sun, they push technology. You've got to develop new materials, and these things come back. There's spin-offs that they're used in everyday life, and they improve our lives in different ways. So I think also education, in a sense, that people are really invested in it. By doing these, you've really enhanced your technical capabilities and your engineering capabilities dramatically in all the different ways that Professor Tripathi was talking about.
That's why it's very important for us to all, support such projects which will get back our investments in some way or the other. May not be immediate, but there will be some effect. So we'll take one last question from the gentleman here and finish it. Please take the mic. Thanks.
I already got. My question is non-astronomical and non-scientific also. When this project started, and because this is going to launch this year only, so how many years it took? That is the only question. Thank you.
Right. So the first proposal we put in for this, okay, so let me take you a little bit of history. ISRO in the beginning was planning to have a very small satellite with one instrument and also with the lower capabilities, just a coronagraph imaging. And that was supposed to be launched in 2010. Of course, any space project has its, we're doing it for the first time. We have to develop our technology, we have to develop expertise, manpower, and so on. So it was getting a little delayed. And in the meantime, number of people have returned to country with various kind of expertise and ambition. And we should give credit to Professor U.R. Rao. He was heading the apex body of ISRO. And he said that, why don't we aim bigger? And of course, this instrument which we planned is not going to go, but we can make it even better equipped. And instead of going to this low Earth orbit, just going around the Earth and having not being able to see the sun all the time, but rather go to a point which is technologically also challenging for ISRO, because it also gives them an opportunity to create some technology which is fulfilling and enriching. But also to scientists, it will give you much better capability and equipped instruments which you can do science with. And then so this thought is started in around end of 2010. In 2012, this announcement or opportunity came from ISRO that you start putting in for any idea you have for different kind of instruments. So that's the time scale. And then from there, so when you put in a proposal, it goes through a various level of review before it is accepted that you can, yes, we will fund it, because you have to demonstrate various things. I mean, you can have a very nice idea which may not be realizable given the technological advancement and so on. So that goes through critical reviews at various stages before they say, okay, we will go ahead with this. So it was approved by the end of 2015 after a number of reviews, which it took 3 to 4 years. And we started working on it full time from around 2016 after the approval. So since then it has been 7 years, and it will be launched in the 7 years. But it does take its own time, from the inception of the idea to eventually launch it.
So we wish it all the best, and a big round of applause for the scientists here who have worked hard in envisioning this. A big round of applause to some of the engineers who are actually in the crowd who have made this part of this telescope, and to some of them who are right now at ISRO headquarters putting it together so that it can go for the launch. A big hand again. Thank you so much. Thank you. That brings us to the end of this wonderful session, and also to the end of this wonderful day at IUCAA, the open day. We've enjoyed having you all here in person. Thank you. Keep coming back. We'll have a lot of public programs throughout the year, of course. So keep a lookout for all our programs. Thank you so much. Have a great evening.